Hey everyone, another acids bases lesson, this time based around universal indicator paper. Now, school students will probably be more used to seeing this green liquid that is added to different substances to see what colour changes occur to determine the pH. But Tiny Science Lab hasn't been keen on sending out liquids because we're, scared about liquids leaking and that sort of stuff. And so we supply universal indicator paper, but we're sort of going to make our own testing liquid, okay? So that's the focus of today, of this lesson, making universal indicator liquid using the paper. And we're also going to use litmus paper. Now, we didn't seem it worthwhile enough to actually distribute red and blue litmus paper, so I'll just be doing this as a demonstration. Maybe you've got some. And litmus, I believe it's based on like a lichen that's found on trees. I could be wrong. You can do some fact checking, but that's where I think litmus is originally from. And litmus turns red in the presence of the acid, so red litmus stays red, blue litmus goes red, and it goes blue in the presence of an alkali, so blue litmus will stay blue and red litmus will go blue. Anyway, we'll find that out, won't we? First things first, let's get ourselves a beaker, put in a good 10 ml of water. Even I'm going to put a tiny bit more in, to be honest. And I think three of these pieces will be enough, but you know what? I might just do 4 because I feel like it. So I'm going to be extra generous. I don't know. I can't even. I think it's fairly thick stuff, this. There we go. 4. I think that's 4. Anyway, close enough. Rip it off. Rip it off. And roll him up in a ball. Roll him up in a ball like this. Just give it a bit of a squishy. And drop it in. And it is important to make sure that your equipment is fairly clean when doing acids and bases stuff, because it's very easy to get contaminants. You'll know because you'll get some unusual colours happening which are unexpected, and that's usually because you haven't washed up the equipment very well. Anyway, let's put this on there like that, center that up, and I'll get my tweezers out because tweezers are good for holding things, and I'm going to really give it a nice bit of a blast here and give it a bit of a stir. And because I've been generous with the universal indicator paper, it's not going to take long for those dyes to come out. And I guess I'm hoping that I get a green liquid. And the reason I want a green liquid is because I'm hoping my tap water is fairly neutral, and that the beaker is clean, free of contaminants, and it looks like I am getting this green. Now, you could be doing this activity in a rural area where you may be using tank water or bore water, and your colour could be completely different because your water could actually be acidic or basic. Where I live up on the hills at Somersby, I know that it can be slightly acidic. And so I know people who actually run their bore water over oyster shells. And those oyster shells, calcium carbonate, actually help neutralise the acidic bore water. There you go. And one last blast. And we're about there. I know we're about there because I can see the paper has gone pretty colourless, and that's a good sign that we've got all the dyes out. There we go. Okay, I'm very happy with that. Beautiful. Pop that there. turn my fire down, turn my fire off, and let's get a conical flask out because it's nice to see things in a conical flask. I'm a bit worried that I haven't washed this equipment up properly though. And to set a good example, although I can probably use my fingers, I am just going to pour that in. Look at that! Golden! Not golden, but green. Beautiful green. And the paper has gone white. Before it was yellow. And I might even do a little bit of washing up right there. Perfect. And again, give that a squeeze. Excellent. And is my pipette clean from a previous lesson? What I'll do is I'll put some nice clean water in there and I'll like suck it up, push it out, suck it up, push it out. That's how I do the washing up. So our first substance is some citric acid. And so let me tap a little bit of citric acid there into the watch glass. And we'll start with some blue litmus. Okay, and blue litmus starts off blue. And it's literally a blue paper. Now, it won't respond at all to a solid. So I actually need to dissolve the citric acid with a little bit of water. And let's pop in my blue litmus paper. And I am expecting it to go red. Oh no. Have I got the world's dodgiest litmus paper here? This is the question. Maybe it is old, but it should be going red. 100% this should be going red. Like, how dodgy is that? So, my blue litmus paper, is it out of date? Does it actually have a date on it? But it's not turning red. Blue litmus should turn red in the presence of an acid. Let's try a different piece. Okay. Nope. 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 Okay, that's a bum bum. That's a disaster right there, people. So what about if I pop some red litmus in? Well, I'm clearly expecting the red litmus to stay red because litmus should go red in the presence of an acid. And well, it stays pink, pinkish. Wouldn't call that red, but it stays pinkish. Let's hope I have more success with my universal indicator. Let's grab up some universal indicator and squirt that in, and yes! What a relief. What a relief. And if we have a look at the scale, okay, we have a look at the scale. It's an orangey colour, so it's somewhere between the 4 and the 5. So I'm going to call it a pH of 4.5. Okay. Good. Good. Shall we say good? Let's just say the universal indicator is good. And I'll pop that over here and pour that in. And that's going to be right there. And make sure you give things a good rinse. Okay, give it a good rinse. And I'm actually going to clean it with a little bit of kitchen towel this time, not the corner of the tablecloth. Let's pop that there. And the next one is bicarb soda. So, the bicarb soda. This is not an easy way. I've got, oh no, this is all right. Wait, that's enough. You don't need much. Again, I'm going to add a little bit of water. Not much. Well, the blue should stay blue. Oh, you know what? Maybe, just maybe I was using the outside part. That's a possibility, you know. Maybe I was using the wrong part of the litmus paper. Well, at the moment, the blue is staying blue. Let's see what the red does. Oh, I'm hoping it goes blue. It's supposed to go blue. Come on. Please. Please go blue. You're kidding me. I think I've been ripped off. Oh. It's gone a little bit blue. It's gone a little bit blue. Yeah. Yes. The red litmus went blue. What will the universal indicator do? Dun, 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 dun. Oh. Teal? There's a fancy name for a colour. Teal. Ooh. Oh, I don't know. I wonder if I got a good scale here. You know what? I think I'm like using a scale that's I think I'd rather use this scale right here. See that? And in actual fact, it doesn't have really that colour on there either. So I'm going to give it a... Oh, I'm struggling here. Maybe a 10? Okay, maybe a 10. Yeah, on 9.5. Somewhere between... No. Between 10 and 11. 10 and 11. Definitely alkaline though for bicarb soda. Okay. Alright, let's tip him out. Alright. Alright. Water. And okay, the next one is salt. Bit of table salt. Oh! Salt Bay can come and visit me. Look at all that salt. What a duffer. Okay. Blue litmus. No change of colour. Probably because the litmus is dodgy. Red litmus. It says red litmus, but it's more like salmon litmus. No change of colour. Universal indicator. No change of colour. No surprises, because sodium chloride, table salt, is neutral. So, I almost wasn't going to do it, you know. Almost was like, oh, I couldn't be bothered wasting my time. But no, for you guys, I did table salt. Tap water I'm not going to do. Green, blue, litmus stays blue. Red litmus stays red. Green universal indicator will stay green. I'm sorry for you science purists out there. These lessons have been long enough as they are. So let's go to vinegar. Vinegar is a solution. Acetic acid, ethanoic acid, same. Okay, that's what we use on fish and chips. Salt and vinegar chips. It's nice and sour. Used to poached egg. You put a bit of vinegar in hot water to poach an egg because it helps bind the egg instead of the egg going everywhere. Here's my blue litmus. Oh! I was using the wrong part of the blue litmus. I was using like the outside wrapper. Yay! Thumbs up. The blue litmus turns red. Blue turns red in the presence of an acid. BAR. B-A-R. And the red should stay red. Okay, so I haven't been ripped off. What I was using the first time with the citric acid, let me just show you. I was actually using the outer wrapper. Silly Billy. And this acid should go like a pinky colour. Oh, yellow. Yellowy orange. Nice. On my scale, this one's an easy one. 5. See? Matches the 5 right there. See how it's matching the 5? There's the colour, same colour, pH of 5. 7 is neutral. 7 is neutral. Under 7, 7 or lower, is acidic. And so a 5 is acidic. Now, sulfuric acid, hydrochloric acid, they're probably going to be even more acidic. They'll have an even lower pH, which is part of the reason why they're more dangerous. Don't go drinking hydrochloric acid or sulfuric acid. Lemon juice, that's part of the reason. There's a bigger story. But you guys are a bit too young for the big story of acids. Just building up our understanding. I might just dilute it a little bit because it's a bit yellow. And remember how I've said before that sometimes the colour can interfere with when you're doing colour changes. Here comes our blue. Woo! It's gone red. You're yelling at me. It's gone pink. It's not red. It's close enough. And our red litmus stays red. Dun, 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 dun. And our universal indicator zoop, goes yellowy orangey. So another pH of about 5. There it is there. Nailed it. Wash him out. Bring it over here. Tip it. And rinse it. Good. What's next? Soap. Now, at the end of the last lesson, I brought my knife up. So I don't have a knife. So I'm going to use my tweezers and just do a bit of a scraping with the tweezers. I don't need much. Put that there. Good. Add a bit of... Now soap. Soap is made from oils, okay, fats and oils. Fats and oils are quite similar. And sodium hydroxide boiled together in a process called saponification. So fat and oil boiled with sodium hydroxide or hydroxide, and you end up with this a molecule that's attracted to both water and like oils. See, normally water doesn't mix with oils, but soap is basically a molecule that will grab onto a water molecule and grab onto an oil molecule, and so like a grease or dirt. So if you've got greasy, oily stuff, you put soap on and then put water on it, the soap will bind to the two, and so you'll be able to wash away your oil, your grease, your dirt. Otherwise, the water just washes straight off. It's probably discovered around like fire pits where people were like cooking like fatty meat, and then when the wood burned, it would produce like potassium hydroxides. And in the morning when it cooled down, they probably found this chunky stuff in the fireplace, and they found that when they were, I don't know, maybe put water with it, that it frothed up and that it bubbled up, and you could use it to clean. So that's probably how the first soaps were discovered. So very interesting. Basically, detergent is a synthetic copycat. Okay, we've sort of copied the molecule. Okay, so the blue litmus stays blue, and this time I am expecting the red litmus to go blue. That's what I'm expecting. Not much of a colour change there. Okay, so let's just say that the red one stayed red. That's okay. And squeeze him in. Whoa! I'm blowing a big bubble there. Boom. And I like it. I like that a lot. But again, the colour is not really there unless I'm struggling with colours. I'm not colourblind, but some people are, but I'll say 10 to 11, something like that. Definitely alkaline. Definitely alkaline. Which means, what that actually means is that too much soap is actually probably not good for your body. Not too good for your skin, because your skin, as I've said in the past, the microfloras, okay, all these living, bacteria and funguses that are living on your skin, and actually quite healthy, because they actually protect you from bad bacteria and bad funguses that can take over. Like if you've got tinea between your toes, that's because you're probably being overtaken by a bad fungus, and you've got to kill that fungus and re-establish healthier funguses. So you've probably heard about probiotics, things that you like, Yakult, yogurts, good bacteria in your gut, and you want to be careful about taking antibiotics. I saw this on the news like last week. Australia's got a very high rate of asthma, and they've discovered that it could partly be due to antibiotics taken as kids, killing these bad bacteria in your gut, but they also kill all the good bacteria as well. And so they're looking at, if you take antibiotics as a kid, that you actually take some other medicine so it doesn't have cause the asthma effect. Interesting. Science, very interesting. Some detergent. And I'm going to add a bit of water. Whoop. Give him a little bit of a mix. Stir. Just to get a solution. There's a solution. And some blue. Now I'm starting to get contaminants. I can see I'm getting contaminants because I'm getting bits of pink and blue, and I'm not working that neatly down here. The blue goes in, and the blue, ooh, can I say a little bit of a pink forming? Not really. What about the red one? And the red. So, not much of a change with the litmus paper. Does that mean it's neutral? Well, ooh, well, there we go. There's not much of a change of colour there. I'm looking at that and I'm thinking that we're talking 8. So it's only slightly basic. Okay, it's only slightly alkaline. That's the detergent. Skin cleaner. Skin cleaner. Now remember that, skin cleaner goes on your skin, of course, and obviously I use quite a lot of it for a wonderful complexion like mine. That was a joke, by the way. We are expecting it to be slightly acidic. Okay, we are expecting it to be slightly acidic. So whack it there. Clean my equipment. Neutral to acidic. And Squeeze him on. Clear, colourless. It's a gel. Oh, it's a gel. Okay, not a liquid. Add a bit of water. And give it a bit of a stir. Mixy, mixy, mixy. Okay, that's good. And blue. What will happen? Dun, 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 dun. Ooh, what do you think, people? Slightly pink? Yeah, slightly pink. Slightly acidic. What about the red one? Should stay red. That'd be very confusing if it went blue. I'd be like, what? No, good, stay blue. And did I say it should stay blue? I was meant to say it should stay red. And there we go. Again, similar to that detergent, I'll have to give it a actually maybe 7-ish, neutral to acidic. Okay, and then our final one is our magnesium oxide, and I need to get some magnesium oxide. So I've got a piece of magnesium ribbon. Tip him out. I need my glasses on. Tweezers. Action, action. Alright. Pop him to the side. Light my Bunsen burner. Now remember, you do not want to drop, make sure there's nothing flammable around. You do not want to drop anything in your Bunsen burner, okay, then it won't function so well. Let that burn. Very gently I'll bring it over to the watch glass and add a little bit of water. Now remember, it's not very soluble, okay, it's not very soluble. Magnesium oxide is not particularly soluble. I've actually still got a bit of magnesium unburnt there, so I'll just go like that. Give it a mix here. Hopefully I haven't diluted it too much. Let's get the blue litmus paper. And seems to be staying blue. Let's get the red litmus paper. Should be changing colours. Should be going, ooh. Ooh. Seems to be staying red, but it should be going blue. And what about the universal indicator? Maybe I haven't, oh, I can just see a bit. Maybe I don't have enough magnet. Oh no, there we go. I can start seeing it going a little bit blue there. Yes, yes, just needed a little bit of a mix. Beautiful. It's clearly showing that it's a bluey colour, which is about 10. Okay, well, that is how we use universal indicator to determine the acidic basicity of substances. And in real day use, it will be used for swimming pools. It's very important to have the right levels of pH for the different chemicals to work. So sometimes if the pH is too high, so if it's acidic, if it's basic, people have got to put in an acid in. If the pH is too low, then they put in some bicarb to bring the pH up to neutral. Fish aquariums, it's very important to have the right pH for the health of the fish. If you're growing plants, particularly with hydroponics, but that's with water and the dissolved nutrients, the pH is also very important. So pH is actually a very useful and important property in science, particularly for living things. So there we go. Okay, hopefully you've enjoyed this lesson, and I look forward to seeing you again soon. Bye for now. Hey, so we are going to be testing some different chemicals from around the house for their how acidic, neutral, or basic their pH level, so to speak. So I've been ravaging around under the kitchen sink, and also I've been in the laundry, and there's a cupboard up the top there with all these bottles. So I've just grabbed a selection to use, and we'll be testing them today. Now, a surprising thing is that you can actually buy some pretty caustic, corrosive chemicals from the supermarket. The supermarket is not necessarily a safe place, and particularly so the hardware, like Bunnings, they carry some pretty dangerous stuff as well. So just because you can buy it from the local shops doesn't actually make it safe. Now, I think the best way to do this is to actually make a solution of the universal indicator paper again, so that we've actually got like a liquid. I think we get the best color changes from that, and so let's make that happen. We need a beaker, we need some water, and I was quite happy with what I made before, which was, I think I used four pieces of the pH paper. Okay, so I'm just going to do the same because I think that worked quite well. And in that little booklet, there's actually quite a lot of pH paper there. So let's pop that in there and get my safety glasses. We'll need safety glasses today. Okay, we'll need safety glasses today, and gloves if you've got them, because as I said, some of the some of the chemicals are quite nasty. They're not good for us. So look, I can actually see this is actually dissolving. The chemicals are actually dissolving in the cold water. So boy, it won't take long. Won't take long for them to the chemicals to dissolve into the hot water, that's for sure. Okay, so I've got that boiling up. Let's get the tweezers, and a stirring rod would be good. And let's go, just a nice bit of a stir here. Get all that nice pH indicator chemical off the paper and into the water. It's going green, which is, I'm really happy about that, because that means my water is relatively neutral. Yep. And terrific. Oh, it really doesn't take long at all. Maybe if I just bring it up to the boil, that will probably do it. Like it looks, I'm looking at it now thinking, oh, there, it looks a bit yellow and orange, but that's actually the glow from the wire gauze there. What do you think? I think that's pretty good. I'm not exactly sure how much I'm going to need, so I might just whack in a little bit more water, just like that. I know that dilutes the colour a little bit, but I might need a fair bit of volume. Perfect. Alright, pH of chemicals from around the house. I'll turn that off. Alright. And pop it here. And you know, I like putting it in the conical flask. It makes me feel like I've got a bit of a bit of a potion. And there we go. Oh, overflowing. Pop him out. That looks terrific. I can give him a quick rinse before I put him away. And similarly, let's just clean up as we go along, shall we? Best to try and work as neatly as we can. Terrific, cleaned out that beaker. These wash bottles are really good, aren't they? And, all right, let's do some testing. Let's put the watch glass here. And the first chemical I'm going to use is Rinse Aid. Okay, so now Rinse Aid is a liquid. It's for dishwashers, and it's a blue liquid, which could be slightly problematic, couldn't it? And it's for powerful streak-free cleaning, leaves, glassware, sparkling. Now it does say lemon on there. That's interesting. And it does smell a bit lemon. You'd think it might be yellow if, okay, I'm going to add the green universal indicator to the blue Rinse Aid. Now, I should just put my gloves on, like I said I was going to. Set a good example. Doctor. Okay. Protect my skin. And this is where some people might wear lab coats as well. And green into the blue. What do we get? Interesting. Definitely went a yellow. Definitely went a yellow. So where's my little booklet? My little booklet there. The yellow is slightly acidic, number 6. See that? Interesting. So that's really quite good. So Rinse Aid, this Rinse Aid is number 6. It's slightly acidic. I actually would have thought it was going to be so slightly basic. But what we'll test next is the actual dishwasher powder. Okay, so let me pick this up and give it a rinse now. Now it's very important to give these a good rinse. So let's test a little bit of dishwashing powder. Now, we've actually only just started using dishwasher powder. Normally we use tablets, but my wife has just started buying these about 2 weeks ago, and so I'm the one who puts the dishwasher on. My kids try and stack it, and then I restack it. Well, not too much, but you know what I mean. Alright, so we've got a bit of a powder there. It's actually been quite successful. So I've been happy with the dishwashing powder. Add a bit of water and just dissolve it a little bit. Now I've got no doubt that this will be a fairly caustic substance. I'm sure that this is going to go like a blue colour. I think it's quite alkali in nature. I'm very confident, very confident. Okay, get my green liquid and add it to it. Hey, look at that. This is why you want to keep dishwashing powder out of reach of kids. So it's probably not a good idea to actually put it under the kitchen sink unless you've got like locks on the door or whatever. But it's a dark blue there, so we're talking about like an 11, you know, quite alkaline. So there we go. Grease cutting formula. That's it. That's the hydroxide in here. It's probably a sodium hydroxide. Dissolves the grease. Just seeing if it actually says what the active ingredients is. I don't think it has to say that because it's not a foodstuff. And so it's got some poison advice and that sort of stuff, but no, it doesn't actually say what the active ingredient is, but I'm pretty sure it'd be sodium hydroxide. All right, let's clean that one, and this will take it. You probably want to use a fair bit of water to rinse that off. Terrific. What's next? Oh, interesting. I've got a something to do with nail polish remover, I think. Yeah, it says for fast and gentle polish remover with acetone. Contains acetone 58%. Now, because I was a science teacher for so long, I did a lot of chemistry. Now, if you want to smell something safely in science, you take your finger or two fingers and you waft the smell towards you, and I can smell a strong acetone. Now, I've got two girls and they occasionally put a bit of nail polish on, but they know the rules for our house. You have to do the nail polish outside the house because I'm very susceptible to the nail polish smell. I think because I've spent many years around chemicals, I'm quite susceptible to it. Alright, this is interesting here. It's just gone green. Well, it stayed green. So the nail polish remover is neutral. Okay, there we go. Nail polish remover, neutral. Let's give him a clean. I wonder what chemicals you've got from around the house. Have you got similar ones to me? Be good if we can you could fill up that whole page. All right. Shower sparkle. Shower sparkle. Daily shower clean. I might just put the goggles on for shower sparkle. Now it says mold guard. Now, that's typically mold removers contain something called hypochlorite, which is like a bleach. Now, because it's a spray, it's hard to spray like this. So what I'm going to do is I've got a bit of some cut up kitchen towel. Okay, so I've got some cut up kitchen towel. And I'm going to just spray onto the kitchen towel. Like that. And I'm going to lay the kitchen towel there and then put my indicator solution on it like that. What colour has that gone? Yellow. Yeah, that's going yellow. Okay, so, or like it's going, is it yellow? The colour's travelling along. Or is it slightly greenish? I think I'm going to call it an 8. Slightly alkali. Okay, slightly alkali. Interesting. There's a little bit of capillary action happening there too as the water travelled along the liquids travelled along the paper towel. Dab, dab, dab. Okay. Really feel like a chemist today. What's next? Let's pop that there. That was the daily shower sparkle. Okay, descaler tablets. So sometimes your appliances like your kettle, your iron, which you put water in, a coffee percolator, get these build-up of crystals. Typically it's from when you've got what's called hard water. And hard water is water that's got chemicals dissolved in it. And if you've ever been to a cave system or something and you see like stalactites and the ones that come up from the ground. I've been to an excellent cave system in Vietnam called Phong Nha Kabang. If you ever get a chance to go there, wow, amazing. And let me pick this little, they're broken up, the tablets are broken up. And so, boom, there's a little tablet there. It's a descaler. It says it's an irritant. I'll add some water there. Anyway, these stalactites, the water drips along them and the water contains dissolved chemicals. And as the water evaporates, it leaves those chemicals behind and they form rock. So this is what's happening inside your kettle. Whoa! So, descaled tablets are very alkaline. Very alkaline. I'm talking probably an 11. So, I think, again, they contain some type of hydroxide. Alright. What about Glitz glass cleaner? Glitz glass cleaner. What will be the story there? Hopefully you're finding this interesting. And I've got another little piece of paper towel. And I'll give that a little spray. Boop. So this is a blue, slightly blue to start with. But the colour's not very strong, so I don't think that will be an issue. Let's see what happens. I think it's gone slightly yellow. Slightly yellow, so I'll give it a... It's got the original blue in there as well, remember, so if anything, it's around the 7, it's fairly neutral. Okay. Now, just because it's neutral doesn't mean it's safe, but generally speaking, I've noticed that the more neutral a substance, now, I've got to be careful here, but I'm going to say generally speaking, the more neutral, the less harm it will do to your skin. Now, there might be people out there in video land jumping up and down now saying I've got no idea, and they're probably right, but from my general experience, you know, when you're using glass cleaner, you're spraying it all over the place, that sort of stuff. Now, you wouldn't want to be spraying mold cleaner all over the place. If you're spraying mold cleaner, you want to wear a mask, your glasses, gloves, wrecks your clothes. Mold cleaner is very alkaline. And today for this lesson, last but not least, I've got the Clean Freak. Clean Freak. Bath and shower cleaner. Bath and shower cleaner. So spray a bit onto the paper. Clean Freak. Pop him there. I'm thinking it will be basic alkaline. Oh, it's gone very yellow. It's gone very yellow. And the yellow is definitely pH of 6 for that one. pH of 6, definitely. That requires further investigation. Community Co. kills 99.9% of germs. I reckon you want a new invention, yeah? You need to get another bottle of stuff that kills the 0.01%. Yeah, you get rich. Yeah, this one kills the 99.9%. You got to get another bottle that kills the the remaining 0.01%. Active ingredients: citric acid. Dun, 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 dun. Ah, that's why it's called acidic. 5.5% weight for weight. That means for 750 ml, that's about 750 grams. 5% of that is citric acid. And doesn't tell us what's in it, but you know what? My guess is it's mostly water with a little bit of dissolved citric acid and probably a little bit of detergent in there. Yeah, I bet you're paying a couple of bucks for like 15 cents of ingredients. That's my guess. Yep. Because there's some really good household kitchen chemicals that are good for cleaning. Citric acid, vinegar, bicarb. They're cheap chemicals, but companies want to put them in a bottle and sell them for a lot more. Yeah, anyway. Okay, well, that's it for this lesson. We have investigated the pH of some chemicals from around the house and have got some very interesting results. All right, looking forward to seeing you again in another lesson, and bye for now. Hey everyone, in this lesson we're going to be looking at acids and bases. What are they? What are the properties that acids have in common? What are the properties that bases have in common? Help us build up this concept of what they are. Acids and bases and pH is a very important part in chemistry. So it's good to start at a simple point and build on that. And so let's talk a bit about acids first. Typically, but you shouldn't do this, but typically acids are sour. So citric acid, vinegar. Where's my vinegar? Vinegar, it's sour. These are probably the only two acids that you should be tasting. No other acids should you be tasting because they can be very corrosive and very damaging. They turn blue litmus red, as long as you're not using the outer packaging. That doesn't work. They react with metals to form hydrogen gas and a salt. So in some experiments, lessons to come, we're going to be doing that and a few experiments and that sort of stuff. And they neutralize bases. So citric acid, which we can buy from Woolworths or Coles, the formula is C6, excuse me, C6HO07. So a molecule of citric acid has got 6 carbon atoms, 8 hydrogen atoms, 8 hydrogen atoms, and 7 oxygen atoms. So that's the chemical formula right there. Now what's it used for? Well, it's used in foods, it's used in drinks as a flavouring, it's used as a preservative. It helps foods last longer, and it's also used in some cleaning products. So I actually had a cleaning product, this one, the Clean Freak, which contained, what was it, 5% citric acid. So yeah, a fairly important acid. Vinegar, also known as ethanoic acid or acetic acid. What's its formula? Well, this one's an easy one for me to remember. CH3 Q. There we go. And this tells us a little bit about its structure as well, because normally, say here's a carbon atom and carbon atom, normally we just write C2H3OOH, but by writing it out as CH3Q, it actually gives us a little bit of an idea of the structure. Keep in mind when we look at these that you're always going to find hydrogen atoms linked with these acids. So where's a vinegar used? It's used in cooking, particularly like sauces. It's used for poaching eggs. It's also used as a preservative. So vinegar is used a lot in where you put the veggies like pickles in vinegar, the sliced up, you know, food preservation uses a lot of vinegar. And it's also used in cleaning products as well. Aspirin. All right, so I've got some aspirin tablets here, and the formula for aspirin, sometimes called salicylic acid, is C9H8. So there's our friend hydrogen again, and O4. Now, aspirin has been used for a long time for headaches. And, you know, people in England, they didn't go to in the olden days, they didn't find, you know, shops that were selling aspirin tablets. But it was commonly known that if you chewed the bark of the willow plant, that would help get rid of your headaches. And that's because the bark of the willow plant tree contains salicylic acid. Now, we don't go around chopping down thousands of willow trees to get this aspirin anymore. We can synthesize it using carbon and hydrogen, oxygen in like industrial labs. So if scientists can identify particular molecules, then there's a good chance they can actually replicate them. Now, aspirin these days is probably more taken to lower, to actually make the blood a little bit thinner. And so some people, you know, usually males from about my age or a bit older, start maybe taking half an aspirin a day. And in fact, on the back of this aspirin pack, it's like Monday, Tuesday, Wednesday, Thursday. These are not designed for headaches. These are designed to help blood flow and to help reduce the danger of like strokes and heart attack. So anyway, that's what aspirin is there. Phosphoric acid. Now my family doesn't drink a lot of this, and you're saying to yourself, well, why would you have 2 litre bottle of Coca-Cola? Well, I did a science day and we need Coca-Cola. It would contain some phosphoric acid. If I looked in these ingredients, it would have some phosphoric acid. And the formula is H3PO4. H3PO4. And that PO4 there is phosphor, and the H3 is the what causes it to be acidic. So we've got phosphoric acid. It's used in as a food and drink additive. It's also used as rust, as for rust removal. So that tells you a little bit about Coca-Cola, doesn't it? And it's also used to produce fertilizers. So quite a helpful thing. Hydrochloric acid. All right, this is from Bunnings, and this is a bit scary, to be honest, because like literally anyone can buy bottles of hydrochloric acid, but this is concentrated. This is like 18 molar. Now the molarity is how concentrated something is. This is 18 molar, and to give you an idea of that, a kid in year 7 high school can only use a maximum of 2 molar. Year 10 they can probably use 4 molar. And year 11 and 12, 4 molar as well. So if you want to make this into 2 molar, you have to dilute it by a factor of 9 times. So that's a lot of water you need to add to make it safe-ish. So if you were to get this on your skin or your clothes, it would burn. Now, hydrochloric acid is the easiest acid to remember. The formula, HCl. Hydrogen atom and a chlorine atom react together. The hydrogen gives the chlorine its electron. The chlorine gets the electron, turns into a negative ion, an anion, and the hydrogen ion is a cation. It becomes basically what we call a proton, and that's what makes it hydrochloric acid. It's used for cleaning. It's used for pickling of steel. That is where you've got like steel with corrosion on it, and you put it into some hydrochloric acid and that removes the corrosion. And it's used in the production of a range of chemicals. Now, last but not least is sulfuric acid, H2SO4. Now, if there's any chemical that you should learn the name, the formula for, it's hydrochloric acid and sulfuric acid. Now, there's a little rhyme I learnt when I was, in early high school, and I can't remember the whole thing, but it went something like, what she thought was H2O was H2SO4. Something, poor little Susie. Anyway, what she thought was H2O was H2SO4, and she was in all manner of strife because what she thought was water was sulfuric acid, and she was in trouble. Now, you'll find sulfuric acid in car batteries. Now, not like Tesla electric car batteries, but the starting batteries, the heavy starting battery, if you pop the bonnet of the car that's got a petrol motor, they've all got this heavy battery. And the heavy battery contains a lot of lead, but it contains liquid sulfuric acid. And sulfuric acid is important. Yeah, car batteries, manufacturing, fertilizers, making different chemicals. Sulfuric acid is so important to a country's industrial production that economists can work out how productive a country is by how much sulfuric acid they use. So one way to find out whether a country is making stuff, it's not whether they're buying components and selling stuff. Look at actually how much sulfuric acid that country is using, and that will tell you how much stuff they're making. That's how important sulfuric acid is to the industrial sector. So there we go. There's our acids. Pretty interesting, I think. Okay, but I find some things more interesting than other people. So, oh, wow, that's so interesting, Jacob. Acids. Okay, so that's acids. Let's have a look at bases. Now, bases or alkalis, they have a bitter taste. So, if you ever have a taste of sodium bicarbonate, it's bitter. Okay, it's bitter. It's not very nice. Okay, they turn red litmus blue. They turn red litmus blue. There's another property of bases. They have a slippery feel. Now, this is the scary part. Typically, they're not slippery. So, for example, if I dip my fingers into some water and then into some caustic soda, which is sodium hydroxide, it will feel slippery. It's not because this molecule or this substance, not a molecule, this substance is slippery. It's because it breaks down the proteins in your skin to fats and oils, and those fats and oils feel slippery. So basically, you're being turned into soap. That's what's happening. So yeah, we don't want to be feeling slippery stuff. And they can neutralize acids. So example of a base is aluminium hydroxide, Al, aluminium, and then OH3. Okay, OH3. Oh, I got that slightly wrong here. That's a big mistake. Wow, that would have been a disaster. OH3. What's that saying is that for one atom of aluminium, you have 3 hydroxide ions. And that is because the hydroxide ion requires an electron to be stable. The aluminium has got 3 excess electrons, and so it can give away 3 electrons, and so you have 3 hydroxide ions. Now, this is used in some as a antacid in some medicines. So, for example, Mylanta, if you get heartburn, maybe older people like me again eat too much, pushes the stomach contents up your esophagus, and the stomach contents contains hydrochloric acid, which is breaking down proteins, and then that starts burning near your heart, so it's called heartburn. So Quick Ease, Mylanta, Rennie, they're all examples of heartburn medicine. It's used in water purification, aluminium hydroxide, to adjust the pH so that you can actually add other chemicals for treatment. And it's used in antiperspirants as well. So deodorants use aluminium hydroxides. And there's been a little bit of fear of the aluminium ion. They think it might cause issues, health issues. And so some people are wary of the aluminium and cooking in aluminium pans. I don't have a lot to say about that. You can research that yourself. Magnesium hydroxide. Now, magnesium has got 2 electrons in its outer shell, and so it can give up 2 electrons, and so magnesium hydroxide is MgOH2. Okay? Now, it's used again as an antacid, okay, and also as a laxative. Softens your stools, helps you go to the toilet, helps you do number 2, and again for wastewater treatment. When I say wastewater treatment, what it can do is if you're an industrial site and you've been using a lot of acids and you want to put those into the waste stream, if you add magnesium hydroxide, it will help neutralize them. So there we go. Ammonia. This is quite an unusual base here. I've written out the name of it. It's NH3. NH3. A little bit of an unusual base because you'll see all the others contain hydroxides, and this one doesn't. But ammonia is used for lots of cleaning products. It's a very strong smelling substance. It's also used for fertilizers, refrigeration, and I believe it can be used in explosives as well. Calcium hydroxide. Now, calcium has got 2 electrons in its outer shell, and so it's CaOH2. And again, it's going to be used as water treatment, a pH regulator in agriculture. So you might have soils that are too acidic, then you might put some calcium hydroxide in there. It's also used in construction plaster. So, you know, we use a lot of gyprock, and we use like this white paste, and we put cornices up with the plaster. A lot of these, and we also do bricklaying with mortar. Calcium hydroxide is used a lot in those different substances. So, potassium hydroxide. Now, potassium has got 1 electron in its outer shell, and so it's KOH. Okay. Now, if you wanted to, you could put a OH1 there to show that, but we don't actually do that. Okay, we don't do that. All right, so I shouldn't even show you that. We don't do that, or chemists don't do that. But I just sort of wanted to help give you a little bit of a picture for what we're talking about here. Potassium hydroxide is used in soap and detergent making. It's used in alkaline batteries. So sometimes you've got an AA battery. This one's not an AA battery, but this will be an alkaline battery, and it will contain potassium hydroxide and also chemical manufacturing. And the final one, and probably the easiest one, or the most common one, is sodium hydroxide, NaOH. NaOH. otherwise known as caustic soda. Now, sometimes if you're cooking like chicken in the oven or lamb in the oven and all the oils, okay, and the fats, they're like liquid oil, some people pour that into the sink and then it goes down into the waste, but then it cools down and it solidifies and it turns into a solid white fat layer, and then that blocks the water. Well, if you pour caustic soda on it, the caustic soda breaks it down, and it's an exothermic reaction, so it produces a lot of heat, and that also then melts the solidified fat and breaking it down, and then you can use hot water to sort of flush it through. But that means this is quite dangerous, because if you put it in your hand or on your skin, it's going to break down your skin. So you've got to be... The scary thing is you can buy this from Coles and Woolies, and it's probably, it's a very dangerous substance, very hazardous, very risky. So they've got like a child-proof cap on it, so you've got to squeeze it, but it's not too hard. It's white, it's like this white crystals. If you leave it out, it actually sucks water in from the atmosphere. It acquiesces, okay, acquiesces. Anyway, it's caustic soda. It's used for making soap. It's used in drain cleaners. It's used in paper manufacturing. It's used to make different chemicals. I find this very interesting too, because there's this stuff called biodiesel. And biodiesel is very similar to diesel fuel, but to make biodiesel you get fish and chip oil, waste fish and chip oil from fish and chip shops. And by adding a certain amount of caustic soda and by heating it and mixing it, you can actually break down the fish and chip oil molecules so that they're shorter and that they become a similar length to the diesel molecules of fuel. And so you can actually use it as a fuel in diesel cars or diesel generators. So very, very interesting biodiesels. Okay, well, that's a rundown on the acids and a rundown on the bases. Hopefully you've enjoyed the lesson, and I'll see you soon, and we'll be doing more practical work, I guarantee it. Bye for now. Hey everyone, in this lesson we're going to be doing a food preservation experiment. Have you ever noticed that when you've cut open an apple, it goes brown fairly quickly? The white flesh oxidizes in the oxygen, causing it to go brown. And so I've seen where people making apple salads, they actually put, well, not an apple salad, but a salad with apples in it. They actually like put the apple in some lemon juice. Now, lemon juice contains citric acid, and we've mentioned before that acids can be used as food preservatives. So that's what the basis of this experiment actually is. And it will be a good experiment to talk about experimental design and the scientific method. So the aim is to find out what substances might best preserve an apple and see if we can find any generalizations in terms of maybe even acid bases, that sort of stuff. So now there's something called, I call it the lotus flower planning method of science, and I think it's a really good way to plan lots of different science experiments. So here it is here, and you can just see a faint outline of our lotus flower, and there's like the inner part of the flower, and the inner part of the flower is very important. It contains what we call the independent variable. And the independent variable, okay, is what we, okay, are going to change. What are we going to change? The independent variable, what are we going to change? And what we're actually going to change is what we soak the apple in. That's what we're going to change. And so that's at the center. What goes on in the petals or around the outside are all the variables we're going to control or keep the same, okay? Keep the same. So we have to think of as many things in this experiment that we can keep the same. And we also state what those variables or how we're going to control them. So we're going to start with the type of apple. We're obviously not going to do this experiment with 8 different apples. That would not be a very good experiment. And so we're going to use the one type of apple. Now, interestingly enough, I'm actually not 100% sure what this apple actually is. I'm not a fan of apple. Well, I do like apples, but I don't eat a lot of them. Is it a Fuji apple? I mean, no, it's not a Granny Smith apple. I'm pretty sure it's not a Pink Lady, but we don't tend to buy Fuji apples. I might call it a Pink Lady. Okay, all right. So the type of apple, it's a Pink Lady. That way, whoever does, if anyone wants to redo this experiment, they know, you've got to use a Pink Lady. Good. The shape of each apple piece. Now, we're going to actually be testing 6 different things. So we need this into at least 6 pieces. I know an easy way to turn it into 8 pieces. So I'm going to say eighths of an apple. Okay? An eighth of an apple in slices. All right? Good. The size of the apple piece. Now, this is where you can actually, if you want, like measure something, and it's going to be pretty much the length of the apple, take away the skin. So it's actually going to be about 5 centimeters long. 5 centimeters long. And the width of it is going to be pretty close to the radius, which is about 3 centimeters. 3 centimeters wide. Okay. The length of time apple is soaked for. So we're going to soak it into some different substances. And so how about we say, I think 1 minute each. Okay. So we'll call it 60 seconds. Good. And the concentration of the soaking solution. So we're going to be doing like vinegar, lemon juice, bicarb, soda solution, sugar solution, salt solution. And so we'll do, I think we'll do 50 ml of water. Okay, 50 ml water. And a teaspoon, okay, teaspoon of the substance. And then the exposure conditions, once we've soaked them in each substance, we're going to take them out and we'll put them just in a cold, dry room, like down here in the studio. So not in the sun, not in a warm position. It's a cold, dry room. I mean, you could say the fridge if you wanted to. But that's a cold, fairly dry room too. And the exposure time, how long are we going to leave them out for? Now, I'm not 100% sure on that one, so I might leave that part of the method out and fill that in later based on what's going on. Now, people might say, oh, you can't do that, but I can do what I want because it's my lesson and my video. So there we go. And then I've got room for one other, if there is anything else that we can think of. We'll say peel the apple. Okay, apple peeled. There we go, apple peeled. Good. Now, you could actually use that as your method if you wanted to, but if you needed someone who wanted a step-by-step method, this is easy to convert to a method. You go, 1, take a Pink Lady apple. 2, peel the apple and then slice it into 8 equal quadrants. Well, they're not quadrants, but quadrants 4. Cut the apple into quadrants and then cut each quadrant into half. So that each piece is 5 centimeters long and 3 centimeters wide. Soak the apple into 6 different solutions made up of, or soak each piece of apple into a solution made up from 50 ml of water and a teaspoon of vinegar, lemon juice, bicarb, sugar and salt. Take out, leave in for 60 seconds and take out and leave on a plate in a cool, dry room. After, insert this later, 1 hour, rank, give each one a mark out of 10 for how brown it is. See? There we go. That's a good scientific method, or good scientific experiment based on the scientific method. And then our dependent variable is how brown the apple goes. Okay, how it depends on the independent variable, what we soaked it in. Okay, there we go. Good experiment, isn't it? So what I do now is I've got a little chopping board and I'm going to peel the apple. Oh, no, I'm not going to do that yet. We'll do that last. Do that last. I should get my 6 glasses out first. Okay, oh, almost did it wrong, because if I peeled it now, it would start oxidizing straight away. And so what are we going to have? Well, water. Now this is a this pen is just you know, you can rub it out pretty easy. What else was the next one? Let me move my sheet here. Vinegar. Lemon juice. Hopefully I'm not using my permanent marker. Bicarb. Sugar. Salt. Put that there. Okay, so I'm going to put equal amounts of water into each one. Approximately 50 ml. Okay, now get down to avoid parallax error. Okay, very good. And the first one is what we call the control. It's, you know, just plain water. It's what happens if we really don't do anything to it. Okay. Next one, vinegar. Vinegar. Now I'm doing a tablespoon of each substance. And this is where an improvement. Okay, 1 spoon of vinegar. I mean, maybe 1 spoon of vinegar is not like a fair. Maybe it needs to be like soaked in vinegar for it to have any effect. But lemon juice. But this is where, okay, this is where you can do an experiment the first time, get some results, discuss the experiment, and then come up with maybe some modifications, changes, suggestions, and then do some more experimentation. Yeah. So, bicarb. Bicarb. Sugar. And salt. All right. Now, they'll of course need a nice stir, but you know what? Why don't I just put these like this here for now, and then make my apple pieces, because they'll actually start dissolving while I'm doing this work. So, no, I should get them dissolved now, because it's all got to happen fairly quickly. Okay, the salt. Dissolve him up. And I should rinse my spoon between each one so that I don't contaminate. Each specimen. Does that make sense? I don't want to add a bit of salt to the sugar and a bit of sugar salt to the bicarb and a bit of bicarb sugar salt to the lemon juice and so on. Okay, you know what, that will actually do, because the others are liquids and I'll be busy mixing. Okay, here we go. Ready, set, finally. I mean, I guess I've just been looking forward to peeling this. Have you ever done a competition who can actually peel the longest apple peel without it breaking? That is a competition I would win every single time. Nobody would be able to beat me at this, because you think my jokes are funny. You wait to see how good I am at this. I am literally a master at peeling long lines. Now, I know it's not a good thing to boast, and that pride goes before the fall. But when you're as good at something as I am at peeling apples, I think you just got to tell the world, don't you think? Look at this. I know you are in, oh, sugar, not sugar, apple. I know you are in absolute awe of my skills here. Ah! Broke. Not bad though. Here we go. Take a bow. Take a bow. Look at that. I can hear the cheering and the clapping through the screen. So thank you. Thank you. Thank you for your support. Okay, I've got to cut these into quarters first, quadrants, and then into eighths. So that half of a half, yep, a half of a quarter is an eighth. Oh, that one wasn't quite half. Half of a half. Half of a quarter is an eighth. Okay, and then I'm going to give it a quick core. Make sure there's no, that's not bad. If I made a mistake on here, then I've got a little bit of spare. Good, good, good. Hurry up, hurry up. 5. Good, okay, I've got to get them in quick. Fast, fast, Jacob. Okay. Yoo-hoo! Oh no, this stupid one. Put the wrong one in. Put in a whole quarter. What a dope. Okay. Let's put this down here. I should start the stopwatch. 60 seconds, I said. Okay. Start. And okay, around in he goes. He's in the water. This one here is in the vinegar. Give it a good stir like this. Make sure it's got a good coating. I should wash the spoon each time. I know, I can hear you yelling out, Jacob, wash the spoon. Lemon juice. Do you think this will have any effect at all? That's the question. Will this have any effect at all? Bicarb. Okay, so I actually have to dissolve a little bit of the bicarb now. I'm up to 55 seconds here. I think I might have to adjust my time. Okay. And the sugar. Round we go. Still a bit of undissolved sugar in there actually. Probably should have dissolved that properly at the beginning. My mistake. That's something I can improve on if I was to do this experiment again. Beautiful. And finally the salt. That salt water looks unusual. Normally salt water is not as milky as what it is. I think there's something going on there. I think there's some type of reaction going on. Okay, 2 minutes. There we go. I've soaked them for basically 2 minutes. And what I'm going to do now, this is fairly important. So I'm going to put that there. And I'll take that apple out of the water puppet there and have it sitting up there like that. Then the vinegar. Stab the knife in, sit it there like that. What you've got to see, what I'm trying to do is I'm trying to make sure that we've got fairly identical conditions, right, for each one. And I'm also putting it next to the stuff I soaked it in, because that's got a label on it. Does that make sense? It makes it easy to identify. There we go. So now the question is, what's going to happen and how long do I leave it for? Okay, so I don't know, I'll come back in half an hour, and we'll continue the lesson then. Obviously, with the power of video editing, it's not going to be long at all. Okay, 5 hours later. Okay, now, I'm not going to lie. I would have rathered some more dramatic results, you know. I would have liked the control, which was just plain water, to have gone like the absolute brownest. Now, it definitely has gone browner, 100%. Like, you can sort of, one thing I can do is if I cut it lengthways, I can actually compare, right, the colour of the flesh to the colour of the brown there. So, look, I've got to give it a number out of 10. And it is sort of all over. There's a lot of extra oxidization now. I'm going to give it a 5 out of 10 for the control. Okay, brown, 5 out of 10. So I'm going to hold this one as my standard. I'm going to say that this one is my standard, and then the next, the next one is vinegar, and if I put that next to it, it's slightly lighter. So I'll give it a 4 out of 10. Like so. And the lemon juice, 4. I would have hoped that one would have been lighter, but I've got to be honest, you know, you just got to be honest about these things. Oh, bicarb, hey, that's interesting, and there's some big brown marks on there. I've got to go 7. It feels slimy. There's an observation. And that's a bit of a shock. 7, I am quite surprised with that. The sugar, the sugar looks pretty similar to the control, so I'm going to give that a 5. And then the salt, no, it's definitely lighter, but it also has a bit of a slimy feel on it. I think I'm going to have to give it a 3. Okay. So, interesting. Alright, so the graph is the preservation of apple slices. So we always do a title. Then the independent variable goes down here, and so it's the substance apple soaked in. And in this case we had like, we've got 6 substances, so 1, 2, 3, 4, 5, no, 1, 2, 3, 4, 5. I'm not keen on this. I'm going, it has to be this one has to be a column graph because there's no numerical link between the different substances, and I would like to have a break between each one. 1, 2, 3, 4, 5. If I do the lines, 1, 2, 3, 4, 5, 6. I'm just going to cheat a little bit. I'm going to go water is the first one, then a break, vinegar, then a break, lemon juice, bicarb, sugar, and I'm going to put salt here all on its own. And then the browning out of 10. Browning out of 10 is our dependent variable, which goes on the vertical, and it goes from 0 to 10. 4, 5, 6, 7, 8, 9, 10. And our control was water, which was 5. And so I'll go to 5. There's our nice column. Because there's no quantitative link, no numerical link between water and vinegar. That's why I have to do a bar or a column graph. 4. Okay, so it was less brown, so better preserved. Lemon juice, 4. Bicarb soda, this was the really unusual one. Its browning was the oops-a daisy. That was a mistake, people. The browning was the most. It accelerated. It accelerated the browning of the apple. Sugar solution 5. And then finally the salt solution was 3. So I'm going to start another one here. Should have used a ruler, but that's okay. So in my discussion, they didn't go as brown as what I would have thought after 5 hours. Maybe that's the type of apple. Interestingly, the bicarb seemed to accelerate the browning, and it turned out that the salt solution appeared to best preservation. So our aim was to determine the preservative effects of some different substance on apples, and so we could say the best preserver was salt and the least preserver was bicarb. So there we go. There's a science experiment from the planning, the carrying out, looking at the results, graphing, discussion, conclusion. How good's that? Okay, I'll see you guys again soon. Bye for now. Hey everyone, in this lesson we're going to be looking at metals and acids. Now, most of the elements on the periodic table are actually metals. Now this D shackle is made out of iron, and it is dense. I can tell you this thing's heavy. This like weighs 2 kilos. It's a solid piece of iron, and I'm quite interested in terms of why it's not corroded. I think it must be galvanized. That means they must have hot dipped this into some zinc, molten zinc, and the zinc has coated it, and that produces a barrier, okay, a very good barrier from a cathodic barrier from rusting. Yeah, excellent. This is aluminium. It's a lightweight metal. This has actually been extruded with a lot of pressure. It's been pushed through a die, and it actually comes out as this shape, which is a right angle aluminium. And it's used in window frames, it's used in outdoor seating, it's used a lot in construction, cladding, it's used in boats, it's used in aeroplanes, aluminium. Interestingly, aluminium is quite a reactive metal, but when it reacts with the oxygen in the air and forms aluminium oxide, that aluminium oxide actually produces an impenetrable barrier, stopping it from corroding further. There are ways to remove that barrier, but I'm not going to tell you. All right, another one is copper metal here, this brown metal, and it's fairly non-reactive. That's why it's used for water pipes. And this tap is actually cast from brass. Okay, brass. And brass, I believe, is an alloy of copper and, let me get this right, it's either zinc or tin. You can check it out. There's bronze and brass. And I'm pretty sure that this is brass. And it's cast. That means that they put this shape into sand, and they pour in, then they pull it out, then they pour in the molten alloy. And an alloy is two or more different elements, typically metals, combined together to produce a new substance with some superior properties. And the superior property of this to copper is that I think you can melt it and pour it and cast it. Whereas I don't think you can melt and pour and cast copper very easily. So, 3 metals. Now, different metals have got different reactivities, and a very reactive metal is potassium. Potassium is a very reactive metal, and in fact it will react with water if you put some potassium in some water. In fact, if you put some sodium in some water. And well, talking of that, maybe I should do a little bit. What do you think? I think so. Yes, I think so. Let me get my glasses on because I want to show you something new that I haven't shown you with sodium before. So if I put my glasses here, and we need a white background. Okay, so if I give you a white background here, and let's give I'm not going to use a watch glass actually, I'm going to use a plastic dish like that, and I'm going to put some water in it. Okay, put some water, but I'm also going to put some universal indicator solution. So a little bit of universal indicator solution, and it's gone green because the water is neutral. And in here I've got my sodium metal, which is kept under oil. And it's kept under oil because it's a very reactive metal and it's going to react with the air. Now that is way too much to use. And so how about I cut it with a little knife, and you can see it's shiny. It's shiny when freshly cut. I'm going to pop that back in there, and it's called sodium because sodium, the symbol is Na, natrium. Natrium in Latin is swimmer, and we're going to see that it swims on the surface of this water. Let's move that across to the water. Whoop. And what you'll notice is it goes purple, okay, turns into a ball. Woo! Wow! Oh, wow. Still reacting there. How awesome was that? The sodium reacts with the water to form hydrogen gas and sodium hydroxide. That's why the universal indicator went purpley. That's quite caustic now. How good was that? That was very exciting, wasn't it? I'm so glad that I did that. All right. Okay. I think I can move this safely away without it exploding. It's probably like melted the... No, I think it's okay actually. All right, so that's why schools can only do very small amounts and in fume cupboards and stuff like that. So, all right. So sodium's very reactive. Then it's lithium, calcium, magnesium is still quite reactive, and it will react with an acid. Yeah. Aluminium down to zinc. Zinc will react with an acid. So will iron. but copper won't, silver won't, and gold won't. And so gold is the least reactive metal. It's the least reactive metal, which is why it's used, one reason why it's used for jewellery. That means it stays, you know, shiny, goldy. You know, metals have many properties in common. They're malleable, they're able to be hammered into sheets. They're ductile, they're able to be drawn into wires. They're good conductors of electricity, good conductors of heat, shiny when freshly cut, react with acids to form hydrogen gas. So lots of properties in common, but that doesn't mean they're all exactly the same. They've got different reactivities. Gold is the least reactive, and we've got potassium way up the top there as a very reactive metal. So, and which ones react with water? Well, potassium, sodium, lithium, and calcium. Magnesium will if it's like hot water or steam. Okay. Now, an absolute classic reaction that school kids do is magnesium and hydrochloric acid. Now, we're going to be doing magnesium and citric acid, which I think is not just as good. I actually think it's better. So, yeah, we'll do that after. But when you react with magnesium with hydrochloric acid, you get hydrogen gas and magnesium chloride. And magnesium, the symbol is Mg. Hydrochloric acid is HCl. Hydrogen gas is H2, because the hydrogen always exists as a pair, as a diatomic molecule. And that forms magnesium chloride. Now, magnesium chloride, magnesium's got 2 electrons on the outer shell. Chlorine's missing an electron. And so magnesium chloride is MgCl2, because you need 2 chlorines to match up with the 2 electrons on the magnesium. So that's the formula, MgCl2 for magnesium chloride, which means, of course, that we need to have 2 Cls over here. Now, I can't just put a little 2 there, because that changes the formula, but I can put a 2 out the front here. And that actually then, 2 hydrogens forms the 2 hydrogens, the 2 chlorines, the 2 chlorines. And so what I can say is 1 atom of magnesium reacts with 2 molecules of hydrogen chloride, not hydrogen chloride, hydrochloric acid, to form 1 molecule of hydrogen gas, and one, I don't want to say molecule of magnesium chloride, but because it's a little bit trickier. They're not actually individual molecules. It's like a ratio. So we'll just say 1 of MgCl2. What about magnesium and sulfuric acid? Again, Mg. Now, sulfuric acid, what she thought was H2O was H2SO4. So I can write H2SO4. That's the formula for sulfuric acid. Hydrogen gas is the same, of course. And then that makes magnesium sulfate, MgSO4. Now, I know sulfate is a polyatomic ion with a valency of 2. And so it's 1 atom of magnesium to 1 of the polyatomic ions of sulfate. And that is balanced. I don't have to put numbers anywhere else. So 1 atom of magnesium reacts with a molecule of sulfuric acid to form a molecule of hydrogen gas to form magnesium sulfate. Magnesium and citric acid, that's what we're going to be doing. We're going to go magnesium, Mg, plus citric acid, C6H8O7, and it forms hydrogen gas, H2, and it forms magnesium citrate, which we're going to go C6H6O7Mg. There's our magnesium citrate. And now we're going to do something very exciting. We're going to do the pop test. Okay, so we need some magnesium ribbon. Now, it comes in this jar in length of 2 centimeters. You can break it in half. You only need a length of 1 centimeter for this. I'm going to pop my safety glasses on and get a tiny test tube. And in that tiny test tube, I need to put some citric acid. Tip, tip, tip. There we go. Let me do my washing up, my cleaning up. So I've got a bit of citric acid in there, and I'm going to wash it down with a little bit of water. Not too much water, okay, not too much water. And there we go, I've got a nice concentrated amount of citric acid there. And just don't put your thumb on it and mix it like that. This is how you mix a dissolve a solid in a test tube. Tap, 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 tap. You put the test tube between your two fingers, your thumb and your index finger, and then you tap it with your other index finger, and the liquid goes around, round, and it dissolves it quite quickly, actually. And you'll notice, I'm putting it like this because that's quite a sensitive part of the body, the skin on the neck there. It's cold. It's cold. It's called an endothermic dissolution. Okay. Now, this little activity might be best if you had a helper. Helper. I don't have a helper. So this is going to be my helper, the little ice cream, the ice cube tray. But I'm going to fold the magnesium in two, and I'm going to drop it in and give it a shake. And if I look at it, well, it's sunk and then it rose to the top. Oh, rose to the top. If I give it a shake, it sinks again. And it's rising to the top because it's forming hydrogen gas. Now, I think this rubber stopper's too big for it. It is. I could actually, if you've got any, I could actually put a little balloon on there like that. Oh yeah, that's what I could do. This would be interesting. Now, the reaction starts off relatively slowly. And the reason is, even though it's got very concentrated citric acid, remember it's cold. Yeah, and so when it's cold, the particles are not moving very fast, and so when there are collisions, the collisions are not very energetic. But as the collisions occur and the reaction occurs, it's an exothermic reaction, and so it produces heat, and that means it gets hotter, and that means the reaction particles are going faster, and so your reaction rate will actually increase as the reaction goes on. All right. Now I'm hoping that 1 centimeter is long enough, and it is, and I can even see, like this fountain of bubbles. It's like a fountain of effervescence. It is very interesting, and I can see that balloon is about to go. Whoop. Come on, you can do it. You can do it. Here we go. Oh, close. This is actually the basis of some new robots where they actually pump air into like tubes to actually produce like structure and movements. Okay, all right, so I'm getting some hydrogen gas. And now I'm going to hopefully do the absolute classic pop test. So I'll just get my heat-proof mat here. I got a match. I'm going to take the balloon off and just put my finger on it. Okay, just put my finger on it. I would have lost some of the hydrogen gas. And then, whoo! That was a bit lame. There was only a really small little pop. And this is why I needed help, because I have to somehow light that match while I've still got my finger on this. Yeah. Uh-oh. Is it possible? Oh, I don't know. Let's try again. Here we go. Ready, set, whoop! The smallest little pop. The smallest little pop. Now, this is probably one of the only things with Tiny Science Lab that's not as good as like when you got big stuff. Most of the time, Tiny Science Lab does a better job than the big stuff. The classic pop from a good sized test tube is it's like pop, pop. Maybe you're getting a good pop because you've got some help. I don't know. Whoop. I'm just getting a pop, pop. Okay, but nonetheless, the hydrogen reacts with oxygen to form an explosion and some water. Okay, so in actual fact, when you explode hydrogen gas, you actually get some water. Now the magnesium is reacting with the citric acid to form hydrogen and a salt, and the salt is actually called magnesium citrate. And magnesium citrate is actually soluble, and so it's dissolved in here. Now it's still, it's quite warm now. It's actually, oh, I can go and I can listen to it like that. I'm tempted to do it once more. I so much would love to have a proper little pop. I would really, really love that. So I'm going to try once more. Here we go. That's if I can light my match. That was so close. That was pretty good actually. But we're going to do an activity to see if we can recover the magnesium citrate. And so I'm going to need my Bunsen burner like this. And I think I need a bit more gas. Let's turn him upside down. Make sure there's nothing flammable around us. Push that down. Beautiful. Pop that there. Like that. Let's go over. And let's light the Bunsen. Oh, can't light a lit match. Oop. That's better. Fantastic. Put that in the bowl. Tripod. Wire gauze. I need some water. I'm not going to fill it up. Just half full. Okay. And that's not going to take very long to get boiling. Now here's the trick. Here's the trick, my friends. You get a watch glass. Just make sure it's clean. And you put your watch glass on top of the beaker like that. Okay? The heat from the steam touches the bottom of the watch glass and it causes the watch glass to get hot. And then this has almost finished reacting. Okay? Almost all the magnesium ribbon has reacted with the citric acid. It's almost all gone. There's a few millimeters left. Just going to get my tweezers. So I might get a bit of bumping happening here. So I need to make sure that it's good. If you're feeling a little bit unsafe, you can actually push the equipment away from you. And once it's boiling, you can turn it down. Okay, you can turn the heat down. There we go. We just need a gentle boil. That's good. That's good. I'm getting some nice heat. I'm getting some steam. I can tell you that the top of that watch glass will be warming up. I'm going to pour my solution onto that. Now I will tell you why I find chemistry so wonderful. I've got some water, but we dissolve some citric acid in the water. And the magnesium reacted with the citric acid. Now I put in 1 centimetre of magnesium. The big question is, how much citric acid did I need? Did I have enough citric acid to react with all of the magnesium? Or did I have too much? Well, I sort of made sure that I'd have too much. That's why I added lots of citric acid. I wanted a nice concentrated solution so that my reaction would go fairly quickly. But you know what? When you do senior chemistry, it's actually quite an easy calculation. I'm just going to turn this up. It's actually quite an easy calculation to work out how much citric acid you need to react with 1 centimetre, or you need to know the mass of the ribbon. Let's say it's 0.1 grams of magnesium ribbon. You can actually calculate it. It's a little bit like you're making sandwiches, and let's say you're making let's say you're making a ham sandwich, and if you like lots of ham, you have 2 slices of ham on each sandwich. And so you might say, okay, I've got a loaf of bread, it's got 24 pieces of bread, right? how many pieces of ham will I need? And you're like, well, 24 times 2 is 48. I need 48 pieces of ham. And so therefore, you've got 48 pieces of ham, a loaf of bread, and you can make all your sandwiches up. It's a bit like that with the magnesium ribbon and the citric acid. If you know how much you need, if you've got of one, you can work out how much you need of other, put the two together and then react them. So what's going to happen now is that we're evaporating off the water of solution, so the water in that watch glass, and we're going to leave behind the unreacted citric acid and the new product that was formed, the magnesium citrate. And we probably won't be able to tell. They'll be combined. They'll probably be a white, crusty, crystalline substance, solid, and it will probably take 5 to 10 minutes. And I'm hoping that you're doing this, because if you're not doing this, you're not going to actually find the final answer, because I'm not actually going to finish this off. This is something for you to do and for you to finish off, okay? So good luck. Things to watch out for is make sure that that beaker does not boil dry. If that beaker boils dry, then the temperature of the beaker goes higher, higher, higher. The glass expands, 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 and then it will crack. If you're worried about it starting to boil dry, you can actually get your large peg and you can take it off. Right, you can take that off and you can add some water to it, to the beaker, and then pop that back. All right. Okay, well, hopefully you're going to keep doing this when I say goodbye. Okay, everybody. Bye-bye, bye-bye. Hopefully you've enjoyed the lesson. Bye. Hey everyone, in this lesson we're going to be doing a rate of reaction experiment. Now, a reaction rate is how quickly a chemical reaction proceeds. Now, some chemical reactions are quite slow. For example, the setting of concrete, okay? Now, when they built like Warragamba Dam, they actually had to use a lot of ice. And the reason is, when concrete sets, it's actually an exothermic reaction. It gives out heat. And they just like had thousands and thousands of tons of concrete that they were using. And the problem is, if you let it like cure normally, it just gives out so much heat that it actually affects the strength of the reaction. And so they actually used ice water to make sure that the reaction rate was slower. The ice water absorbed some of the heat, and so you had a stronger concrete at the end of it. Now, a very fast reaction is like in an airbag. Now, an airbag shouldn't really be called an airbag in a car, because there's this compound, I think it's called sodium azide, and when it's triggered by a small electrical current, so if you have a smash, there's a sensor. The sensor sends a message to the computer. The computer decides whether the crash is there's a significant enough of an incident to trigger the airbag. And if that's the case, then it sends a signal to the airbag, a little electrical signal, and that little spark ignites the sodium azide and produces, I'm pretty sure, a lot of nitrogen gas. So they should be called nitrogen bags, not airbags. And then that's a very fast reaction, super, super fast. Now, what are some things that can affect reaction rates? Obviously, the temperature. Colder, the slower, faster, the higher, the faster it goes. But also concentration concentration amounts. And so, if you have high concentration, so like more stuff, more surface area, more collisions, then you'll have a greater rate of reaction. It will go faster. And so that's what this experiment, this lesson is looking at. And we're going to be using citric acid and magnesium to produce hydrogen gas. And to measure the speed of the reaction, we're going to time how long it takes for the hydrogen gas to be produced. Now, I've got a bowl of water here. It's a glass bowl. You don't need a bowl this big. It was the only glass bowl that I had that was glass, so that you could sort of see what was going on. Okay, and I've just added a little bit of blue food dye, just so that you can see the water a little bit better. And I'm just going to get out my measuring cylinder, and I can fill up this measuring cylinder with water from the bowl here. So if I fill him up, and when I say fill up, I'm talking about fill it up to the very, 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 very top. I'm going to put my finger on it, over the top, turn it upside down, and what you might notice is that the liquid water doesn't actually come out. It only comes out if I lift it up out of the water, but otherwise the air pressure pushing down on the water pushes the water up, and it stays exactly where it is. And this is a really good way to measure a volume of a gas. I'm going to take some hose that comes with the set, and you probably get enough hose where you can cut it in half and that sort of stuff. So I'm going to feed the hose into the measuring cylinder like that, and I can actually just hook that over the end just for now. And so I could actually blow air in, and then that will displace the water. So I could actually blow 5 ml of air in if I wanted to, but I'm not going to do that. So I need the conical flask, or a conical flask, and I need to put the rubber stopper on, because I'm going to, well, before I put the rubber stopper on, I should actually connect the rubber stopper to the, not the rubber stopper, the glass tube on the rubber stopper to the tube. Now I need to dry my fingers because it's a little bit slippery, and it is a little bit difficult. It is challenging to push that silicone tube onto the glass tube. It's definitely a tight fit. Okay, it's definitely a tight fit. And so if you're having troubles, I'm not surprised. But the beautiful thing with a tight fit is that, oh, I'm like, once it's on, it will stay on, and I just pulled it off. Oh, dear, oh dear, oh dear. You do need a tight fit, because otherwise gas escapes, and we don't want the gas to escape. Okay, and we don't want it to come off too easy. So just take a bit of care with glass tubing. All right, that is on quite firmly. And so we need 0.5 grams of water to 3 ml of water. We need 0.5 grams of citric acid to 3 ml of water. And now I've used my measuring cylinder over there. Oh, how stupid is that? I guess I can actually use my pipette, because this is a 2 ml pipette. So I'm actually going to draw up 2 ml. That's the 2 ml mark. Push that in there like that, and then halfway up is the 1 ml mark. So that looks like 3 ml there. Okay, so that's good. And I need 0.5 gram of citric acid. So I'm going to get out my scales and turn it on. Now it takes AAA batteries, and those batteries should actually last quite a long time. And if I pop my watch glass on, well, my watch glass weighs 8.90 grams. I tear it, and then it goes to 0. So now it will weigh whatever mass I put on there. And I need 0.5 gram of citric acid. All right. So if I go tap, 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 0.16, 0.2, 0.3, 0.4, 0.49, need the tiniest bit more. These are actually very accurate scales. There we go. And I have to get that into here without spilling it. So look, you can use a piece of paper or something like that. I'm actually just going to use a piece of filter paper and go like this. I'm going to put it on the filter paper, the citric acid, and then I'm going to put the citric acid in there like that. and I'm going to give it a good swish. Now, we do have a little bit of a technical issue here, and the technical issue is that the dissolution of citric acid is actually endothermic. That means it goes cold. And the problem is temperature affects the rate of reaction as well. And so I don't really want it cold, okay? So what I could do is just really quickly warm it up. Okay, I could really quickly warm it up just to like room temperature so that it's not actually cold. Or I could just like hold it in my hand for a little bit like that. But that is a little bit of a problem with this experiment, and that is that I want to do it fairly quickly, but I know that there's going to be, it might invalidate the experiment if I don't return everything to the same conditions every single time. So I've got a little bit of a catch-22 problem here. So I then need to have a 1 centimetre length of magnesium ribbon, and I've got a little ruler here, and the lengths that come, yeah, they're 2 centimetres, and so I'm going to break it into half. And you can use a pair of scissors, or you can fold it. And let's get a stopwatch happening like this. And this is good, this is good, this is good. If I put in the ribbon and now push the rubber tube on, and I'll press start. Give this a little bit of a swish to make sure that the magnesium is fully surrounded by the citric acid, and I've got bubbles forming. Okay, I've got bubbles forming. Okay, so there is a reaction occurring, without a doubt. Is there any, can we see any gas bubbles yet? Not yet. Okay, not yet. So it takes a bit of time because don't forget gases are compressible. Okay, and so you actually have to build up a little bit of pressure here of this gas, and the gas has to push. There is some water. There's actually some water in that. There's actually some water in. Whoa! Oh, that's what I wanted to avoid. Oh, that was actually quite quick. That wasn't a problem. Might have to refer to that later on. That, you know, the end of the tube just popped off. I've pulled it down with my nails there, and I've pushed. Whenever you're pushing a rubber tube, or a rubber, not a rubber tube. Whenever you're pushing a rubber stopper with a glass tube, always push the rubber stopper. And I can actually watch the water. There is gas forming. Okay, 100%. There is gas forming. And in in about 30 seconds or so, we're going to see our first bubbles of gas. Now, because that tube popped off, I probably should have started. You know what? This is it. I'm going to press stop, and I'm actually going to press start. The moment I get my first bubble. That's what I'm going to do. I'm going to press start the moment I get my first bubble. I think that's actually a fair thing to do. That's an improvement to the experiment. Here we go. As soon as I get the first bubble, I'm going to press start. Here we go. Ready, set, go. There's my first bubble. Okay. Yeah, I think that's a fairer way of doing this experiment. 100%. Because I've actually produced a fair bit of gas before you got the first bubble. And so I think it's better to start the timer once you've actually seen a bubble pop out. because you actually needed a bit of gas to push the water through the tube. And by pressing the start button way at the beginning, you're not making any allowances for that. So I think this is much better. Yeah, I think this is much better. And I'm just checking the temperature of this. The interesting thing will be how much citric acid and magnesium ribbon are actually used up in this chemical reaction. And you know what? I actually don't think it's very much. I can calculate it, of course. Ooh, see the bubbles? So I'm looking here at the 5 mil mark, because that's when I'm going to press stop. Give it a bit of a swish just to make sure we've got our reaction going still. And ready, set, stop. 2 minutes 28. So that's 2 minutes, that's 120 seconds plus 28. 120 plus 28, 148 seconds. Okay. So I'll just jot that down, 148 seconds for 0.5 grams. Good. So, I'm very happy with that. There's some hydrogen gas in there if you want to come and get it. And what we now need to do is pull off the rubber stopper. And I'm going to... Ooh, there's something in that beaker. I'm going to pour that in there, but I'm going to remove the magnesium ribbon. Okay? You can see it's gone quite shiny. I actually want to keep that for another experiment later on. So I'm actually going to, I'll give my magnesium ribbon, I'll wash the acid off it. Okay, because that's still magnesium, but we really should actually start with a new piece. Okay, we should start with a new piece. So I'm going to now, I'll put that back in the bottle when it's dry. We need 3 ml of water. So I'll get my 2 and 1. And we need 1 gram of citric acid. Turn that on. Wait for it to go 0, 0, 0, 0. When you use these scales, treat them very gently. Tear. Now it reads 0, 0, and I want 1 gram. .6. Okay, there's 1 gram. Take my filter paper and in it goes. Oh, this is going to be quite the concentrated solution, that's for sure. I wonder what the solubility of citric acid is in water. Very easy to look up. Okay, I can see. I know it's very soluble, but there is a limit to how much citric acid can be dissolved by the water. it's something, usually you get a number like 200 grams per litre of water or something like that. That means you can only dissolve up to 200 grams of citric acid in water, in a litre of water. For sugar, I believe it's 2 kilograms or 2,000 grams of sugar will dissolve in 1 litre of water. So water will actually dissolve a lot of sugar. Water is actually a very good solvent. Okay. All right, there we go. And remember, I have to fill this one up. So there we go. I'm just going to put it under there like that now. Put my finger over the top, and then I'm going to use the gas to displace it. Oh, I've got a bubble in there. I've got to get rid of that bubble. Boop, goodbye bubble. Pop that tube up. Good. And dry my hands. Pop my 1 centimetre in of ribbon. Okay, so this is a new piece of magnesium ribbon. Give it a bit of a swish. Now the downside is, of course, it's cold, and I should probably measure that. I should actually make sure that we're starting at the same temperature each time. So that's an improvement to the experiment. The improvement to the experiment would be to make sure we are starting from the same temperature each time. That's actually very important to ensure that this is a valid experiment. So probably would be better if we use the Bunsen burner to bring it up to like 20 degrees or something like that. Now notice I haven't started the stopwatch yet, because I'm going to do the same thing where I'm going to actually make sure we get a reaction happening. The gas is going to push the water, and then once it's pushed out the water, that's when I'm going to start the timer. Give it a swish, 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 swish. And oh, I can see we're not that far away. We're not that far away, so I might reset my timer and get ready. This is what we call a quantitative experiment. A quantitative. We're actually measuring quantities, and in this time we're measuring the mass of the citric acid, the length of the magnesium, which is actually the length. The mass depends on the length, so it's all very quantitative. The time it takes to fill up, well, not to fill up, but to produce 5 ml of gas. Yeah. So there's actually, oh, we're pretty close here. Okay, here we go, and start. All right, so we've got our bubbles of hydrogen gas. Now, hydrogen gas is way less dense than the water, and so the gas travels up to the top. And don't forget, the gas is made up of particles which are moving around, and they're actually going to be colliding with the walls of the glass, but also with the surface of the water. And so those collisions are known as pressure. And that pressure is pushing the water down. Now that pressure has to be greater than air pressure, because air pressure is pushing down on the water surface. That force is basically carried through the water as a compressional force and is pushing up on that air there. But if that, not air, the hydrogen in there, and so if the hydrogen pressure is higher than the air pressure on the water surface, then that will cause the water to get pushed down and be displaced, and we can measure the volume of the gas. Not a bad way. I think this is actually a pretty good way to measure the volume of gas produced. You can also use syringes. Now, I've used plastic syringes in the past, but there's a bit too much friction with the rubber stopper in there, the rubber plunger. So I now tend to use glass syringes with glass plungers, and the glass is ground so that, believe it or not, no air can escape through the you can actually get very tight fitting glass syringes that are easy to move in and out, but actually stop the air or stop gases. Okay, so we're at 120 seconds. I'm going to give this a quick swish. Woo! 120 seconds. This is interesting. This is interesting. Okay, because I'm getting a result I'm going to get a result which is quite surprising. Okay, I'm going to get a very surprising result. Yeah, and to and to work out why, I'll tell you why it's now taken longer. A higher concentration has now taken longer. Now that's very surprising. One would imagine, and there we go, 5 mil, 2 minutes 55, which is 120. 2 minutes. I'll just go 2 minutes 55. 120. That's 175 seconds. So 0.1 grams is 2 minutes 55 is 120. It's 175 seconds. So it's gone from 148 seconds to 175 seconds. I would have thought that the time would have gone down because of the high concentration, but the time has actually gone up. Do you know why? Do you know why? I think I know why. I know why. Because as I dissolved more citric acid, it went colder. And so my starting position was not good. So what that means is I'm going to start the experiment from scratch. That's right. That's what I'm going to do. And so I'm going to correct the experiment from the very beginning. Okay? So, but this is how we learn. When I write these booklets, I don't actually trial every single thing, you know. I use my past experience and what I think is good knowledge, and sometimes I get it right, and sometimes it's a learning experience. Okay, that's what we call it. We call it a learning experience. So, I'm going to put this bowl down here for a tick. I'm going to get out my Bunsen burner, my heat-proof mat, my tripod, my wire gauze, my glasses, and I'm going to get 3 ml of water in here, and I'm going to come down to the right height, like that. Pour that in there. And I'm going to change the amount of citric acid. Rather than 0.5, 1, 1.5, 2, I want to reduce that. I want to reduce that. I think the concentration is so high that it actually is not going to make a huge impact. So what should I change it to? What about 0.3, 0.6, 0.9, 1.2? That's what I'm going to change it to. Okay. All right, so I'm going to change it now on the hop. And so I need 0.3 grams of citric acid. So I get my watch glass. I mean, I could have started this video from, you know, restarted it, redo the worksheet. You'd never know. You'd never know about these issues that we'd have. I think it's better to learn these issues together. have our struggles. All right, there's nothing wrong with a struggle. Why? Why do you have to be presented with perfection right at the beginning? You know what? 0.2 grams. 0.2 grams. No, we'll go 0.3. We'll go 0.3. Because I'm using 3 ml of water, and 0.3 sounds good, I think. Come on. Tappy, 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 tappy. Oh, went over. Silly Billy. I knew that was going to happen. Gotcha. Tap it back a bit. There we go. Close enough. And let's take my 0.3 grams. Pop it here. Put it in. Like that. Give it a good swish. And what I'm going to do is I'm just going to give it a burst of heat. Okay? Going to give it a burst of heat. If I can get a match. Oh wow. Let's get another matchbox. Redheads are usually a very good match, I must say. Now you can actually hold your just push that there like that. I'm dissolving it and warming it, dissolving it and warming it. Okay. I don't want it too warm. Make sure it's fully dissolved. Okay, I'm going to turn that off, and I'm going to get out my thermometer now. Pop in my thermometer. I haven't quite fully dissolved it yet. Yeah, that's about right. You really have to get your probe in sideways, right? You've got to get your probe in there sideways so that you can measure properly. Oh, it went warmer than I thought. Okay. 45.9. Okay. So I might call it 45 degrees. 45 degrees Celsius. That's the temperature that I want to perform this at. 45 degrees. And I'm going to get my bowl. I have to move fairly quickly because the temperature is going to fall fairly rapidly. And that's an issue too. Okay, get a centimetre of like that. Pop that in. Has it gone in? Yep, give it a swish. Push this on. Pop this here. So now I've got 0.3 grams of get rid of that bubble. Oh wow, I can actually see that it's producing the gas quite quickly. I can see the bubbles there. That's okay. That's okay. Be better if I had some help here. Can you help me please? Reset. And oh, hopefully that's still all right. Dropped off the table. Got my first bubbles. Press start. Okay, here we go. Here we go. Wow, this is called modifying an experiment on the run. So we started at about 45 degrees, and I'm not sure if you can see this, but even though we've got a lower concentration, it seems that the rate of reaction is much faster than before, and it's because of the fact that the temperature does make a big difference. It's very interesting experiment. So if you want polished, go watch another YouTube channel, alright? If you want to have everything smick and not real, I'm not the guy to watch. If you want to see someone who's trying to learn from their mistakes, you're on the right channel, people. So we're pretty close here. Yo! Ready, steady. Okay, 1 minute 30. That's 60 plus 30, that's 90 seconds. 90 seconds. Alright. Good job. Let me record that. 90 seconds. As I said, it'd be better if I had a few hands, wouldn't it? Pop this down here, because I'm going to need the Bunsen burner. Alright. You know what I'm really tempted to do? I'm so tempted. No, I'm going to do it properly. I was thinking I'm so tempted just to actually add the 0.3 grams, but I won't do that. Oh, my magnesium ribbon's almost gone. It is, it's basically gone. Interesting. Okay. Need to get out another piece. I see it there. Okay, so this time I need 0.6 grams. 0.6 grams. You can stop, actually. If I start it, I won't have to reset the calculator each time. No, the phone. Tear. And 0.6 grams. Let's go for it. Tiny bit over. Shh, don't tell anyone. Just, that's a secret between me and you, okay? And pop in there. In you go. 0.6 grams. What do I need? 3 ml of water. The measuring cylinder is far more accurate than that little pipette. And we need to get the temperature up a little bit. Remember what temperature I started with last time? 45! 45! Everyone yells out. 45. Push that on. Give it a good swill. Heating, 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 heating. This is a great way to mix a solution. Okay, that's dissolved. Let's measure the temperature, shall we? Push him in. Come on, 37.5, 43. 45. Good job, Jacob. 46.5. 47. Okay, 47.1. So it stopped rising. So that's good, because what that means is if I go fairly quickly, I can even keep that on if I want. I have to get my centimetre of magnesium ribbon. Pop that in. Pop that there. Nice. This pick's going to pull it over, I think. Oh no, I'm just going to go down there like that. Get my container of water. Fill him up with water. Go like this. Need to do this all fairly quickly, because here comes my gap. Ow! Just put my little pinky. Stop, reset, start. Okay. Look at that. Ha ha! Yes, success! I like it. Oh, I like it, I like it, I like it. We started with the same conditions in terms of temperature this time. Yes. And this is going much faster. Done. 37 seconds. Incredible. 37 seconds. I love science when it works. Don't be afraid of failure. Learn from your failure. Learn from your mistakes. Make your changes. Improve. What do I say? 37 seconds. There was two problems with that original experiment. One was I was using so much citric acid to start with that the concentration was already so high. I think that was the problem. I just had one of the problems. I just had so much citric acid in there that by adding even more, the concentration was already like saturated. It was already a saturated, you know, quite saturated. There was already so many collisions, and so by adding more, it wasn't actually making much of a difference. But the big issue was the significance in the temperature. That was the big issue. Okay. What do I need? 0.9 grams. 0.9 grams of. I'll just dry my. Got to wait for it to 0 before I touch it. Put this on. Or tear it. Not 0.9 grams, and I need my conical flask. Need my 3 ml of water. And going to heat that up. Glasses. mix. We want to get it to about 45 degrees. I think it's going to take a little bit more effort this time because it started colder because of the more citric acid that was needing to be dissolved. So I'm just sort of guessing about how long I need to do this, what feels about right. Just from experience, I guess. Okay, let's try that. Pop this in, push it in horizontal, perfect. 38.8, 44.3, 46.6, 47.5, 47.8, 47.9, and then it will start to drop 47.8. Okay, so it's now dropping, which is good. It's got to drop an extra 1 or 2 degrees. I'm not in such a rush this time. Okay, so I don't have to rush it as much as I did a moment ago. Because remember, it was like, I think 46 degrees or something last time, and so I had to go really quite quickly. I don't need that, don't need that. Oh yeah, I need to put water in my measuring cylinder. I need to turn it upside down. This needs to go like that. This is a better order of doing it. Just dry my hands. Dry my phone. Get my phone ready. Okay. I need my centimetre of magnesium ribbon. So I've got to break that one in two. Good. Pop him in. Give it a mix. Pop that on. Give it a mix, mixy, 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 mixy. And as soon as I got my first bubble, then I'll start the timer. Give it a quick swish. First bubble, start. Okay, bubble, 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 bubble. Look at that. Look at those bubbles racing. What was the last one? 37 seconds. We're up to 20. Whoop. 24. And boom, 31 seconds. Okay, 31 seconds. So I've got 3 results, and I want to go for a 4th one, but because of the length of this video and the length of the course and that sort of stuff, I'm going to put a hold to it there, not do the 4th one, but hope that you do the 4th one. Yeah, that's my hope, that you do the 4th one, because I'd like to analyse and graph these results. All right, so my original was 0.5 grams and it took 148 seconds. And then 1 gram took longer. And so I stopped the experiment there, because I realised I needed to readjust. And so this time, how about we do modify and put a 45 degrees Celsius start, and we did 0.3 grams, 0.6 grams, 0.9 grams, and we had 90 seconds, 37 seconds, and 31 seconds. Okay? And so we'll do concentration and reaction rate as the title of that graph. The thing that we changed, the independent variable, was the citric acid used. Citric acid used in grams. There's 0, and I might do 0.3, 0.6, 0.9, 1.2, and then this vertical is the time. 0, and we might go up by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So 0.3 grams of citric acid in 3 ml of water took 90 seconds. So I'm going to put a nice cross there. 0.6 took 37 seconds. So I'm going to put a cross there. 0.9 took 31 seconds. Hopefully you've done 1.2 and you know where it is. I suspect it's going to be around about here, because I actually suspect, and then I'm just going to do a graph like that. I suspect that there's like a limit to the concentration. Like, doesn't matter if you get, water will only dissolve a certain amount of citric acid, so it can reach. There's a maximum concentration of citric acid you can get in water, and this graph, I think, indicates that there's actually a maximum concentration of citric acid, and once you reach that like maximum, you're not going to change the rate of the reaction. So discussion. Well, we realised we had to warm up the initial solution so that we could start with the same temperature, because that made a huge difference to the reaction, right? However, we definitely found that once we'd done that the concentration does affect the rate of the reaction, and that the higher the concentration, the faster the reaction goes. For further experimentation, I would like to do less citric acid, like 0.15 grams. And I could actually make a bit of a prediction. Okay, I'm going to make a bit of a prediction that it would take like 110, 120, like 125 seconds. That's called extrapolation, where you extend your results. Or you could interpolate and say, oh, what would be the rate of reaction if we use 0.45? Then you go to 0.45, you go up to your graph, and then you go across and you say, oh, it'll be about 58 seconds. That's called interpolation. The conclusion, does the concentration of acid affect the rate of reaction? Yes. We would say the higher the concentration, to a point, increases the rate of the reaction. There we go. What a big lesson. Hopefully you've enjoyed it. Look forward to seeing you again soon. Bye for now. Hey everyone, in this lesson we're going to be exploring a very important concept to do with acids and bases, and that is neutralisation. Now, when I was a kid in high school, on Saturdays in the school holidays, I used to work with my Uncle Pete, and with a couple of my cousins, we'd form a paving team. And we'd go do paving, you know, we'd go do someone's driveway or around a pool or some paths. And you started by, well, digging first to make things flat. Then you had to put down sand and make it nice and level with the sand. And then we'd wheelbarrow pavers over there, and then we'd lay these pavers on the ground on top of the sand. And then you had to put cement along the edges to hold it all together. Now, a long time ago, and you know, like work health and safety wasn't such a big thing, and sometimes we didn't use gloves when we were doing like the cement. And I remember there was times where I'm patting the cement, you know, along the edges just with my bare hands. And I get home and my hands were red and sore, and there was bits of skin peeling off, because cement is one of the ingredients is like calcium hydroxide and calcium oxides, which are very basic, very alkaline, quite caustic, and that was corroding my skin. And so I would, because I knew a fair bit about science, I'd either get vinegar or lemon juice, which is acidic, and I'd add it to my skin, and that acid would neutralize the base, and my skin would repair itself relatively quickly. Having said that, I sort of do wish that I wore gloves, and I certainly recommend that you use gloves if you're ever using like cement-based or mortar-based products. There we go. So that's just one little example. So we're going to sort of do the theory, and to do acid-base reactions, we need to look at the pH, and to look at the pH, we need some universal indicator solution. So how about we boil up 6 ml of water. So I'll just wash my equipment. 6 ml of water, because, you know, I've been using citric acid, and maybe there's some remnants in there, I'm not too sure. And 3 pieces of filter paper. Now, of course, oh, there we go. If you use more, that's not a problem. I'm going to fold it up because we want to boil the chemicals off it. So let's pop that in here. In you go. And get my safety glasses. Light up my Bunsen burner. Whoop. Wonderful. And pop that there. Probably be good to have my tweezers and a stirring rod. And I might just give this a real blast. So for this lesson, we're going to need some vinegar and some bicarb soda. So it doesn't take too long for this to happen. I'll hold the beaker with my tweezers. And uh-oh. Houston, we have a slight problem. You know what the slight problem is? Contamination. It's gone yellow. It should be green, because it should be neutral. But, as I said, I didn't wash out my, whoa! Oh, oops-a-daisy. I didn't wash my equipment out very well. So, I've got a slightly acidic solution there. Is that a problem? Not really. Not really. I think I can live with that. We can do some bit of chemistry to fix that. Okay, so my solution is yellow because it was actually, there must have been some citric acid there. Now what am I saying? Add 1 ml of vinegar to the pH solution. Okay, so I need a measuring cylinder. Where's my measuring cylinder? There it is. And pop that there. I might use my measuring funnel, and I need just 1 ml. Oop. Ew, that was 2 ml. That's okay. Hard to pour from a big jug like that. And so I don't repeat too many mistakes, I'm going to give this funnel a wash before I put it away. And I want to pour in 1 ml of the vinegar. Now, no surprises, it hasn't changed colour because vinegar is acidic. The citric acid was acidic, and so it has gone a darker yellow. Okay. Then it says slowly add bicarbonate solution, bicarbonate solid and stir. So I might put a bit of bicarb onto the little plate, little watch glass, and I've got a little spoon. Yep. Let's start with, I don't know, 1 spoon. I'm using the stirring rod to push it on. Might start with 1 flat. Whoa, whoa! Well, that was cool. That was cool. So, whoa. Ta-da! So, there was a chemical reaction. Bubbles were formed. Bubbles are a new substance. They weren't there before. Now, they're actually bubbles of carbon dioxide gas. And it's gone green. Yay! It's neutralized. So, that was actually quite exciting. I neutralized the acid with the bicarb soda, which is alkaline or basic. That's what a neutralization is. I didn't actually expect it to go green so easily, okay? Normally I expect to have to add a bit more. So I might just do that. Let's see what happens. Let's add a spoon of bicarb. And what you'll notice is that the reaction wasn't, I put in the same amount of bicarb, but we didn't get that same reaction. That's because it was a relatively neutral solution. We'd used up the acid, and I put in a 3rd spoon, and almost no bubbles. What is a bit surprising though is the fact, okay, well actually it's not surprising, because this green that it's gone now, this like dark green, is actually like a pH of 9.5, and that's probably, that seems to be all the as far as the bicarb will go. How about I add a little bit of vinegar? Whoa! And when I add a bit of vinegar, I do get the bubbles, and I do get a colour change. Now, how will I know when I've got a neutral solution? Well, I'll just make sure that I am getting a full, complete reaction, that the reaction has gone to completion, and I'm looking at that by the bubbles being produced. Yeah, might just add a little bit more vinegar. Give it a mix. Give it a stir. Still getting some bubbles, but that colour has gone like a much nicer green, indicating a pH neutral solution. So basically the citric acid, not the citric, the vinegar, otherwise known as acetic acid, is reacting with the sodium bicarbonate to form carbon dioxide gas, water and a salt. And in this case, the salt is called sodium acetate. Sodium acetate. What does sodium acetate look like in its solid form? Glad you asked. I'm going to get myself a beaker, add probably 5 ml of water, and we're going to make a water bath, a hot boiling water bath. Get the Bunsen burner going. Light him up. It's probably a bit strong. That's good. Let's just move things a little bit around so that it's nice and straight. Fantastic. Then I need a watch glass. Now I've got another watch glass in here. I'll just make sure it's nice and clean. Perfect. Pop him on top. Get a pipette and squirt some. I might just blast this up for a tick, make it happen quickly. Alright, I want this boiling fairly quickly. Whoa, look at that. It doesn't take long, does it? Almost boiling. Once it's boiling, then I can reduce the heat. Okay, then I can just back the heat back off. I'm in a good place now. Suck up some of this neutralised solution, which I'm hoping is sodium acetate solution. Put some drops on. Like this. Beautiful. Now, when I used to do this as a school teacher, used to have 8 benches around the room, and when it was boiling like this, you could actually get the kids to sit down at their desks and do some other work, because it took quite some time. It could take 15, 20, 25 minutes. Because the beakers were bigger, the bubbles were the same, the boiling bubbles were the same, but, lost my gas. Because the bubbles were the same size, regardless of the beaker that you're boiling it in, the bubbles are the same size. Now, if you've got large beakers, the bubbles don't really affect it too much. One of the, series of downside with Tiny Science Lab in that is that because the equipment's small but the bubbles are the same size, the force of the bubbles can actually cause the equipment to move. Now look, at the moment I must admit it looks quite perfect, so I shouldn't really talk about the downside of it. This is happening super quick, 5 times quicker than using regular size equipment. And in fact, the beaker is not really bumping around at all. You can get something called little boiling chips. Currently, as I film this, Tiny Science Lab doesn't supply boiling chips, but maybe when you're doing this course, by then, with sometime in the future from now, by then maybe we've added it to our list. And if you put a few little boiling chips, and boiling chips can be little tiny glass balls, or they can be like little pieces of broken pottery. But basically they provide a surface for the bubbles, the steam bubbles, to form on, and it causes the amount of what we call bumping. That's where the bubble causes a shake or a movement in the equipment. It reduces the amount of bumping. But as I said, this is quite perfect. The main thing to watch is that we don't actually boil off all that water. So at the moment, that water in here is boiling at 100 degrees Celsius. And that means that the glass is at 100 degrees Celsius. But what can happen if this dries up, you go for a walk, not a good idea, come back, all that water has evaporated. The moment it's evaporated, the beaker will actually start heating up 100, 120, 150, 200, and as it heats, the particles are going faster and faster and faster. The particles of glass are vibrating. Greater vibrational energy that causes them to expand, and so your actual glass beaker can expand, and it can expand to such an amount that it can actually crack, and the glass can just crack. But typically what will happen is it will be really hot, and then you turn it off, and then it cools quite quickly. And different parts of the glass cool at different rates, and that can also cause the equipment to crack. Now, while I've been talking, the neutral solution is definitely evaporating, because I can actually start seeing a bit of a crust around the outer ring. That is the sodium acetate that is being left behind. The sodium acetate's got a much higher boiling point than water. The water in the solution, that boils off at 100 degrees Celsius. Sodium acetate, its boiling point might be, I don't know, I could look it up. I'm guessing like 1500 degrees Celsius. 15 times higher than water, and so it's just left behind as salt crystals. And sodium acetate, I'm sure it's got a purpose for something. It's probably in some type of, you know, medicines or some type of multivitamin, or anyway, it would have a particular use. I don't actually know what that particular use is, but someone else might know. And sometimes when you've almost got to the very end, you can sort of, and there's only a few drops of the liquid left, then you can sometimes turn it off. Now, a question that you might be asking is, why don't I just boil that? You know, why don't I just boil the water off that neutral solution? Well, the problem is that as it boils down, it will start to spit. And you get like the sodium acetate will be going everywhere. And if that sodium acetate is what we call the product, and if you're trying to save the product, then you lose the product. And I've often seen it just becomes a real big mess. This is a very gentle way to evaporate a solution to actually to find out what's been dissolved in there. We call that substance, what's been dissolved, we call that the solute. Okay, so the solute in this case, I've said it 5 times, is sodium acetate, and the solvent in this case was the water. So I've been driving off the water, and you know what? We are done. That's not too bad, is it? Because I've been talking the entire time, trying to teach you some good old chemistry while this has happened, and in actual fact it has happened. And so I'm going to grab and look, the water coming off is actually the little bit of water from here condensed. It's clear and colourless, but you can see that crust. Okay, look at that, that's sodium acetate. There's a bit of blue on there, which is actually the universal indicator colour as well. There we go, we've just obtained the product. That is, how wonderful is that? So anyway, what about doing what we call a little bit of quantitative analysis? And the question is to find the mass of citric acid which has the same acidic value as 5 ml of vinegar. Okay. So I'm going to tip that out. I actually need some, I probably don't need it, but I'm going to have it anyway because it won't really, it will help. I'm just going to make a bit more of the pH universal indicator solution. And I'm just using that hot water that I've just been boiling away for a little bit. So, and I'm a bit paranoid about my equipment that I've got it contaminated with acids and bases and stuff. So I'm going to give it a nice wash. And yeah, no wonder I'm a little bit paranoid about it, because look at that, it's gone blue. Ah, painful. It's actually already basic. It's not what I wanted at all. So what I'm going to do, I might just really use the smallest amount of citric acid, okay? And I might get a second, what about a little plate or something? Here we go. Give this a bit of a clean. What am I going to use? Well, it looks like I've left some chemicals on there and it's gone like a little bit coloured. I'm just going to put a very small amount of citric acid in here just to see if I can neutralise. Oh, went way too far. Yes, and that was a snort. Let's put a bit of bicarb there. There we go. I've neutralised it. There we go. There's neutralisation in action. I've got a neutral solution there. Okay. Now, what am I interested in? Okay, I want to find out the equivalent mass of citric acid to, what is it, 5 ml of vinegar. So, all right, what do I have to do? Dissolve 0.5 gram of sodium bicarbonate in 5 ml of water. That's the first thing I need to do. So, there's many ways to do this. This is just the way that I wrote down. Let's see how it goes. So let's turn that on. And I need clean equipment. 5 ml of water. 5 ml of water. And what did I put in that last? Probably vinegar. And so I need to give it a wash. And so I want 5 ml of water. Was it 5 ml of water? Yep, 5 ml of water. And put this here. Come down now. That was actually quite a lucky guess, that. The bottom of the meniscus needs to be on the 5. So here's my 5 ml of water. And now I need to put this here and tear it. It says 0, 0, 0, 0. And so now I'm going to add 0.5 gram of sodium bicarbonate. So I can just go like that. 0.14, 0.28, 0.46, 0.50. Woo! I'm not lying either. It's not 0.50. Give it a quick stir. It's going to need a better stir than that. So what have we got? 0.5 gram of sodium bicarbonate in 5 ml of water. That's the concentration of that. 0.5 gram in 5 ml of water. Sodium bicarbonate is not as, doesn't dissolve as quickly as sugar or salt or citric acid, that's for sure. Even though the particles are really fine. Now, what do I say, even though the particles are really fine? Because if you've got fine particles, it means you've got bigger surface area, more of the particle, or more of the sodium bicarbonate is exposed to the water, and that also affects the concentration rate, okay, the concentration speed. That is pretty good. Ah, no, it's not. It's not dissolved. I shouldn't lie. It really does take some time to dissolve that. So now don't bang your glassware because your rod will go straight through it. What am I going to do now? Find out how many mils of vinegar are required to neutralize the sodium bicarbonate solution. Okay. All right. So pop that there. And I'm going to start with 5 ml of vinegar. And again, oh, that was lucky. I've got 5 ml of vinegar here. And I might actually, I can add, adding a bit of water is not a problem. Okay? That won't actually affect my reaction. The reason I added that bit of water is so that, because it's got the universal indicator in it. And so I've still got 0.5 gram. I've still got 0.5 gram of sodium bicarbonate, even though I've got a little bit extra water. Now, I'm not going to add a lot. I'm going to add little bits of this vinegar at a time. So I'll suck up some and I'll squeeze that in, and I can see bubbles forming straight away. Bubbles forming straight away. Let's add some more. go, we've still got reaction happening. Still got reaction happening. Still got reaction happening. Okay. Still got reaction happening. Still got bubbles. So we're still going. The bubbles are definitely less, but they're still there. So we've still got unreacted sodium bicarbonate in there, in the solution. Definitely less bubbles. I think we're almost using up the full 5 ml, which I'm a bit surprised about. I can probably just pour that last bit in. Mixy, 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 mixy. This is a bit surprising. I need some more vinegar. Okay, I need some more vinegar. I have to put a known amount in. I have to put in like another 5 ml. Perfect. This is a bit of a problem if it's overflows. My container's not going to be big enough. But I think we're very close to the end of it. Yeah. Almost no bubbles. Almost, but not quite. Okay, I'm going to have to get this 20 ml container out. Transfer that to that. While still reacting. Takes a lot of that vinegar to react with 1/2 gram. We're talking like 10 ml. We're talking like 10 ml of vinegar to react with 1/2 gram of the bicarb. I'm in complete shock. Absolutely, I'm in complete shock. Now that would actually just take, I'm gonna say it takes 10 ml of vinegar to neutralise 1/2 gram of the bicarb soda. Now if you go to Woolworths, you can actually buy double strength vinegar. That would mean it would only take 5 ml of the double strength to react with 1/2 gram. Basically, you are just buying a lot of water. When you buy 2 litres of white vinegar, you're actually buying a lot of water, I can tell you that now. So, all right, interesting. Now I want to find the equivalent, okay, amount of citric acid that I have to add to half a gram of bicarb. So let's pop this on. Let's wait for it to settle. Like so. Tare it. I need to put in half a gram of bicarb. 0.2, 24, 32, 4, 0.4, 0.6, 0.49. That's close enough. 0.49. Have to stir it, of course. Okay, have to dissolve it. Mixy, 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 mixy. That'll take a little bit to dissolve. And now I need to get a known amount. I need to get a known amount of citric acid into a watch glass. So let me just clean this bicarb off. Pop this here. Press the tare button. And this has actually got, this has had a very important practical application to me. My company basically. I go to schools and I do incursions. And for primary school, I'll do chemistry incursion. There's 1 gram. There's 1 gram of citric acid. Okay, so I've got 1 gram of citric acid on this thing. And I'm going to start scraping in just a little bit of citric acid to start with. There we go. Now I have to... Oh, no, 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 no! Oh, you twit! What a dope! Do you know what I've just done? I've just wrecked that experiment. Oh, stupid. I lost the product. I don't know how much of the bicarb came out. I don't know how much of the citric acid came out. Oh, what a dope. Okay. Got to start that again. Tip that out. Great. This course has just gone from like 20 hours to 30 hours in one foul swoop. Woo! You're probably going, what, we're paying this guy? Well, at the moment, when this video goes live, it's going on YouTube, which you can access for free, so you're technically not paying me. So, but who knows, down the future, maybe you have paid for some subscription somewhere, somehow. So, my apologies. So what do I need? What do I need? Wait for it to 0. Put this on, tare it. I need half a gram of bicarb. That's the first thing I need. .2. Oh, that's terrible. Went to 0.91. Scrape a bit onto the table. Pop that there. 0.58. Scrape a bit more off. 0.52. Shh. That's close enough to 0.5. Some will get stuck on the paper, you see. Approximately 5 ml of water. Now, it's not actually that important how much water you use. The important thing the important thing is how much bicarb there is. That's what's really important. So let's give that a good mix. Then I need some citric acid, and if I pop that there and I tear it, let's put the citric acid on. And I'd love 1 gram, to be honest. That will make it easy to work out how much I used up. That big lump caused the problem. Take a pinch off. 1.01. Good. Okay, are we ready? Here we go. I'm going to put in a little bit of citric acid. Just do it slowly this time. Remember, I stirred it, and then that made it go really quickly. Bubble, 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 bubble. I'll tell you why, because this will take a bit of time for it to happen, why this is important. Because when I first started doing these little chemistry incursions, and I, have 100 kids at a time, and so there's 100 little bottles of like vinegar, and then there's little containers of bicarb, and they're doing this reaction with the vinegar and the bicarb, and it's all good. It's all good. It's all great. The problem is they do end up using a lot of vinegar, and then there's 100 bottles where someone has to take the lid off, take the top off, and refill them between each incursion. And so it's a lot of work to do 100 bottles of vinegar. And so I thought to myself, rather than using a liquid in a bottle, what about if I used just the powder? And so I started using citric acid, and it's been so much better because I don't need to refill. I don't need to refill all the bottles. So let me keep tipping this in. Tip, 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 tip. Tip, 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 tip. How am I going here? Oh yeah, there's still plenty of citric acid there. So nicely reacting with that bicarb. Careful, careful. If it overflows, I've wrecked it. And it's actually reacting with like some of that undissolved bicarb, so wasn't even worried about fully dissolving the bicarb. And tip, 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 tip. But that is interesting, isn't it? Because, oh, I think we're pretty close. Whoa, just spilled some. Do I need a little bit more citric acid? Let's just see what happens. So far, 1 gram of citric acid has fully reacted with half a gram of bicarbonate of soda. Okay, so we've got to bear that in mind. I've got to get some more citric acid, a known amount. I'll bring it up to 1 gram again, you know. There we go, 1 gram. Let's add a bit more. It looks like the reaction has come to a complete. Yeah! No more bubbles. So I used up 0.25. So the quantitative analysis is that it took 1.2, get this right, it took 10 ml of vinegar to react with half a gram of sodium bicarbonate. So it took 10 ml of vinegar to react with half a gram of sodium bicarbonate. It took 1.25 grams of citric acid to react with half a gram of sodium bicarbonate. Therefore, the equivalent in terms of the amount of acidity is 10 ml of vinegar to 1.25 grams of citric acid. So therefore, if I'm using 100 ml of vinegar, I need 10 times 1.25, I need 12.5 grams of citric acid. And so I can use that for my planning for the day. If I need to replace 100 ml bottles of vinegar, then I need to make sure the kids have got 12.5 grams of citric acid. How good is chemistry and quantitative analysis? Very good, very interesting. Hopefully you've had a wonderful lesson. I know how I have, and I look forward to seeing you again soon. Bye for now. Hey everyone, today we're looking at a tasty neutralization reaction, aka also known as sherbet. So, going to need some bicarb soda, some citric acid, and some sugar. Now I've got some sugar in this little bowl, and I'm going to pop the bicarb white powder in here. Now, interestingly, a lot of chemicals in science are white powders. Yeah, just the way it is. A lot of chemicals are white powders. Interesting. You can make a whole range of colours using combinations of them in reactions and that sort of stuff, like basically every colour of the rainbow with different chemical reactions. But it's interesting that many of the chemicals are actually white powders. Anyway, and so we actually need different ways to distinguish between them. And we're going to look at each of the ingredients of sherbet: sugar, bicarb, citric acid. And the sugar, it's a white crystalline solid. The crystals are, I don't know, about a half a mil, quarter of a mil by a quarter of a mil by a quarter of a mil, something like that. And you can get different types of sugars, like brown sugar. It's a rawer sugar. I quite like brown sugar. I have it on my fruit toast. You can get like caster sugar, which the crystals I think have been ground up a little bit more. But we can learn a bit about sugar by actually heating it up a bit. Now in your these containers you might find a steel pan. If we pop a steel pan there, and if I get a spoon, now I'm not going to put this spoon, which is from the set, I'm not going to put this spoon into that sugar because that would contaminate it. I actually need a clean teaspoon, and so I've got a clean teaspoon here straight out of the kitchen cupboard, I think. And I'm going to put just, you know, a quarter of a teaspoon of sugar into that pan. I'm going to put my goggles on and get the stirring rod, and I'm going to light this up. I don't want it too hot. I don't want to blast it like I normally blast things. I want to have the flame fairly low this time. Let me get my tweezers just to hold the pan and give it a little bit of a stir. Now if you're doing this, that would be good, okay, because it tells us a lot about sugar. Now the formula for sugar is C6H12O6. Carbon, whoa, straight away I'm actually getting some melting. The sugar molecule actually melts at a fairly low temperature. Okay, the sugar molecule melts. So the molecules, the heating breaks the bonds between the molecules. So that's what melting is. It's where the bonds between the molecules, not the bonds within the molecules, but the molecules between the forces between the molecules, and that causes it to turn into a liquid. Okay, so that's still sugar. It's a physical change. Smells a bit like toffee. Toffee's not as popular as it used to be, making toffees, probably because fates and things are not around as much. But toffees are very interesting. It's from melting sugar, and then you pour it into like little patty pans and let it cool. It used to be very popular, but not as popular now. But if you heat it further, you go from a physical change to a chemical change. And a chemical change is much more difficult to reverse. We want to do this in a ventilated space, probably outside, and I don't want it to go over the top. But it's turning black. Okay, it's turning black. And this stuff that you see coming off is actually water, H2O. If you look at the formula of the sugar, C6H12O2, can you see the C6H12O6? See the H12O6? See how the highest common factor there, or the lowest common factor is the 2, that it's actually 6H12O6 is a multiple of H2O times 6. And so you're driving off the water, and what are you left behind with? Carbon. And so we're actually being left behind with black carbon. Now I don't want to cook that too much, but it does tell us a little bit about sugar. Now if I put that underwater, then if I come back in a few hours time, I'm quite confident that that black substance hopefully will have dissolved. So same thing with this stirring rod. I'll put this stirring rod in water too, and hopefully that the sugar dissolves off. What about bicarb? Got some white bicarb here. So the formula is sodium, Na, H, hydrogen, carbon, and then 3 atoms of oxygen bonded together. So NaHCO3. And that CO3 is the carbonate polyatomic ion, CO3. It's got a valency of 2. Okay, and I might actually heat this one up as well. So let me just light him up. Sodium bicarbonate is very different to sugar. Okay, very different to sugar. If I pop that in and start heating it up, I've got a little bit of white powder in this pan, and if I heat it up, well, actually what is going to happen is it's actually going to undergo a chemical breakdown. It's actually going to release carbon dioxide, which is actually a little bit difficult to see. What you can, there's doesn't appear to be any change to it, but I can tell you there is a change, and I'm going to show you that change. I'm going to tip out that white powder, okay, and I just want a very small amount of heat. Okay, very small amount of heat. I'm going to put a bit of sugar on there like that, and we'll get a physical change fairly quickly. Turns into a liquid quite quick. See that liquid? Like that. If I add a bit of bicarb, and there was a bit of bicarb left over, because look at that, it froths up as it produces the heat of decomposition. The heat causes the bicarb to undergo decomposition produces carbon dioxide gas. And that actually is, whoa, that actually is honeycomb. Look at that. Woo! Smells delicious in here. Now, do have to, if you want to, you have to dissolve that in water if you want to get rid of it. It's going to be a bit difficult to get rid of. What about citric acid? Citric acid, the formula is C6H8O7, C6, so lots of carbon there, H8 hydrogen and some oxygen. If I put the aluminium pan there and try a bit of heat on that, oh, that was a lot of citric acid. Oh, very interesting. Look at that. Is it melting? Look, I didn't actually realise that it had such a low melting point. There we go. I've never actually heated citric acid before, and she's boiling away. Wow. I wonder if that means it's breaking down. Anyway, that's an area of that can be looked into. Huh. Okay, so the ingredients for sherbet are sugar, bicarb and this citric acid. And to taste them, put a bit of sugar, back of the hand. Make sure your hands are clean and washed. Sugar, sweet. It's got a crunchy texture because of those crystals and breaking them with your teeth. You wouldn't want to have sugar made out of diamond because the crunch would be your teeth, not the diamond. I really quite like sugar. Sugar's very nice. Bicarb soda, I wonder whether I like that. Put a bit of bicarb here. Bicarb not so nice. Bit salty. Bit bitter. Don't like it. Don't like that at all. Might do a tiny bit of citric acid. So sour. Sort of nice though. There you go. So, we're going to sort of do a bit of a taste test. Making sherbet. I'm going to start with a level spoon of sugar. There we go. I should use a knife. Forgot to bring a knife down. 1 level spoon of sugar. Half a spoon of citric acid. So half a level spoon of citric acid. No, citric, bicarb. Half a level spoon of bicarb. Pop that in. And a half a spoon of citric acid. Okay, tap, tap, tap. Half a spoon of citric acid. Give it a mix. Okay, mixy, mixy, mixy. Now, you shouldn't use your mortar and pestle to grind this because your mortar and pestle in your set probably is contaminated with chemicals. And when you're doing tasting in science, you should always, or food in science, you've got to use equipment that's not used for normal chemistry, okay? You've got to use bowls and stuff out of the kitchen cupboard and spoons out of the drawer cutlery. Don't use equipment from the set. Now, sherbet. It needs something to activate it, and that is the liquid water in your saliva. So that will actually provide an environment for the citric acid to react with the bicarb. So there we go. I've mixed it up now. I'm putting it on the back of my hand. Good. Oh, very fizzy. Very fizzy. So, very fizzy. Let's do the good. The fizz hits you, bang. Too fizzy for my tasting. I'm going to give a score of 5 out of 10. Now, rather than starting from scratch, because I only took a small amount out, I'm actually going to try an extra spoon of sugar. So now I've got basically 2 spoons of sugar, because I only trialled a really little bit. Okay, now some people say, well, that's taken out some of the reactants, and it has a little bit, but I don't want to throw out this whole lot and do it fresh each time. Of course, if you're doing a really important investigation, you start from scratch, but I don't think that's necessary this time. And different people have different tastes, so you could actually trial this on different people. See what they think. Mixy, mixy, you've got to get a good mix happening. Mixy, mixy, mixy. And that's a lot better. The sugar has like what's the word? It's diluted the citric and the bicarb. Sweet. Bubbles of carbon dioxide, sour. The bicarb and the citric acid, when they react, it's a neutralisation. It produces a salt. And so it actually goes from like slightly bitter to a sweet, salty citrus, sour. And our taste buds like that. Thai food, sweet, salty, sour, hot. I love a Thai beef salad because of the sour, the sweet, the salty. Sour, sweet, salty, chili. Yeah, what is it? No, pad Thai. Pad Thai, it's got the noodles. It's got a little pile of salt, little pile of sugar, a little pile of, it's got a lemon to squeeze, a little pile of chili, and so you can add those to get those 4 flavours. You can keep experimenting. Very good. All right, now, that's it for the sherbet. Bye-bye, sherbet. But that's a neutralisation reaction. Citric acid and baking soda produces water, carbon dioxide, the gas, and sodium citrate, which is the salt. Okay? Yummy. And so nuclear warheads, so many lollies. Mike and Ike, so many lollies rely on this sourness of the citric. Not that many lollies have sherbet in them these days. There are these lemon lollies that have got sherbet on the inside, and there's Japanese lollies as well, Coca-Cola lollies that rely on this. Go looking for them. Whiz Fizz, of course, is sherbet, but you can get lollipops with sherbet in it. So it still actually is quite a popular confectionery. Yeah. Now, what about a fire extinguisher? Can we make a fire extinguisher? Now, we should be using quite a big bottle for this, but I might, you know what, I might even try a tiny little, might try and make the world's smallest fire extinguisher. I've got no idea how this might work, but basically, I really don't feel like making a big one. So I can get citric acid in here with a bit of water, and then I've got to react it with the bicarb that sits here. Can I just like, okay, I'm gonna make it. All right, so bit of citric acid. I think that's this one. Yeah, bit of citric acid. Pop it in here. And lots of water. And if if I put on that rubber stopper, give it a little bit of a shape like that with the rubber stopper. I'm dissolving it as well. Dissolve, dissolve, dissolve. Okay, I've probably got too much in there now, I think. So I might just tip some out. Let's try that. Then, I'm just thinking what happens when I tip it over. Okay. This has to be wet. Okay. So I'm going to wet that glass tube, and I'm going to dip it in the bicarb like that. Very gently pop it like that. See? Then if I've got a fire, alright. Now, this is not the smartest thing to do. What about if I make a little fire? If I do it on my heat-proof mat, it's gonna wreck the heat-proof mat, isn't it? So what about if I get my tweezers? Actually, that's cooled down by now. I still should use my tweezers. I think that's got the citric acid on it still. I'm going to build just a little fire. Another match. Now this is best done outside, of course, my friends. And safety goggles, just in case. Make sure there's nothing flammable around. This, or make sure your computer's not too close if you're watching this on a computer, because this might get a little bit messy. Woo! I'm not very good at lighting fires. Am I? Maybe there's something going on with that bit of citric acid in it. Oh, okay, there we go. I've got a fire. Quick, call the fire brigade. Here we go, I'm going to turn this over. Whoa! Oh, look at that! That was amazing! You're like, Jacob, that was not amazing. You know, but... You know, we got the chemical reaction of the citric acid and the bicarb produced carbon dioxide. When I turned it over, the gas pushed it out. Obviously, that would need to be a smaller nozzle, and we need bigger volumes. But you get the idea. That's the important part. The fundamentals were there, my friends, you know. And that's literally how they used to make fire extinguishers in the old days. You used to turn them upside down, and the vinegar, I think, mixed with the bicarb, and then squirted it out. And the carbon dioxide that's produced is actually quite good too, because it's denser than air, and it creates a bit of a blanket, and it sort of suppresses the oxygen. Citric acid, yeah, well, I was thinking about when it's dissolved, it cools down, of course, but it's already dissolved. But maybe if you have the baking soda dissolved, and then the citric acid reacts with it. Anyway, the main thing is that you saw the theory involved. So there we go. A tasty neutralisation reaction and a fire extinguisher to put out those fires. Hopefully you've enjoyed the lesson. Bye for now, everybody. Hey, well, welcome to another chemistry lesson. I'm hoping that this one will be excellent. So, quail eggs. Now, I've bought these quail eggs from Harris Farm, and I know there's quite a few Harris Farms around the place. Can you do this lesson without quail eggs? Yes, you can. You can actually use normal hen's eggs. Quails are a little bird. They're not very big. You know, they're about that big. And look at the little tiny eggs. They're so cute and so beautiful. A lot of them are like got a beautiful speckle on them. They remind me of a one of those speckled ponies. Actually, I think they're called Palomo. I'm not sure what that pony's called. You could look it up. Some of you, I'm sure, are horse lovers and are saying, "Oh, it's blah blah blah." Anyway, sorry if I forget. These are often used in Asian cooking. Typically they hard boil them and peel them and then put them in like salads and noodles and that sort of stuff. Yeah, quite popular in Asian food. So, the first thing we're going to do is put these eggs in 2 different acids. And one of the acids we're going to use is vinegar. So, I've got a cute little glass here. And it's actually a double glass because it's actually got a vacuum and it's for coffee shots, I think. And the vacuum is to stop heat transfer via conduction and convection. Okay, so we've got some vinegar there, and I'll get myself an egg out. And let's pop the egg in. Alright, now the moment you pop the egg in, you actually start seeing some, like a bit of a fur on the outside, and that fur is some bubbles. And the bubbles alter and it doesn't take long for those bubbles to start joining together, and then they get to a certain size, and then they get too big, and then they sort of rise. Now, when I first put it in, some of those bubbles are just like air that's sort of like trapped. The surface of the egg is actually quite rough. It might seem to be smooth, but if you're looking at it with like a pocket microscope or something, I'm sure it would actually be quite a rough surface. But now as I'm looking at it, this fur of bubbles is sort of growing, and now I'm starting to see lots of little bubbles starting to form. Now those bubbles are carbon dioxide. They're bubbles of carbon dioxide gas. And then after a little bit, I think those bubbles can even they start lifting up the egg. And so the bubbles are attached to the egg, and the bubbles are less dense than air, and then together the egg and the bubbles together become less dense. Oh, sorry, I should say the bubbles are less dense than the water, not less dense than the air, because carbon dioxide is actually a fairly heavy gas and is actually more dense than air. But carbon dioxide is far less dense than the water. Now, the vinegar, the reason it's an acid, you might remember the formula, CH3COOH, CH3COOH. That H at the end is quite special because that H is a hydrogen ion, and it's actually the hydrogen ions which make the substances acidic. So if you think hydrochloric acid, HCl, there's a hydrogen ion there. Sulfuric acid, H2SO4, there's 2 hydrogen ions there. Phosphoric acid, H3PO4. Now citric acid, that's a lot longer, and I can't quite remember the formula. C6H8O7, and anyway, I can't quite remember. Sorry. But there's lots of bubbles forming now. Now, of course, you can do this with a normal egg in a bigger bowl of vinegar. Now, I've got another glass here just with some water in it, and I'm going to put the citric acid in, and as I put the citric acid in, it starts to dissolve. And the molecules of citric acid will release hydrogen ions. And so we're going to have a greater proportion of hydrogen ions. Now, remember when we talk about measuring the pH? That H stands for hydrogen ions. It's to do with the concentration of hydrogen ions in the liquid, in the water. the greater the concentration of hydrogen ions, the more acidic the substance is. So there we go, learning something new every day. Let's pop an egg in here, and we can slowly see the same sort of thing forming. Now, this will take hours. To see the full extent of this, we actually have to leave it overnight. Now, the eggshell is made out of calcium carbonate. Calcium carbonate. And you might have heard that calcium is good for your bones. You know, it's the calcium ions are the hard part of your bones. The inside of your bones is softer, which makes your bones absolutely wonderful, because our bones, if they were just purely hard, they'd be like brittle, like glass. Imagine bones made out of glass. You know, they'd be hard, they'd be strong, but if you whack them, they'd shatter. The softer stuff in the middle actually provides some flexibility, which makes our bones absolutely wonderful, because that means they can actually have a little bit of flexibility, still be hard, but they won't shatter as easily. And so they can actually absorb a lot of the forces without breaking. Now, of course, if the force is too large and in the wrong spot, you can definitely break your arm or your leg, and I'm sure some of you have broken your arms before. But the calcium carbonate reacts with the hydrogen ions, or I should say that the hydrogen ions react with the calcium carbonate to produce water, carbon dioxide gas, and calcium ions, and those calcium ions within the solution are like a salt, yeah? So we've got calcium ions being released, and that actually degrades the eggshell, so that the acid is eating away the eggshell. Now, if you've ever seen a cooking show, they come out and say, here's some I prepared earlier. Well, the good news is I can say the same thing, because last night I got this ready. And so here are some I produced earlier. And if I give them a little bit of a swirl, you'll actually see the outer layer, okay, the outer layer of the eggs coming off first. And then over time, you'll actually remove the entire shell. And so let me scoop this one out. This is the one in vinegar, actually. And it is well worth the effort doing this, because we end up with this, whoop, look at this, woo, bouncy, bouncy, rubbery eggs, you know? Look at that. And it's a little bit spongy, so I could actually like just give it a bit of a rinse like this. I'm wondering, you buy boiled eggs peeled in cans. I'm wondering whether they boil the eggs and then they like put them in vinegar and let the vinegar actually peel them. That might, rather than, you know, sitting around peeling a million of these tiny little eggs. But there it is there, it's a rubbery egg. And years ago, like, maybe 8 years ago, you know, I was doing this YouTube channel, Make Science Fun. And I did a lot of stop-go motion with Lego. And I did this one episode, it was called like The Hunt for Dinosaur Eggs or something like this. Anyway, these Lego explorers, they found these eggs and they wanted to get inside of them, so they actually put acid on them and then they ate it away. And it's really quite a good, fun little video. And yeah, anyway, I'll talk a bit more about it after, and some things that I did too. All right, so what are we going to do with this rubbery egg? Well, we could just look at it, but I've got a bit of an idea. So let me talk about my idea. So, you know that, so Tiny Science Lab, we buy a whole lot of components, and we make some components, and we make the infills, and we make these chemistry sets. Well, when I buy components, one of the components I buy is a 10mm measuring conical flasks. And I think these are handmade. I think these are handmade. They're not, I don't think they're made. The reason I think that is because often there's quite a big variation in the size of the opening. And one of the problems is, well, this one's not too bad actually, but sometimes the opening's so large that you can't actually put a rubber stopper in there. And so I can't sell these, we can't sell these in the chemistry sets. And so we actually make a different product called the Kaboom kit, which you can, it doesn't matter if this is a bit wider. But, I don't think this is going to work. I think even that's the opening's too small. But I'm going to give it a go. I think this could be a bit messy, but I'm going to give it a crack. I'm going to try and get, this is stupid, I'm going to try and get the egg into this conical flask, which I'm looking at it now thinking that's just absolutely impossible. And I'm not trying to be funny here and, you know, like pretend or anything like that. I'm actually thinking that that's impossible, but I'm going to give it a go anyway. Okay, so I'm going to light the Bunsen burner. Like that. And I need a little bit of water. Not too much. And I'll pop that here. And what we can say is that that conical flask contains some water and air. Then I'm going to blast it up a little bit. It contains water and air. I actually want to get this water boiling. Okay, so I want this water to boil and the water will turn into steam. The steam molecules will start filling up the conical flask. Okay, so the steam molecules will fill up the conical flask, and as they're filling it up, they're going to sort of push out and carry out the air that's in there. Okay, so that's fairly important. Now, what else is fairly important is that this egg, if I'm going to have any chance at all, has to have it. It's got to be nice and clean, nice and slippery, and sort of wet. All right, so we can see the boiling happening here. Also probably need this to happen quite quickly. That's another thing as well. It's actually got to go quite quick. So I'm going to, that's what I'm going to do. I'm going to, okay, I'm thinking what I've got to plan this out a little bit. All right. Planning in my head. Okay, yeah, good. I think I know what I'm doing now. See that? I'm getting some pretty bad bumping happening there, but it's full of steam. I've got my water. I don't want that beaker there. All right, this is going to happen fairly quickly, if anything's going to happen at all. I'm going to pop that down there now. Pop that there, and squirt water on there like that. Whoa! Did you see? There we go. I got some egg in. Oh, let's have a look at that in slow motion. Oh, I really don't like egg. But look, there's the... There's the membrane. Look. It's like a little... I could actually put some water in there now. Woo! Maybe not. That's quite disgusting, isn't it? That membrane is actually thicker. Amazing. Eggs are absolutely amazing, I think. Also, eggs are absolutely disgusting, and they can make a big mess. Now, you'll know if you're allergic to eggs or not, and if you are allergic to eggs, I don't suggest that you do any of these activities. So, some people can be very allergic to eggs. So, it used to be a really good prac that I used to do where, as a physics teacher, where the kids had to make a contraption out of straws and paper and balloons and stuff, and then drop them from a couple of meters high. And, you know, if you built the contraption well, then the egg survived. Okay, so that hole was not big enough. Maybe I needed to boil the egg. But anyway, I used to love the egg in the bottle trick when I was a kid, because it wasn't just a trick, it was a science demonstration, and I used to love science demonstrations. As you can tell, I'm not just a Johnny-come-lately. I've grown up loving doing science experiments my whole life. All right, now, can eggs go boom? That's $1 million question. Can eggs go boom? Let's find out. Probably not, but we'll have fun trying, that's for sure. All right, so what I've got here is a little needle. Okay, I've got a needle from a sewing kit, and I need one of my quail eggs. Okay, and this is going to be disgusting, absolutely disgusting, because I need to get this needle. I can take this off now. I need to try and poke, okay, the top of the egg. So I'm going to. I was able to penetrate the eggshell with this needle, and I'm going to try and put a few holes in around the place. So around we go, around we go. Okay, yeah, that was actually easier than I thought. Then I'm going to put the needle in and go around and around it like I'm stirring it. Well, what I'm trying to do is I'm trying to break the membrane, and I'm also trying to break the membrane around the yolk as well. Okay, poking, poking, poking. That was actually a lot easier than I thought. Around we go. And then, make sure you wash the eggs first. This is disgusting. You got to blow, don't suck it. Blow the egg. Oh! I got the giant bowl here, and then You're kidding me. Oh, disgusting. Bah! You know where eggs come from, don't you? I mean, we know they come from quails, but you ever seen a chicken lay an egg? Oh dear, the things I do for you guys, unbelievable. And you think I'd be able to get it into the mortar? No, giant miss. Okay. You're probably there killing yourself, aren't you? Oh, okay, so I've got this egg, and it's empty. Now, it's probably best if you were to put this in the sun for the day to dry out the insides. But I don't have one I've prepared earlier. Okay, I don't have one I've prepared earlier, so I am going to use this one. And okay, so what I'm going to do is I need to see if I can get that tube in there. There we go. I can get that tube in there like that. That's good. Then a conical flask, and I'd like to get some citric acid in here. Best if I put it on a filter paper like I've done in the past. If I get it nice and concentrated like this. Excellent. And I want this reaction to go almost as fast as I can get it going, which means, of course, we need to have it at a reasonable temperature. So let's, and with this is actually fairly important to have quite a lot of liquid in here for safety. Okay, and I'll explain that later on. But let's just get this citric acid dissolving fairly quickly, and also we want to raise the temperature a bit so that it's not too cold, because I'd like the reaction to proceed fairly fast. Wow, I can actually see a convection stream forming there quite quickly too, which is good. I don't want it super hot, okay, but I want it to about 40-50 degrees, something like that. This process will dissolve the... Okay. Nice. And I can give it a little bit of a stir, and I can see the citric acids dissolve. Top it up with some water here, and then I need some of my magnesium ribbon, and you can use, if you've got any smaller, older pieces, right, that you've used in some other experiments, you can use those. Let's pop him down. Okay, and it's bubbling away straight away. And if I push that on, like that first, I get that as the gas is produced, it pushes the liquid up. And so I've actually starting with some liquid, but now here comes the hydrogen gas. Now you can't see that hydrogen gas, but one of the beauties is that we actually don't have much hydrogen gas down there. That's very, very important. By having a full beaker, we actually don't have too much hydrogen gas. And that's fairly important for this, because now I sort of want to rest the egg there without it going down. I'm putting my finger on the top. So what's happening now, I've got my finger on the top hole. This egg is definitely filling up with hydrogen gas, 100%. And the hydrogen gas is actually pushing the air out. So at the moment this egg is filled with gas. I would prefer it, I know what I'm going to do. I'm going to put this peg there. And see that little bit of glass there? That way the egg doesn't slide down. There we go. Okay, I'm happy with that. I'm going to put my goggles on. Now I don't actually want the egg to go boom. Woo! 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 How cool was that? Egg go boom. Oh yeah! Oh wow! That was fairly mild. Okay? Now egg did go boom. Yay! And you know, it was a very small explosion. Okay, it was a very small explosion. And the reason that it was a small explosion is that to really get a big explosion, you need hydrogen and oxygen in the correct ratio. Now, the thing is, we only had like pure hydrogen and only a little bit of oxygen. So, because there wasn't the right amount of oxygen, it wasn't like a huge boom, but it was a satisfactory. Well, I thought it was a very, very satisfactory little boom, that's for sure. So I'll put my finger here. Now I might have some people saying that that was so dangerous. But there's some big things that we've done to keep it safe, and that is that we've actually filled up the conical flask with the liquid, and so that there's a very small amount of hydrogen gas in that conical flask. Also, it's got a rubber stopper on it. It's not like it's got a screw-on lid, so the rubber stopper can actually come out. It's also very, very thick glass. Okay, it's also very, very thick glass, and so unlikely to break. So there are numerous things that have been done, or that I've ensured, to make sure that this is safe. Stand back, glasses on. Oh, that one was much safer. Oh, sorry, not much happened at all there. I think maybe the hole's too big now or something like that. Maybe I have to trap that gas. Maybe I just got super lucky that first time, you know. I mean, that's always a possibility as well. Just got super lucky and I shouldn't even tried it again, you know. Beginner's luck, quit while you're ahead, and all the rest of it. Okay, well, that's it for the quail egg lesson. Hopefully you've enjoyed it. And make sure you stay safe when you're doing science. Keep your glasses on. If you're doing hydrogen gas, make sure that you're only producing very, very small amounts. All right, I'll look forward to seeing you again soon. Bye for now. Hey, time for some acid base color fun. All right, I'm excited. Let's make up some indicator solutions. So we'll make up a cabbage indicator solution first. And so just grab some red cabbage out and finely slice the red cabbage. Best if you do it onto a plate, of course, but this will do. Okay, that's heaps. And let's boil him up. If you keep this stuff covered with some cling wrap in the fridge, literally lasts for months. And you might have to cut off like a bit of a spongy outer layer or something like that, but that's okay. All right, so if we get some water in there. Now, for this lesson, you really do need to wash out your glassware well, okay? So if you haven't cleaned out your glassware for a little bit, now's a great time to give it a clean. And terrific. Pop that on. Just pop some glasses on. And that won't take too long. So for this lesson, need some bicarb, some citric acid, some vinegar would be good. Yeah, just some of the basics, the universal indicator paper as well. Speaking of which, I might get some of that starting to go as well. So I'm going to get a second beaker while that one's boiling. Just grab 1, 2, 3, a couple of pieces of paper. Roll that up in a ball. Roll him up. Pop him in. And perfect. And we'll boil that up as well in a tick. Let's just give this a bit of a blast. Look at that. Nice. I love the orange from the glow of the heat-proof mat. I love the sound of the Bunsen burner. I love it all. Let's give that a little bit of a poke as the dyes dissolve into the water. Good. That can just sit there for a little bit. Well, that's a real jet engine, that one. Let's turn that down. We don't need it. That's a bit dangerous, so let's turn that down. That's a bit safer. Nice. And let's heat this one up. This one, the action's already happening. Doesn't actually need a lot of heat. You can see the green coming out. I think that's great. Perfect. It's already done it. Happy with that. Plenty of dye and universal indicator in there. One last blast. Perfect. Okay, so I've got my two indicator solutions. I'll just pop them there. And if you grab an ice cube tray, like so, then if we get a test tube, let's try and put, now the worksheet says sodium carbonate decahydrate. Now let me talk about that first. For the first, I think, 700 or so chemistry sets that we sent out, well, they all had 6 chemicals in them. One was sand, iron powder and sodium chloride for a separation experiment for the Year 7 course. One's got a small amount of black copper oxide, magnesium ribbon, copper sulphate, black manganese dioxide, which is going to be used in the Year 10 course for producing oxygen. And in the first 700 sets, it came with sodium carbonate decahydrate. Now, that's a basic substance, quite basic. The common name is washing soda. You can actually still buy it as washing soda. There's these white crystals. You can get them like from, I think, Woolworths. You can get them online. I think it's Beck's washing soda or something like that. In the olden days, they used to use that as the like a detergent for washing clothes. But now we use more modern combinations of detergents and enzymes and surface active agents called surfactants that help the clothes get washed. The problem with the sodium carbonate decahydrate was there was a few little problems, and one is that it on some trips it acquiesced and it liquefied, and then some of the liquid came out of the bottles and then it solidified, and so it was producing like crystals in that area, and so it's not a great look. Also, it's very similar chemically to sodium carbonate, and so we sort of really only wanted to send out the really difficult chemicals to get. So why send out sodium carbonate decahydrate when basically sodium bicarbonate will do the job? So since then, the chemistry sets have been, instead of the sodium carbonate decahydrate, they've been getting sodium thiosulphate, which isn't without its issues either, but it's also a relatively difficult chemical to get, and it's going to be used later on in this course, and probably a course down. We've already used this in this course actually, and so it is actually a very good chemical for us, and so that's what we send out now. So if you've got the sodium carbonate decahydrate, you can put a little bit in this test tube, but if you don't, because you've got the sodium thiosulphate, then you can actually use a bit of bicarb soda for this. All right, so I'm going to put a bit of bicarb soda in this watch glass, and what I'm going to do is try and get some into this test tube. So I'll put it onto a piece of paper as a funnel, and I'll try and send it down to the bottom. Oop, there we go. Good. Excellent. Then using a pipette, now make sure the pipette is clean. That's another thing. When you're washing your equipment, make sure you wash your pipette out as well, because I might have sucked up some citric acid or some vinegar or something like that. So I suck up the liquid, squirt it out, suck up the liquid, squirt it out, and I'm pretty confident that's clean now. And I'm going to add some red cabbage juice. So, and I just want to dribble it down the side. Dribble it down the side like this. Now I'm not too sure why I got bubbles straight away. Why did I get bubbles? That's a good question. Some reaction happened. I'm not too sure why it happened. And then let's fill this up gently. And then I'm going to put some vinegar in it. Put a bit of vinegar in the beaker. And just going to release it gently on the side here like this. Just gentle. And then I'm just going to leave that nice and quiet. So that's my first setup. That's my first setup. What about my second setup? We'll leave that. I'm going to put the sodium carbonate decahydrate in again, or the baking soda, if that's what you've got. Let's pop that there. Let's get some baking soda, and I might actually put a bit more in actually. The thing with the sodium carbonate decahydrate is that the crystals are quite large, which is good, because that means it takes them a fair while to dissolve, whereas this bicarbonate, the powder, because of the surface area, it will react quite quickly. And I don't necessarily this time want the reaction to go quite quickly. So, yeah, things to consider. And I'm just cleaning my equipment here. All right, I'm going to put in the cabbage juice. Now you can see I must have used a lot more, and I'm going to go around and try and clean this cabbage juice. Now these were relatively similar, but obviously I've used a lot more bicarb with this one, but that's okay. I mean, this is acid-based colour fun, right? And I am actually using a lot more. I'm bringing it all the way to the top this time. And now, I'm going to get some citric acid. Just sprinkle some citric acid on the top. Whoa! Wow! It's amazing! That was beautiful. Now, we'll leave that over time, all right? We'll leave that over time and watch the colour transitions, yeah? It's really quite beautiful, isn't it? This, you can see, I'll pull it out so you can see it even better, but yeah, this is going to take a bit of time to happen. I might even put a bit more citric acid in. And I'm talking about leave this for overnight. There we go. Leave it overnight and see what happens. Sprinkling in the citric acid. Okay, cool. Love it. What about if we do something similar with the universal indicator? So in each one, Now I sort of want to do a bit of a fresh start, so I might even just like hide the back ones so that we can actually just see the... Does that make sense? Otherwise it gets all a bit colourful, so I'll fix that in a tick. What do we need? Some bicarb in each one. So, bicarb there. I'll just straighten that one up, straighten them up a little bit. Bit of bicarb in that one. In we go. And let's get some of the universal indicator solution into here. Notice I'm dribbling it down the edge. I'm trying to just sort of add it gently. That one I'm going to add some vinegar to. And this one I'm going to add some citric acid to. So I can fill it up a bit more. There we go. So I've tipped that one out and get some vinegar. Gently, 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 gently. Let's leave that one over time. And then let's put a bit of citric acid in this other one. Woo! Wow! How nice is that? That one, I've got a fairly quick... If I pop that there, you can sort of see what I'm talking about. Look at that. Hey? And we'll leave that for a long time, like overnight. See what happens. There's the first bit of acid-based colour fun, and we can put that to the side to do its thing. Now I'm going to actually need for the next one a bit more cabbage colour. Okay, so a bit more cabbage colour, and so let me just slice up a bit more cabbage. Probably don't even want it too strong, to be honest. So I've cut it way too much. Get a bit of water happening in there. Light him up. Pop him there. Let's clean up my mess as we proceed. Always good to try and work neatly. Set of good examples. Put some eye protection on, and I just need my stirring rod. Let's blast them up a bit. Nice. That's almost good enough. I think that looks good. Probably just get it boiling. Yep, happy with that. Okay, now we need some more beakers. Now it's quite important that these beakers are clean. Yep, so pop that beaker there. Pop that beaker there. Empty beakers. And in the first beaker, I'm going to put a sprinkle of citric acid. Not much, just a sprinkle. And I'm going to add a drop or two of water and give it a swish. Okay, so we're going to call this activity Magical Beakers. Now, when you show people, you can say, look, I've got an empty beaker, even though there's a drop or two in there. And then in the other one, we're going to put, actually have to put, make sure you put like more sodium bicarbonate than you did more. I'd have to do the mathematics on this one to take that back what I just said. I need to dissolve this. Maybe I might do this one first. Which one should I do first? Yeah, I actually think I only need a little bit of this. So I'm going to actually pour out, once I've dissolved most of this bicarb. Okay, wiggle, 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 wiggle. I think I'm going to pour out most of it. In actual fact, what I could do is just pour off the liquid part, the part that's dissolved. I'm washing this conical flask. So this is what I'm going to do. I'm going to pour the liquid component off because there's some undissolved stuff in there. I want to get rid of that. So I get rid of the undissolved bicarb. Very good. And just now put in the part that's liquefied. That way you can say, look, I've got 2 empty beakers, although that one's got a little bit too much, but that's okay. And here, I'm just going to decant. Oh no, what did I do that for? I used the same, stupid me. You know how I'm saying wash out your beakers, and then I just used the same conical flask that I did the baking soda in. What a muppet. What a muppet. Hopefully this one's clean. Yay, there we go. Tip out that. Oh, tip out that. I don't even want to put my fingers in these because I know that my fingers have got like citric acid and bicarb on them and that sort of stuff. All right, now let's just top him up. We need to eat the first one quite full. All right, so now we're ready, we're set. We're saying, are you ready for a magic trick? Yes, yes, ready for a magic trick. And so I've got a purple beaker here and I pour in, oh! Pour in like 2/3 of that. Look at that. And then I take this one and I pour in 2/3 of that. Look at that. Isn't that wonderful? And then you can actually start doing woo! And then put it back and go, yay! Almost back to where we were at the beginning. Well, you can do all sorts of versions of that and have lots of fun. You know, you've got conical flasks, you've got test tubes, so you can knock yourselves out. Having fun, don't knock yourselves out, but you know what I mean. Have a lot of fun, impressing people, and you could even do that with the universal indicator and maybe go for a range of colours. Maybe you're lucky enough to have even more than 3 beakers. Who knows, you might have multiple sets, I don't know. But anyway, that's it for this lesson, and I look forward to seeing you again soon, another time. Bye for now. Stay safe. Bye-bye. Hey everyone, Welcome to another chemistry lesson, and today we're going to be doing a little bit of an experiment on some medication called antacids. Now, when I was a kid and used to visit my grandparents, I'd often see packets of quickies, like in the lounge room or the kitchen, stuff like that. And my grandfather used to take these. Now, these are usually antacids taken by older men, usually maybe a little bit overweight, because what happens is, you know, they have a big meal, food goes down the esophagus into the stomach. So the stomach contains hydrochloric acid, which helps break down the proteins, helps digest them, and what happens is that those stomach acids can get pushed up the esophagus, causing a burning sensation. And because it's sort of like it feels near the heart, it's often called heartburn, although it's not your heart burning. And so I think pregnant women also can suffer from heartburn because of the baby, the size of the baby pushing on the stomach and that sort of stuff. So pregnant women also take it. You can get them in tablet form, which is actually the cheapest. Liquid form is a little bit more expensive. My daughter, Mickey, she works at a pharmacy, and so she gets a good discount. And so she was able to buy these for us, for me, for fairly cheaply. But I don't think I've actually ever, like, tasted one of these medications before. So Quickies, it's been around for a long time. It's made by Nestle. I think that's a Swiss company that's like makes Milo. Quickies. That's sweet. Can crunch it up. Tastes a bit like a lolly. Quite sweet, actually. A little bit of minty spearmint taste. Rennie. Rennie is made by Bayer, a massive German company. Oh, looks a little bit fancier. The ingredients, the active ingredients. This is very important. Calcium carbonate. Calcium carbonate. Remember one stage we made some magnesium oxide. Sodium bicarbonate, yeah? It's a base. Remember what bases do? They neutralize acids. Calcium carbonate, magnesium carbonate, and magnesium trisilicate. That's Quickies. Rennie, a little bit fancier here. And square tablet. Oh, very spearminty. The texture is not nearly as nice. The Quickies was actually almost like a lolly. Now, you're allowed to eat like 20 of these a day or something like these, so it's okay if I have one or two. What's its active ingredients? Calcium carbonate, magnesium carbonate, hydrate. So very similar active ingredients. What about Mylanta to go? Mylanta to go. Aluminium hydroxide. So not the carbonate, and magnesium hydroxide. So different. These two are quite similar in terms of their active ingredients. The Mylanta's got hydroxides as opposed to carbonates, and hydroxides are definitely bases. Foil pack. And I should actually have a drink of water between each one. Round tablet, very smooth. Ooh. Sweet. Crunch it up. Powdery. Milky. You know what? Quickies was definitely my favourite. Quickies definitely my favourite. So you can do an entire student research project. Like, to do this properly, this could take you hours to do a full proper investigation. Now, we don't have hours, and so I'm gonna maybe just sort of start off the experiment. And I've sort of made up a method in my head, thinking the method's going to work. I don't know whether it will work or not. We'll find out. But the aim of the experiment is to compare the effectiveness of these different antacids. And so it says measure out, the method I've got, measure out 1 gram of an antacid, such as Rennie. All right, so now why we say 1 gram is that, you might say, I'll just do a tablet of each, but the tablets are different masses. And so we should actually compare like with like. And so we should stick with like a known mass. So there's a tablet there. That my lantern, I just don't know about it, Don't sue me, please, don't sue me. 1.3 grams. I wonder how heavy a Quickies is. This will be interesting. Oh, 2.4. Well, okay, so what did I say? Rennie, I need 1.1 gram, I said. Now, what I could actually do is get out my mortar and pestle. And what about if I give it a crush it up? This is good. Crushes up very easily. Excellent, I like that. And I'm going to put my watch glass here, and I'll tear that. And what about if I get my spoon? I'm going to measure out 1 gram. Now, chemical reactions always happen faster when you powder stuff up. Gram. Put that towards the center. Okay, 1 gram. Very good. And let's put this, it says dissolve in 10 ml of water. So let's pop that there like that. And get 10 ml of water. Going to need the stirring rod. Oh, where's my stirring rod gone? I didn't put it back. Here it is. Always put your equipment back. It's actually not all that soluble. Huh! It's not that soluble. I'm surprised. It's not dissolving very well. Wow. I'm very, very surprised there. Ew. That's interesting. I might try and warm it up a bit, okay? Often when you heat things up, and because it's a little bit of an unknown, I'm going to pop on some glasses, And warm this up. Maybe that will help dissolve it a bit. Probably should use my tweezers to hold the beaker. Mixy, 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 mixy. Fantastic. Sort of gone like very... this is helping it dissolve. I don't want it too hot. That's good. Now I might add an extra step, you know. I might actually get a bit of the universal indicator paper going. So let's heat this one up. Quickly relight my Bunsen burner. And put in a couple of pieces of universal indicator paper. What do I normally use? 3 or 4 pieces. I like it. Pop him in. And give it a bit of a stir. That won't take long. Pop this here. It's good to try and keep yourself a bit neat and organised. I reckon that's about right. Won't take long to get the colours out of that. There we go, I can see the green solution. And you know what, I might even, oh, wrong way, might even get a little bit of a stronger colour, because I'm thinking, oh, that's interesting. Look, I'm looking at the beaker with the dissolved, what is it? What did I use? Rennie. It's not dissolved at all, right? Those substances are not very soluble. Calcium carbonate. And what was the other one? Calcium carbonate and magnesium carbonate. They're not particularly soluble substances. Now, if I pour in some of this, woo, wow! Look at that. Went blue because it's a base. It's a base. What's the next step that I put? Oh, I did actually add 1 ml of concentrated pH solution. Good stuff. So now it says measure out 5 grams of citric acid in a beaker. I don't actually think a beaker is the best way to go here. I actually think a watch glass is better. So I'm going to add 5 grams to this watch glass. Hurry up. Just tear it. And pop this in. Whoa. 5 grams is a lot. I'm going to change it to 2 grams. I'm sure 2 grams is adequate. I'm sure 2 grams is adequate. I added a bit too much there. Okay, I'm going to change that on the worksheet. So you'll see 2 grams now. You'll be wondering to yourself, where did Jacob get this 5 grams from? You remember I write the worksheets prior. Okay, so there's 2 grams there. Prior to filming, hoping for the best. Then, this container, it says, once cooled, transfer the solution to the 20 ml plastic container. Oh, change colour. You know what that means? It means there was a contamination. I can actually use a bit of excess water. Having extra water is not going to affect the outcome of this experiment. I've got to make sure I get all the Rennie out. Okay, and now I slowly add citric acid, the acid to the base, to the antacid, to see how much it will react with. So give it a stir. Houston. Uh-oh. Houston, we have a problem. No. No. Oh, thankfully it hasn't overflown. Alright, so now... no, I don't know what to do. Might try and trap some of this froth. This froth is going to be problematic. This froth is going to be problematic. But having said that, this froth is not random, you know. This froth is part of the medication. Right? It's obviously got what we call some surface active agents in there, some detergents that produce a froth. Because I think that froth, when it reacts in your stomach, causes like a buffer layer. That's what I actually think. Like the antacid isn't designed to neutralize all the stomach acids, because then you can't digest your food. I think it's designed to form this bubbly, frothy layer to like act as a barrier. Does that make sense? I think the reaction has come to completion. Yeah. There's hardly any more reaction going on. Okay. Alright. So now what I need to do is weigh how much citric acid I used. Yeah, because I started with 2 grams. What have I ended up with? Let's find out, because that will tell me how much I used. Oh, it's a bit of moisture on this watch glass. Don't know how, don't know where. Pop that there. Tear. Dip all that citric acid into here. Oh, 1.24 grams, so that means I used 1.25. I used 0.75 grams of citric acid, 0.75 grams of citric acid to neutralize 1 gram of Rennie. So how much citric acid? I used 0.75 grams. Okay, let's do this now with quickies, but I will bring this back up to 2 grams for the next experiment. There we go, I've got 2 grams of citric acid there, ready to go. So, goodbye Rennie, and tip this out now. Well, give it a bit of a rinse. I tell you what, the aftertaste of taking those 3 medication, my mouth feels grainy. My mouth feels grainy. Not what I'd say was a very pleasant experience, I must say. I didn't really enjoy that at all. I enjoyed the quickies. I don't have shares in Nestle, all right? Okay, I'm not trying to promote it. Just saying which one I enjoyed the most. Now I need 1 gram. So how about I put my quickies tablet in there, get my mortar and pestle. Oh, this one's a lot harder. Oh dear. Oh. Not happy. This tablet is hard as a rock. It was about 2 grams. What am I going to do? Okay, what was the mess? Oh, pair of pliers maybe. Like the tweezers won't do it. Don't break your tweezers, by the way. Oh! 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 Don't break it. No, don't use your tweezers because they'll break. They're not designed to break it like that. And these things are not designed for like lots. Ah! How am I going to break this tablet? Maybe I just have to dissolve it. So what was the mass of it? We have to overcome problems, my people. I thought it was going to be so easy. It's not easy. This is a 2.4 and I need 1 gram. What happens if I put it into some water? Will it dissolve? 10 mil. Does it do anything in the water? I don't know. Let's heat it up to find out. That will speed things up. Often heating things up speeds things up. Put your goggles on though. A vice. If you have a vice in your maybe in a workshop or something, or a pair of pliers, that will do it. You'll be able to break it up. This is sort of going to go bloop bloop, I think. So just be a bit careful. Oh, I can see it's lifting up and down, bloop 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 bloop. Sort of doing what I expected. Okay, are you going to dissolve faster with the heat? So remember, we need 1 gram, but that's a 2.4 gram tablet. And you're probably thinking to yourself, Jacob, how are you possibly going to get 1 gram now that you're like dissolving it? I have the solution. I haven't told you the solution yet, but I do have a solution. This is what we call chemistry. Bloop, 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 bloop. I feel like an industrial chemist here. Whoa! Whoa, 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 whoa! Slow down. Oh. Okay. Starting to froth up. Definitely sort of dissolving or breaking down. I think dissolving is the wrong word. Mixy, 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 mixy. So what I'm going to do, because I want 1 gram of it, I'll have to do a bit of a calculation to work this out. But it has to be evenly mixed. This is the important part. It has to be evenly mixed. Am I getting it all? Oh yeah, there's the tablet in there. There, it's getting smaller. Look at that. So when you digest food, your teeth are the first part of the process. And your tongue and the saliva turns the food into chyme that you swallow. Goes down to the stomach. And then there's enzymes and acids that break it all up. Have I got it all yet? Oh, still going. How heavy is that little piece? Now that I've started this though, I've got to dissolve it all. Not too much banging with your stirring rod or you'll go straight through the beaker and then you have to buy a new beaker. Beakers are pretty cheap. It's the postage that's not very good. I always feel bad when someone orders a beaker. Not because I charge a lot for the beakers, but because postage is like $9 or something like that, believe it or not. Yeah, $9. I'm not sure what year you're watching this, but typically in 2024, to send a tracked tracked, you know, where you can keep track of where it is in the postal system. It costs about $9 to send. Yep, someone pays for postage. Someone pays for postage. Okay, so what's the story here? I need to get 1 gram of the tablet, so a fraction of 1 over 2.4. This is what I need. 1 divided by 2.4, because there was 2.4. I need 0.416, or I need 42% of this. Okay, I need 42% of this mixture. That way I know. If I get 42% of this mixture by weight, that means I know I'll have 1 gram, as long as it's well stirred. So how heavy is it? Okay, got to do some smart stuff here. Get a beaker. Yeah, you're thinking, Jacob's got to do some smart stuff. Good luck. Don't be like that. That's not very nice. Let's pop that there. I'm going to tear it because I want to weigh how much this liquid I have. And I've got to get all the tablet. There we go. That actually dissolved it. So I got 10.47 grams. And I need 42% of that. So 42 divided by 100 of 10.47 equals, I need 4.4 grams. So now I put that back, tear it. What do I need? 4.7 grams. Now, I've got to make sure it's a well mixed mixture, so that's fairly homogeneous. 4.7 grams. That was too much. I've got 5.2 there. A little bit more. Oh, stupid. Boop. Close enough, 4.8. Okay, good. There we go. Effectively, that's 1 gram of quickies. Okay, that's 1 gram of quickies. I'll just clean my scales up. And if I add this, this will go. Now, adding a bit of water is not going to affect anything. Yeah, and it goes blue. No surprises there. Tip that in. My 1 gram of quickies. And now I'm going to add some citric acid. This is 2 grams of citric acid. Put some in to start the party. And I'm getting the bubbles. Bubble, 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 bubble. Mixy, 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 mixy. I'm getting that raft again. See the bubble raft? You know what the gas bubbles are? Carbon dioxide, of course. So a bit more. Mixy, 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 mixy. How do I know when it's finished reacting? Well, I can hear the bubbles forming, so that means it's still reacting, yeah? So I keep stirring. I can still hear it. The reason we're doing it in this plastic container is it is a lot bigger. How are you going? You having fun? You doing the experiment too? Probably got me in the background. Still reacting. Okay. I think that might be it, you know. I added a bit more and I can't hear. I'll just add the tiniest bit more, just to see if there's any more reaction. There seems to be. This is not a straightforward practical. Okay, it's not an easy practical. It's not an easy investigation. I'm hoping it's relatively valid, although I've got my doubts about the completion of the reaction and that sort of stuff. So, how much of the citric acid did I use? Well, I started with 2 grams. Tear that. And I've ended up with, tip that out, 0. So, it actually used 1.25 grams. So, what that tells me, so quickies, 1.25 grams. So in actual fact, the gram of quickies actually neutralised almost like 50% more acid than Rennie did. It didn't quite form the same raft though. Like the Rennie made this big raft. This one doesn't have. Well, I have been stirring it up a fair bit, so that's not that good either. Whew. This is very interesting. How many? I need 2 grams of this. And I tell you, my mouth from the aftertaste of having those 3 tablets, not good. I'd probably prefer heartburn. I've never had heartburn. So maybe, it's obviously a thing because, you know, these things are, you see them for sale everywhere at the supermarkets and stuff like that. My Lanta, we need, how much? 1 gram. 1 gram. You better crush up. I'm not going to be happy. If you don't crush up, don't you be like a quickies. Oh! Yay. What a relief. Now this is remember, totally different chemicals. Totally different chemicals. I can smell the... Got to look after my scales a bit better. Let's put the scale there, press tear. What do I need? 1 gram. Can't remember what the initial weight was. I don't think I actually measured the tap, 0.95, 97. 1.00! What a champ. And I wonder if these chemicals are a little bit more soluble. So what were the active ingredients again? It was like aluminium hydroxide and magnesium hydroxide. Now, interestingly, when I was growing up, the magnesium got a little bit of a bad rap. Scientists at I was reading articles about aluminium could cause reactions in people's bodies, and so they were recommending that you didn't use aluminium based deodorants or cook in aluminium food. So, but I'm assuming the company that's made my Lanta has done its research and can guarantee us that the antacid is not going to cause issue. Now, yet again, this is not particularly soluble stuff. Alright? So, it's just not very soluble, which is I think a big part of the reason why I'm getting this aftertaste, because I've got like the stuff stuck in my mouth. So the chemicals which are safe to neutralise your stomach acid, just not particularly soluble, which a bit of a pain in the neck, isn't it? Be nicer, I think it'd be nicer if they were soluble, but maybe it's best if they're not soluble. I just don't know enough about this. Okay, that's the problem. I don't know enough. At least I don't have to do fancy, it was easy to get the 1 gram, so that's good. And I know heating up the liquid does improve the solubility, so that's a good thing. By a little bit. I don't want to get it too hot. I actually don't think that's made a big difference at all, to be honest. What colour do you think? What? What? Stays green? Oh, this is... Whoa! Obviously a few contaminants in the in that container. Oh, hopefully there's... I think there might be a bit of undissolved citric acid. Okay, in goes the citric acid. Let's give it a stir. And see what happens. I don't hear anything. What are you doing, my Lanta? I can't hear any bubbles. I can't really see any. What? Is there anything in? Have I got a bad batch here? I can't see any change. Are we being sold a dud with my Lanta? I don't think it's doing anything. Have I just discovered some big conspiracy? My Lanta to go. Fast relief. Doesn't do anything. No, I can't say that. Don't sue me. Obviously, I'm too ignorant. And I don't understand the mechanism. But I would have thought, oh, hang on. This is hydroxide. Ah. Okay. All right. Sorry, I apologise to the company behind my Lanta. Because this is a hydroxide and not a carbonate, I'm not expecting the bubbles. Yeah, magnesium hydroxide and a citric acid, that's just going to produce, hydroxide is OH. So I think I'm only just going to be producing a water, not carbon dioxide. So salt and water. But having said that, I would expect the colour to go green with the neutralisation, and it hasn't gone green. So I just haven't seen any neutralisation happening. This is very interesting stuff, isn't it? This is one reason why we're doing a chemistry course, so that we can grow in our understanding and knowledge. Give that a mix. It's very green, which is the neutral colour. And a little bit of citric acid. Goes yellow. So what would I take? Personally, what would I take after doing this investigation? Although I preferred the flavour of the quickies, the Rennie produced that big fat raft of foam, and I think personally, I would take Rennie. Now you can actually do sodium bicarbonate as well, you know, if you wanted to. Like, what happens if you don't? Now, sodium bicarbonate, that will react with your stomach acids, produce carbon dioxide gas and a salt, but it probably won't produce the raft, because you need the bubbles, and so you actually need some other ingredients like detergents to form these bubbles and to hold the bubbles. So basically, you probably just keep drinking sodium bicarbonate until all of your stomach acid is neutralised, and then you can't digest your food. So I do not recommend that. Okay, I do not recommend that. But let's have a look at the graph that we might do for these results. My Lanta, I'm just going to put question mark. Just don't know what happened there. No reaction. No observable reaction. And the sodium bicarbonate didn't do because we've run out of time. I can't have this video going forever, otherwise the course is just ridiculous. So the antacid, we'll do, what did we do first? We did Rennie first. And then quickies over here. And the amount of citric acid neutralized. And we can go 0.5, 0.1, not 0.1, just 1, and 1.5. So Rennie did 0.75, which was here. Now you'll notice that this is going to be a bar or a column graph or table, antacid. So Rennie did that much, 0.75 grams, and quickies did 1.25, which was, ooh, I have to put that 1.5 here, people. Quickies did that. Zoop. Use a ruler. So, if you're just looking at this, quickies per gram seems to neutralise more of the citric acid, so you might say that it's better, and it does taste better, but the Rennie produced a bigger, thicker raft. So, in that regards, that's why I'd probably go for the Rennie. There we go. Interesting, and a lot in it, and I've only just touched the surface. This could be a huge investigation. So, anyway, that's it for this lesson. Hopefully you've enjoyed the analytical and the practical chemistry, and I look forward to seeing you again soon. Bye for now. Okay, so we are going to do a quantitative experiment to investigate the how the rate of a chemical reaction is affected by concentration. Now, the two chemicals that we're going to use are citric acid and sodium thiosulphate. Okay, they're the two chemicals, citric acid and sodium thiosulphate. And basically, when we make a solution of the two, okay, so a solution of sodium thiosulphate, if it's not too concentrated, then it's clear and colourless. And the citric acid solution is clear and colourless. But when you add them together, there's a chemical reaction, and it's generally a fairly slow chemical reaction that produces sulfur, and the sulfur is not soluble, and so it produces a cloudy mixture. And you can actually use that cloudy mixture to determine like when an endpoint, I guess, of your reaction. So a time. Does that make sense? I hope so. All right, and I will need a stopwatch, so I'll have a stopwatch as well. So, all right, first things first, we need to dissolve 0.25 grams of sodium thiosulphate in 10 ml of water. So, I'll get out my trusty scales, turn them on, wait for it to go to 000, put on my watch glass, press tare, now I've got it as 000, and I need 0.25 grams of this sodium thiosulphate. So some of these crystal sizes are quite large, which could actually end up being a little bit of a problem, because that's 0.09 grams, that's almost like 0.1 gram. Whoa, oh, that was a large crystal. I'm up to 0.21. So really I just need a very small, oh, that would have gone way over. So I might use my tweezers to pull out that crystal and see what happens there. I'm almost selecting, that's 0.23. I wonder what happens if I can break a crystal, whoop, and add that there. Oh, that's pretty close to 0.25 actually. See how I'm just breaking a crystal up just to get the exact, oh, 0.26. I'll take a tiny bit off that crystal. Whoop, bang, bang, bang. If I can break him in half, I'm laughing. I wonder if I can break it with my finger. Yes! Pop him on. 0.21. Yes, 0.25. Okay, fantastic. Now, I need to dissolve him in 10 ml of water, and if I use the measurement on the beaker, that's okay. That's okay, as long as I'm always using that as my 10 ml. So there we go, 10 ml, and put that sodium thiosulphate in. In you go, in you go. Oh, I should warn you that it's very important that the equipment is well washed in this experiment, because if there's any lingering chemicals, you're going to, particularly if there's citric acid, then the reaction will occur. Basically an unwanted reaction will occur. So here we go, we're going to set about dissolving that. Now they're fairly large crystals, and so they'll actually take some time to dissolve. So I'll just pop him there and wait, and then move on to the next instruction. I now need 0.25 grams of citric acid. 0.25 grams of citric acid. So I'll just give my watch glass and give this a weigh. Pop him on. Tare. This will be a bit easier to get 0.25 grams because the crystal size is much, much smaller. So I'm not going to have the same issues. .25, and I'll need a beaker. And tip him in. Good. Okay, so we need 10 ml of water. Very good. And I'm going to rinse my stirring rod, to dissolve this. Mixy, 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 mixy. Good. There's my citric acid. Ah, very good. And the crystals of sodium thiosulphate have virtually disappeared. So just rinse my stirring rod to rinse off the... Make sure I'm rinsing off all the citric acid. Just got to give this one a stir. Sodium thiosulphate. Yep, those crystals are dissolved, which is great. So I've got my two reactant solutions. Give them a rinse so I don't forget later on. And what we need to do is add 2 ml. And I can use the pipette. Okay, I can use this transfer pipette. I'll just give it a clean. All right, that's a good clean, that's good. And I'll need 2 ml, I need my stirring rod. Okay. And I need to put my logo, because this is going to go over the logo. Put this logo here. Sodium thiosulphate over there like that. And I'm going to get 2 ml of citric acid. Perfect. I have to get my stopwatch ready. Okay. Stirring rod. Oh, this is where you need someone else to help. Squirt that in, all of it. Press start. Give this two stirs. 1, 2. And now we time how long it takes for the logo to disappear. All right. So you might be thinking, what's happening here? Nothing is happening. Well, let's just wait. Hopefully this was the citric acid and that was the sodium thiosulphate. Sometimes it's probably good to label things. Yeah. You might be thinking, nothing's happening. Nothing's happening. Let's find out. Oh, hello. Hello, hello, hello. It's slow. It is slow. But something is happening. Can you see it? I can see it for sure. I can still, it's harder to see it in the camera than it is with the, than with my eyes. So I'm going to use my eyes, to be honest. See how cloudy it's going? And there's a very, I can't smell it, but there will be a very faint smell of some type of sulfurous substance. Getting closer, very, very close. This is the hard part. Working out when to say stop. I'm going to call it now. 3 minutes. Okay. So, 3 minutes. That's 3 times 60. That's 180 seconds. All right. I might tip that out. And again, you've got to give things a good old wash. So I'm actually going to use the tap. Okay, so it's a good idea to use the tap. Nice and clean, and I'll dry them on the tablecloth. Not the beakers, just the watch glasses. I'll give it a bit of a dry. Now I've got it down here where we're supposed to do 1, 2, 3, 4, 5, 6 different trials with 6 different masses. So 6 times 0.25 is only 1.5 grams. So that's not a drama. But it will take a long time to do this for the video. So I'm just going to do 3. So the next one I'm going to do is 0.35 grams of citric acid. But I've got to keep the same amount. I've got to keep the same amount of sodium thiosulphate. Okay, so we're going to keep the same amount of thiosulphate. Let's pop that there, tear it, and attempt to get it. I'm just going to break up the crystals a bit. Make sure that's sitting in the center of the watch glass. Teared. I need 0.25. That's a big crystal. That crystal, ooh, so close, 0.21. I really need just to find a very small little crystal now. Oh, that's gone a little bit over. Not much though. Pop him back. I can just break that crystal. I think we'll be right. Crack the crystal. 0.25, yeah. I'm a pro. Pop him into the beaker. And I'm very happy that the dissolving process starts straight away. That makes me very happy. Pop the watch glass on. Now you should be doing 0.3 grams, but because I'm in video land, I'm going to do 0.35. Okay, so I'm going to skip the second one. I'm going to skip the 0.3 and go to 0.35. Perfect. Pop him in. He can go away. 10 ml of water. Very important that we give it a good stir to dissolve it. And so we also, we want to use the same amount of water. We want to make sure it's fully dissolved. Okay, citric acid, fully dissolved. Give it a wash, stirring water, rinse. Bring it over to the sodium thiosulphate. Okay, this one needs a bit of extra time, bit of extra love. I know why the last one dissolved so quickly. It didn't really. I actually had to, I think, go get the stopwatch from upstairs, and while I was doing that, that's why it was dissolving. So had a bit of video editing so that you weren't just sitting there watching the wall behind me while I was off doing something else. But during that time, this sodium thiosulphate had been dissolving. That's the key difference. Okay, And I'm going to put this over here. Put it over my, that's the sodium thiosulphate. Put that over the logo. I need the same amount, 2 ml. And squirt that in. Start the stopwatch. Give it a stir. And the reaction is proceeding. Now I'm not filming it from overhead this time because you saw what the story was. And so we'll now just wait. I'll do a bit of washing up while I wait. Okay, that's 30 seconds. Okay, I can see some cloudiness happening now, which is what I expect. Easily see the logo though. Just turn off my scales. Okay, yes, definitely see the sulfur. Interesting, if I've got my phone here, but I'm pretty sure that will scatter the light sideways. It's called the Tyndall effect. And the Tyndall effect is used to determine whether you've got a colloid, where the particles are so small that they actually scatter the light sideways. So I do think I've got a colloid there. I'll have to have a look over the top. Okay, no, we're still going. Okay, we're at 1:55. That's 2 minutes, so 120 seconds. Okay, I can still see just the logo. Now I'm expecting this to go faster. I am expecting this to go faster. So, but I don't want to cheat. I don't want to cheat, and so I shouldn't even look at the stopwatch because that will bias me. Ooh, but having said that, very shortly I won't be able to see that logo. Don't look at the stopwatch, Jacob. I looked. And stop. 2 minutes 49. Ooh, 120 plus 49 is 169 seconds. So it was a little bit faster. It was a little bit faster, but not much. Not as I thought it'd go actually faster than that. So I've got, for 0.35 grams, I've got 169 seconds. Okay. Well, I'm now going to skip to the final one of 0.5 gram of citric acid. So let's tip that out. And I'm going to go wash the equipment. All right, what do we need? 0.25 grams of sodium thiosulphate. How have you been going, getting your sodium thiosulphate? Been able to do it? Some of you might say, oh, crush it up in the mortar and pestle, but I don't know. There's something about this sodium thiosulphate that it liquefies quite quickly. So what am I after? 0.25 grams again. 0.25 grams. Well, that was a big chunk. 0.12. Oh, push that to the center. 0.19. I'm after a small crystal here, so I might. Oh, there, I can pick and choose. That one might do it. 0.26. Shh, good enough, good enough. Don't tell anybody. 0.26. I might add the tiniest bit of water extra, just so I've got the same concentration. Do you know what I mean? So, in you go. You can start dissolving, my friend. What did I say? A tiny, tiny bit more water so that the solution is the same concentration. Okay, so there's my sodium thiosulphate, and now I need my citric acid, and I'm going to use 0.5 gram this time. 0.5 grams. Tip, tip, tip. Went over the top. Pick some out. Pick some out. Hey, got it. There you go. Perfect. And let's get some. Using a lot of water. Going to get some more water. Okay. Let's dissolve that citric acid. Takes a little bit of effort. Wonderful. I can pop that away. Dissolve the sodium thiosulphate. So we've got the same concentration sodium thiosulphate every single time, but we've been increasing the concentration of the citric acid. We've done that twice so far. I have. I'm hoping that you've done the 0.3, I'm hoping that you've done 0.25, 0.3, 0.35, 0.4, 0.45, that you've got your own results. Okay, I know it takes a long time, you know, making up the solutions every single time, but not everything happens like at McDonald's. Not sponsored by McDonald's here. Just read that for a long time, McDonald's sales went down. People are buying less McDonald's. Probably mainly because the prices of it have been going up and up and up. When prices go up, usually demand goes down. Okay, that's my sodium thiosulphate. Pop that over the logo. Got my stopwatch ready. Stirring rod ready. Pipette. I need to put in 0.2. Oh, not 0.2. I need to put in 2 ml of the citric acid solution. Make sure it all goes in there. Start the stopwatch. 2 quick stirs. So we've been having the same starting conditions every single time. That's been very important. Always keep things the same. Only ever change one thing. And in this case, what we changed was the concentration of the citric acid. So the citric acid concentration is what we call the independent variable. That's the one that we changed. What we're measuring is the time it takes for this reaction to go to such a point that we can't see through the mixture anymore. That's the dependent variable. So the time depended on the concentration. So when we do the graph, this is a bit surprising for some people, but the time doesn't actually go horizontal. No, it's the independent variable, which is the concentration of the citric acid, goes on the horizontal, and it's actually the time, the dependent variable, will go on the vertical axis. Now, I don't want to look at the stopwatch because I know that that does bias. It biases me. Now, the word bias means to change an opinion based on some preconceived ideas. So I don't want my, this is, I'm trying to make this what we call objective as possible, me looking at how long it takes for that logo to disappear. I don't want to be, I think it's subjective if you're using other biased information, so I want to be as objective as possible. But in actual fact, that's almost gone. That logo, oh, I think I can't read it. So close. Getting there, getting there, getting there, getting there. It is difficult to tell, I must admit. Stop. Okay, 2 minutes 12, 120 plus 12, 132 seconds. I'll write that down. Now, it is important to wash this out and empty this out fairly quickly because it can tend to stain your glassware, that mixture. So it is best to give your mixture a nice washout. Your beaker's a nice washout. Citric acid, that won't stain your glassware. All right, so let's do the analysis. Let's do the title. It's rate of reaction, V concentration. Always have a title on your graphs. The independent variable goes down here, which is the amount of citric acid. We could work that out in terms of its grams per mil, but we'll just write down the amount we use. So 0, we're going up to 0.5, and so I'm going to go up by 0.05, so 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5, and the time in seconds, the maximum time was 180, so I might go up by 20s, 20, 40, 60, 80. Notice I'm labelling the lines, 120, 140, 160, 180, 200, and so for 0.25, which is here, it was 180, so I'll put a nice big cross there. Then 0.35, oh, made a mistake here. It's not, the cross should not be there. I'll put a circle around that. It's 0.25 grams, which is actually here. 0.25 grams, which is here. My mistake. Let's put a cross here. 180. And then for 0.35, it was 169, which is a little bit less than 170. So I'll put a cross there. And then for 0.5, it was 132, which is about here. And so I need more information, but I might do a graph like that. I'm not sure. Don't think it would be a straight line. I think it will be a curve. Okay. I think I could have done better than that. I wish I had more data points, but I don't because I only have 3 data points. You'll have more data points. What this sort of tells me is I do need to do some more investigations. What would be the time with like 0.1 grams? You know, it would be a lot longer, but it will help me decide whether it's a like a directly proportional relationship or whether it's we got some curvature happening. But we can definitely say as the concentration went up, the time of the reaction went down, which meant that the rate of reaction is increased with increasing concentration. 100% we can say that straight out. It would be good to have a non-biased way to determine the end point, and I think the best way to do that would be to shine a light down and have a light sensor, and when the light sensor reaches a certain point, that's when you can stop the time. That would be a better way of doing it. And of course I need more values myself. Hopefully you've got more of those values, but we can definitely say for the conclusion, as concentration increases, so does the rate of reaction. There we go. Big lesson. Thanks for joining me. Hopefully you've learnt a lot this lesson. Bye for now. Hey everyone, in this lesson we're going to be looking at how temperature affects the rate of reaction, and we're going to be using the same reaction that we've done previously, and that is sodium thiosulphate and citric acid. And when those two colourless, clear colour solutions are mixed together, it goes cloudy due to the production of sulphur. And the faster the reaction goes, the quicker it goes cloudy. So the cloudiness is a way to determine how quickly the reaction has proceeded. And so we're going to be using the same concentrations of sodium thiosulphate and citric acid, but we're going to be increasing the temperature each time. So first thing to do is to make up some sodium thiosulphate solution. So we'll have a beaker and we'll do our 0.25 grams of sodium thiosulphate in 10 ml of water. So here we go. You probably are good at doing this by now. Thankfully, this experiment, we don't actually have to do the changing the sulfuric acid, changing the citric acid as much. Okay, now I might just pop the crystals onto the table. I'm actually pretty good now at selecting 0.25 grams. It's that big one and one middle size one. Oh, no, that was too big. I need a small one. There we go. 0.22 and that tiny one, 0.28. Let's put a slightly smaller one on. 0.2. Oh, I think I used that. That big one was too big. Having a range of sizes is actually quite handy. And that one, 0.27. Let's try one slightly smaller one. Yay, 0.25. Okay, I knew I'd get there in the end by selecting crystal size. Perfect. And so, let's whack this in the beaker and add 10 ml of water. So get it up to the 10 ml mark. Excellent. And we need the thermometer. Okay, we need the thermometer. And let's just give that a rinse. Okay, give the thermometer a rinse because it might have had something acidic on it. Okay, just not too sure. Give that a little bit of a shake. And you know what? I'm actually going to start it at 25. Okay, so I'm actually going to get it to 25. That's actually going to be my first value today. Now, it won't take much heat to get this to 25. Whoa, sugar, I just spilt some. Don't shake it, stir it. Okay, don't shake it, stir it, please. Okay, we only want 25 degrees. It's not going to take long to get to 25 degrees. And we need that sodium thiosulphate dissolved. So it's taking a bit to dissolve. 22, 22 and a half. Mixy, 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 mixy. I think my fire went out. So I have to light that back up. Okay, it's at 26. I'm going to take that off the heat now. I'm just going to leave that temperature probe in there. And I now need half a gram of citric acid. Half a gram of citric acid. So let's get half a gram of citric acid. Tear 0.5 grams. Perfect. Put that there. Tap that in. Perfect. And how much water? 10 ml of water. Great. Just give my stirring rod a rinse. And I'm going to use this as what I call the stock solution. I don't need to make more citric acid up now. Okay, 10 ml is absolutely perfect for 5 trials. As long as I've dissolved it properly. Very good. Excellent. Okay, so that's my citric acid. I'll pop it here. Give the stirring rod a quick rinse. And wonderful, that's at 26.3 now, which is pretty close to 25. And so by the time I've sorted everything out, we'll be happy days. So I need to put the beaker of sodium thiosulphate over my logo. I might put it a bit closer to me so that I can see it. That's excellent. Then I need my stopwatch. And I need 2 ml of the citric acid solution. So let's get 2 ml. It's perfect. Squirt that in. Okay, get it all in there. Give it a quick stir, press the start, and we're off and running. Okay. Alright, so that reaction is now proceeding. Timer's good, 15 seconds, wonderful. Starting to see the first bit of cloudiness happening. Good. Pop your citric acid over there. That's great. Don't have to make up more citric. Oh, here we go. Here we go, here we go. So we're going to be doing 25 degrees, 30 degrees, 35, 40 and 45. I wanted to keep it, I didn't want the temperatures too high because it makes it easier to handle. Okay, Great. It's definitely happening. Again, it is difficult to decide exactly when to say stop. When I can't see any logo at all, I'm going to say stop. Stop. So 1 minute 13, so 73 seconds. 73 seconds. Good. All right. Press reset. And we have to rinse this one out well. Okay. Got to rinse it out very well. Rinsey, 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 rinse. Maybe it's just a double rinse. Good. And I'll need 10 ml of water. Like so. And I'll need the same amount of sodium thiosulphate, okay, which is 0.25 grams. Pop him on, tear him. I'm going to do my trick of tipping these crystals out and then selecting 0.25 grams worth, because I think I'm actually getting pretty good at that now. If you have a bit of a range, that big one's 0.19 gram, and then this little one is, whoa! 0.25! I've just set a world record for getting crystals. Fantastic. Okay, what temperature do we need? 30 degrees. Pop that there. Have the heat very gentle. It's important with the sodium thiosulphate because it can cause some big bumping to happen, that sodium thiosulphate. So just expect the unexpected. We're not going to be heating it up very much. I mean, we're only heating it up to what, 30 degrees or something like that. So it's not very hot. That might even be it. Let's find out. Okay, let's see, 23, 26, 28, 28 and a half, oh, I think 29, tiny bit more, I think. Just a little bit. That will probably be it, I think. I'll give that a bit of a stir. Yep. There we go. All right, 30. 31. Great. Okay, let's take this off. Get our thing ready like that. Good. Okay, that's now 30. Quick double check. Sometimes you need to wait for it just to cool down just a little bit. 28.4, 29.3, 30.1. That's close enough. I'll pop that over there. Good. I need 2 ml of my citric acid solution. So the same amount. Squirt that in, give it a stir, start the stopwatch. Okay, very good. Now I know I've got that burning, but it's with the gauze on, it's relatively safe, so I might take this off now. Now, the trick is don't watch the stopwatch. Watch the reaction. Yeah, I can see a cloudiness forming. Remember, we don't want to bias our opinion with the time. Now I'm expecting though, my hypothesis is that the higher the temperature, the faster the reaction rate. Because the particles are moving faster, the collisions are more violent, they're more energetic. There's more likelihood that the collision has got a greater, that more collisions have greater activation energies. Okay, all right, here we go. Watching. All right, the green is starting to fade. I'm watching, just looking with my left eye. My two eyes are not exactly the same actually. From the right eye it's gone, but from the left, no, stop. Okay, 1 minute 13, which is 73 seconds. What? Oh dear, it is what it is. I have got the exact same time. Without a lie, that's what I got. Oh well. Just going to record that time. Got to be honest. I mean, if I write down a shorter time, who am I? I'm not being particularly honest with anyone, not even with myself. So it's not a time I wanted, you know. Yeah, sometimes you think, oh, the experiment works. The experiment doesn't work. It works when you're getting the results that you think you want. And if you're not getting the expected results, you think that it doesn't work. Well, often in science, great leap forwards have been found from the unexpected. So the most important thing is you're just honest. Just be honest. Tare, what am I after? 0.25 grams. I need my tweezers, of course. Chunk. Just push them to the center. Okay, I need the smallest little crystal now. Oop. In fact, I could almost scrape the jar to get a smaller one. I've got a feeling I'm just going to start that again. Pop that on. Tare of 0. Big crystal. 0.1. 0.19. 0.26. Okay, that's close enough. And because it's 0.26, which is slightly over, I'm going to add slightly a bit more water. Just a slight amount. There we go. And put that there. Just going to put some of these crystals together over here. Use them for the next experiment. And now I need to get to, oh, having a bit of bumping going on now. Kind of bump, 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 bump. What do I need to get to? I need to get to 35 degrees. 35 degrees. Right, just give this a stir. Certainly need to dissolve all the sodium thiosulphate. And we need a 35 degrees. I'm only at 23. I can do a bit of mixing with the probe. 26, 27, 30. And it's on its way up, so I'm going to pull it off because I know it will just keep going for a little bit. 34.8, 35.1, 35.4, just what I thought. I thought it would just actually keep going up, and it did. 35.5. Just going to keep giving it that bit of a mix. and I can see that the temperature is dropping. Perfect. Pop in there, pop in there, and big squirt, quick stir, start. Okay, while that's happening, I'll just do a little bit of washing up. So this is the 35 degrees. So in this case, the independent variable, the variable that we're changing, is the temperature. We're keeping everything else the same. We're keeping the concentration of the citric acid the same and the amount of citric acid. We're keeping the amount of sodium thiosulphate solution the same beaker. And the only thing we're changing is the temperature, and the dependent variable therefore is the time. Okay, so the time is what? The time depends on the temperature. So in this case, the temperature will go on the horizontal, and again the time. Ready, set, stop. Okay, 53 seconds. All right, that was a there we go. That was a reduced time by 20 seconds. Interesting. All right, keep him out. Nice rinse. Another rinse. And 10. And I need to get my scales. I need the same amount of sodium thiosulphate. Tear. Boom. Boom. Slightly over. Might put replace that with a smaller crystal. 0.26. Good job. Great. Let's put him on some safety glasses. Whoa, does like to bump. Okay, it does like to bump. That sodium thiosulphate likes to bump, so we've got to be super careful about that. So gentle flame only. Hold with the tweezers, because we are getting some bump, and we're after 40 degrees this time. Okay. Dissolved. Not sure what the temperature is. I'll know in a moment. 28, 32, 34, 35, 36. I think it needs a little bit more heat. 37, 39, no, 38, 39, 40, 41. Okay, so she's gone past that 40, but it will cool down quite quickly, which is good. By the time I get myself organized here. Now, you know what? I'm not going to do the 45 degree one. I'd like you to keep doing it. I'll do this one, but I'm not going to do the 45. You can keep doing the 45. Otherwise, this course, the videos will just be so long, and it's unnecessary because I'll have enough data to do a good graph. You'll have even more data because you'll be doing it yourself. So I'm just here to facilitate, not to do everything for you. So if you think you've just come here and you can get all the results, well, you're wrong, because I'm not doing it all. You need to be doing this course yourself. That's how you learn. It's easy to watch someone else do it. Okay? Squirt it all in. Get in there, get in there, get in there. Give it a quick stir. Around we go. Start the stopwatch. Okay. Best if I had a helper. Help! Help! No one here to help. Whoa! It's going cloudy a lot quicker than I thought it would be. Wow. That's for sure. Okay, I better keep my eyes on it. Better get my stopwatch ready. Wow. Stop. 32 seconds. That happened much faster than I thought. 32 seconds. Wow. Incredible. Very interesting. Temperature clearly makes a big difference. Okay, so let's graph this together. Okay. Title, reaction rate versus temperature. So this time we'll put the temperature on the horizontal. Degrees Celsius. And you know what? I'm going to start at 0 and go up by 10s. 10, 20. Notice I'm labeling the lines. 40, 50, 60, 70, 80, 90, 100. And time in seconds. What was our maximum time? 73 seconds. I might go up by 10 seconds again. 10, 20. I always like to try and start my graphs or the axes at 0 if possible, and always go up by equal amounts. And so my first trial was 25 degrees with a time of 73, which is nice, which is about there, and I'm going to put a nice cross. The next temperature was 30, and it was the same temperature. That was a bit surprising. And then 35, it was 53 seconds. 55 was 53 seconds. And then 40 was 32 seconds, which is down here. So interesting. We need more data, but I'm going to make a bit of a call that it's always going to take some time. You're not ever going to have like 0 time, but we are going to get closer and closer and closer to this x-axis. So I think if we do it, if there was a few more experiments done, we could extrapolate from our data and say at 50 degrees it should take about 15 seconds, and at 70 degrees it will take about 4 seconds or something like that. So we could actually extrapolate and see whether this graph is actually predictive. It's never going to be actually an instant, so it can't actually be a line like this. So discussion would probably be to do a 50 degree one, and also a, like a 10 degree one, which, might be all the way up here, which would be like, I don't know, 180 seconds or something like that. But the trend is definitely that the temperature has a very big impact on the rate of reaction, and that the higher the temperature, the faster the rate of the reaction. There we go. Thanks for joining me today. I look forward to seeing you again soon. Bye for now. Hey everyone, in this lesson we're going to be looking at the combustion of butane. Now, combustion is another word for burning, and the fuel that we've been using in our, well, we should be using in our Bunsen burner is a very highly purified or refined, ultra pure butane fuel that comes in these skinny cans. Now, there's quite a few brands of this. Samba from Bunnings, this one I've just bought off eBay, but I've seen about 4 brands, and the ones I've noticed work best are the ones in the skinny can. And by now you would have been have put a lot of this gas into the Bunsen burners, and this gas is used for a very specific reason. Like, it's a hydrocarbon, which means it's got the carbon atoms as the base chain, I guess, surrounded by hydrogen atoms. And the simplest hydrocarbon is actually methane. And methane has got 1 carbon atom surrounded by 4 hydrogen atoms. So that's methane. And it's a gas at room temperature and pressure. Now, ethane is 2 carbon atoms surrounded by, I've got to get this right, 6 hydrogen atoms. Methane, ethane, propane. Propane is a gas at room temperature and pressure, and it's got 3 carbon atoms surrounded by 8 hydrogen atoms. That brings us to butane, which has got 4. A molecule of butane has got 4 carbon atoms surrounded by 10 hydrogen atoms. Now, why does our Bunsen burner use butane? Why doesn't it use methane, ethane, propane? Why doesn't it use pentane, which has got 5 carbon atoms? Well, the reason is butane, okay, it's a long enough molecule that it will actually, under a small amount of pressure, form a liquid like this. So this liquid, this clear colorless liquid, is butane. Well, millions and millions, billions, trillions probably molecules of butane. But if you take the pressure off by releasing it, it goes into a gas. So it's actually very close to being a liquid at room temperature and pressure. If you increase the pressure, you can actually have it as a liquid. Now, petrol, yeah, the liquid that you fill in your car. Now, in this United States of America, it's called gasoline, or they call it gas. Well, it's not a gas at room temperature and pressure, because otherwise you wouldn't be able to, like, use a petrol pumper to, have the liquid coming out. And petrol is octane. Methane, ethane, propane, butane, pentane, hexane, heptane, octane. It's got 8 carbon atoms, and it's long enough that there's enough attraction between the molecules that it's actually a liquid at room temperature and pressure. Butane, it's a gas at room temperature and pressure, and you need a gas to come out. Imagine if a liquid is trying to come out, it wouldn't work. You need a gas to come out, but you want to store it as a liquid, because when you store it as a liquid, it doesn't take up very much space. And so we can actually transfer it, and it sort of transfers a little bit as a liquid, but some of the gas sort of escapes, and when it goes from a liquid to a gas, it actually absorbs heat. It absorbs heat, which makes things feel cold, and that's why it's cold, and that's where what that looks like, the mist, that's actually water molecules coming out of the air and condensing into tiny little liquid droplets. Okay. Now, what we're going to do is we're going to get a beaker, yeah, like this, and we're going to, and I might actually get a watch glass ready for this, and a pack of matches, and just to be safe and not sorry, I'm going to put on some safety glasses. I'll just clean them on my shirt because they're a little bit foggy. All right, There we go. Oh, wow, look at that. I can see so much clearly. So much clearly, so much more clear. So much clearer. There we go. All right, so I've got my matches on the ready. Don't light them yet. And I'm going to, now I have to close these air holes because I want the gas to come out. I'd like to try and trap it. So 1, 2, 3, 4, 5. Turn that off, close that. Turn this off, turn this off. Make sure you turn this Bunsen burner off. Put it away because it's flammable. And let's get ready. Let's see what happens. Whoa, if we light this gas. Whoa, beautiful. I see some blue and some orange. And look, I see a little bit of mistiness. Yeah? I see some mist forming. I see some condensation happening on the inside. How can you get condensation when you've got heat, like burning? I can tell you because the beaker's still quite cold, and when you burn butane with the oxygen in our air, one of the products is actually water, and another one of the products is carbon dioxide, that big mean gas that produces global warming. Okay, what about if we try it in a conical flask? All right, the opening's not as big. Let's put some gas in. 1, 2, 3, 4, 5. I'll trap the gas there. Turn that off. Put this away out of the way. Don't want any accidents. And will there be a difference? I think there will be, because there's not very much room for oxygen to enter. Ooh. It's actually hard to see whether it's lit or not. Woo! The gas is there. The gas is there, but oxygen can't get in, and so it's not burning. Yeah? So, for combustion, you need a fuel, often a hydrocarbon, and you need oxygen. And so, the chemical word equation for the combustion of butane is, of course, butane plus oxygen, and that produces water and carbon dioxide. Now, butane and oxygen are known as the reactants, and the water and carbon dioxide is known as the products. So what's the balanced chemical equation? Well, 2 molecules, okay, 2 molecules of butane. So 2 molecules of butane, and butane is carbon 4, H10. So C4H10 plus how many oxygens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 oxygens. So 13 O2, because oxygen exists as a diatomic molecule. How many carbon dioxide molecules? 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbon dioxides. And we should really say that they're gas. And of course the oxygen is gas. And of course the butane is gas too. And how many water molecules? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 H2O gas. Now, let's see whether this is balanced. Because in a chemical reaction, you can only break bonds between the molecules, so break bonds between the atoms in the molecules, and then reform new ones. You can't create new atoms and you can't destroy atoms. And so in actual fact, the mass of the products is going to be the same as the mass of the reactants. And that's the conservation of mass in chemistry or chemical reactions. So how many carbon atoms in the reactants? Well, 2 times C4, so is 8 carbon atoms. How many over here? Well, 8 carbon dioxide molecules, so 8 carbons. So tick, there's the same number of carbons on either side. What about oxygen? Well, 13 times 2 is 26 oxygens. What about over here? We've got 8 times 2, that's 16, plus 10, that's 26. So check for the oxygen. Hydrogen, we got 2 times 10 is 20. And over here, 10 times 2 is 20. And so we've got a balanced chemical reaction. How good's that? Now, it's not really like 2 molecules react with 13 molecules of oxygen. It's like 2 trillion molecules of butane react with 13 trillion molecules of oxygen gas. Yeah? This basically shows the ratio. These numbers show the ratio of how they are chemically reacting. Does that make sense? Now, that doesn't mean it's 2 kilograms of that plus 13 kilograms of that. No, that's not true at all. But in terms of the numbers, that's what's true. And when you do, if you do, hopefully you do, like senior chemistry, there's a very, very large number. You know, when you buy eggs, you don't go and buy 2 eggs, right? You go buy 24 eggs, yeah? Which is 24 eggs. We have a very large number in chemistry called the mole, okay? The mole, M-O-L-E. It's a huge number, 6 times 10 to the 23. 6 followed by 23 zeros. That's how many atoms that we're talking about. So often we say things like 2 moles of butane react with 13 moles of oxygen to form 8 moles of carbon dioxide to form 10 moles of water. Anyway, that's okay. We're building up our understanding, aren't we? Now, this is the complete combustion of butane. What happens if we don't have enough oxygen atoms? What if you're burning 2 moles of butane, but you don't have 13 moles of oxygen available? Well, let's find out. And so we're going to need some water in a beaker, and I'm going to put my Bunsen burner back in its little home, like that. And I need my tweezers, okay, and I'll pop my safety glasses on. And let's just light up the Bunsen burner. It's a beautiful blue flame, okay? The Bunsen burner's got a beautiful blue flame there. And if I was to just hold the beaker above it like that for a little bit, the water gets, you know, hot as per expected. Everything looks a-okay, everything's normal. Okay, but what about if I get my 2 fingers, and we've got to be careful here that you don't burn yourself, but there's 2 little holes, one here and one here, and I'm going to block those holes. Hey, woo! Woo! Look at that. Lovely flare, isn't it? Hey? Yay! Woo! Oh! Now, this time if I go like this and go like that, I don't want to do it for too long. What I notice, whoa! Let's turn this off. All of a sudden I've got this black stuff that's formed on the bottom of the beaker. Now that can get scrubbed off, so don't worry about that. You haven't burnt your beaker. You've deposited. Is that a word? Deposited? I don't think so. No, I'm not even going to try. Carbon atoms. Carbon atoms. What do you observe on the base of the beaker? Black stuff. Black stuff. And it's soot. Okay, it's soot. It's actually carbon in the soot form. So when do we have the incomplete combustion of butane? Well, of course we've got butane, and we do have oxygen, but we end up with carbon, which is the black stuff, plus of course water, plus of course carbon dioxide. And there won't be 13 oxygens here. I can guarantee that. If there's 2 molecules or 2 moles of butane, there won't be 13 molecules of oxygen. It will be less than that. And when there's less than that for what the butane needs for a complete combustion, you're actually going to end up with some soot in the form of carbon. Anyway, there's the lesson on combustion and incomplete combustion of butane. All right, bye for now. Stay safe. Look forward to seeing you again soon. Bye-bye, everybody. Hey all, in this lesson we're going to be looking at what's called the heat of combustion of butane. That's basically asking what's the energy content, what's the chemical potential energy content of like a gram of butane gas. Like how much work can you do with this? How much, water can you heat up to a certain amount with the gas in this can? Knowing the energy content of different substances, particularly fuels, is really important. So for example, if you put petrol in your car, that's octane, and octane has a certain amount of energy per litre. But what about if you put like a biofuel, like ethanol? Does a litre of ethanol have the same amount of energy as a litre of octane fuel? And the answer is no, it doesn't. It's got less. So if you're buying fuel that's got 10% ethanol, it's actually not going to go as far. It's not going to move your car as far as if it was just pure petrol. So make sure if you buy your fuel that's got ethanol that you're not paying the same price as regular fuel because, well, you're not getting bang for your buck, basically. I mean, it might be a little bit better for the environment because the ethanol might be coming from sugarcane or something like that. But anyway, how are we going to do this? Well, to measure it, we're actually going to use the gas to heat up water because I know that it takes 4.19 joules of energy to heat 1 ml of water by 1 degree Celsius. Right, so it takes 4.19 joules of energy. Now, a joule is actually a very small amount of energy. 4.19 joules of energy to heat 1 ml of water by 1 degree Celsius. Now, the first thing we need to do is know how much gas we've got. So that's our first thing that we need to do. And so I will fill that up with gas and just let that settle down a little bit. I'll need my scales and we're going to weigh the Bunsen burner with the gas in it. So it's the starting weight, the initial weight. Just waiting for it to stabilize. Let's pop that there. And the Bunsen burner with the gas in it is 53.97 grams. Okay, so 53.97 grams. All right, that's the first thing. Now I need to get 10 ml of water. Okay, 10 ml of water in a beaker. So I've got a beaker here. Now I probably should use my measuring cylinder, but you know what? Oh, you know what? Come on, be accurate. Be as accurate as I can. Okay, so let me just shake that out. Let's be accurate, because I can tell you a beaker is not a particularly accurate measuring device, and a measuring cylinder is much, much, much more accurate than a beaker. I can assure you of that. All right. 5. Notice I'm getting eye level right down to it, measuring from the bottom of meniscus. Very good. Pour that in, and if I have a look, oh, it's right on the 10. No, it's not bad accurate. It's not bad accuracy. All right, now I'm going to need my thermometer on the ready, and so I'm going to use my retort stand because it's a very good way to hold the thermometer probe in. So I'm going to use the red fitting, and I'll need my small peg. Perfect. Push him in. There we go. And I'll need my thermometer. Perfect. And I actually have to work out, first I have to know what the initial temperature of the water is. This is quite important. Okay, so I actually have to, I definitely need to know the initial temperature of the water. So where do I record that? Calculate that according to the chemical data. Calculate the energy of combustion used equals the amount of gas. Okay, results for the water. Okay, all right, yeah. So where do I write the initial temperature? T is the initial temperature down here. So basically, I'm doing a comparison. That's what we're doing. We're doing a comparison between the theoretical, okay, the theoretical amount of energy in butane compared to what we find. And so see this formula down here, QT, that's the heat energy given out by the Bunsen burner is equal to C, which is the specific heat capacity of water, which is 4.19 joules, which I mentioned before, times M, which is the mass of water. And don't forget that 1 gram of water is actually 1 mil of water, times TF, the final, minus the initial. So in this case, the initial is 18.5. So I'm going to write 18.5 degrees here. All right. Then I'm going to get ready because this has to be done quite quickly. Once I light that Bunsen burner, I actually have to make sure I start heating. I have to start heating the beaker and making my measurement as quickly as I can. So here we go. Are we ready? In fact, I need to capture all the heat that I possibly can. So I'm actually going to set it up. Oop. Put that match down. Take that. Pop that in here. There we go. Oh, that holds that nicely. Very good. I might just lift it. I'm going to twist that around a little bit, just to lift it up a bit, so it's not quite sitting on the bottom. That's actually really, really good. I'm happy with that. 18.5. Okay. And get ready to light my Bunsen. There we go. Perfect. Blow this out. And I don't actually need to time it because it's the amount of energy. It's not the power. It's the amount of energy. It's not the power. Now, I have to make sure I stop it before it starts boiling. All right. Once the water boils, then I lose track of how much energy is going into it. So at the moment it's 30 degrees, and I'm going to keep the Bunsen burner going quite well. Okay, you want a nice firm burn, basically. Don't want to waste too much time here. We want this to happen fairly quickly because we're actually losing energy. We're losing energy from as energy is radiating outwards. We're not actually getting all the energy from that Bunsen burner, from that butane, into the water. Not with this equipment. And in fact, the longer it takes, the more energy we're losing outwards. So that's why I need this to be done quite quickly. And so I'm really sort of like boosting it up. We're at 60 degrees here. So this is very, very good. I am using up the gas, which is good because I actually need to use up the gas because there has to be a weight difference. And 73.8, 76.1, 78.1, 80.1, 80.2, 84.3, 86. I'm going to turn it off right now. I'm going to turn it off because I know that the temperature is going to keep going up because there's heat in this system. There's heat in the tripod. There's heat in the wire gauze. It's gone to 93.1. It's still going up, not as fast, 93.4. And so I want to get as much of that heat into the water as possible. 93.8. And so I'm waiting for the maximum heat. In a moment, the heat will start coming, the temperature will start falling. That's probably going to be about now. 93.9. It just dropped. So now it's 93.8. So it got to 93.9. So this was the final temperature, which I'm going to write here, 93.9. Okay, now let's go back up here to where it says the final weight of the Bunsen burner, because we're going to work out how much gas we used. So I'm going to pop this here. Now don't forget that this will be hot, so the tripod and wire gauze will be hot. Why am I doing it over the beaker? And then pop this here. Now don't forget that the Bunsen will be a bit hot too, so don't grab it with your, don't grab the top with it with your fingers. All right, now we're only going to have used a very small amount of gas. Okay, so I'm not expecting there to be much of a weight change, but I hope the number has gone down, because otherwise, oh well, we've just broken chemistry if the number hasn't gone down. No, in reality, if the number hasn't gone down, then there's a problem with the scales. So, crossing my fingers here. The original weight was 53.97, and now the new weight is 53.55. Woohoo! The mass has gone down. Not by much. We haven't used much gas, but we have used some. Okay? 53.55. So it says calculate the amount of gas used, which is the initial weight minus the final weight, which is 53.97 minus 53.55. Now, some of you clever people can do this in your head. I probably can too, but I'll embarrass myself. So I'll just go 53.97. Turn on the calculator first though. 53.97 minus 53.55 gives me 0.42. So almost half a gram. So I've used half a gram of butane to heat 10 ml of water from 18 degrees up to 93.9. Now, according to chemical data sources, butane has an average, has an energy of combustion of 45,000 joules per gram. So if you go on the internet and try and find out how much energy there is in, you know, a gram of butane, the data will say it's 45,000 joules, which is 45 kilojoules. The kilo stands for 1,000, so 45,000 joules. Now, we used about half a gram, so it's going to be about half of that. So we can calculate that. Calculate the energy of combustion of the amount of butane you used. It's equal to the amount of gas used, which was 0.42, times 45,000. So 0.42 of 45,000 equals 18,900 joules. So we've used 18,900 joules worth of butane gas to heat that 10 ml of water up. Seems like a lot of joules, doesn't it? Well, hydrocarbons are actually very energy intensive. That's why, you know, a tank of fuel in your car will go so far. You know, some cars with big tanks can, you know, go from New South Wales to, you know, Brisbane, Sydney to Brisbane, you know, like 900 kilometres on a single tank of fuel. That's because there's so much energy in liquid hydrocarbons. All right, but practically, let's find out what we worked it out to be. So we heated to heat 1 ml of water by 10 degrees Celsius. Oh, I've made a mistake, so I'll fix that. You won't see this mistake in your worksheet because I'll have fixed it. To heat 1 ml of water by 1 degree Celsius requires 4.19 joules of energy. Calculate the mass, the increase in heat energy of the water by using the following equation. C is 4.19. See, here's the thing, right? It takes 1 joule to heat 1 mil of water by 1 degree Celsius. But if you're heating oil, it doesn't take 4.19 joules to heat 1 mil of oil by 1 degree Celsius. It takes less. It probably takes about 2 joules of energy to heat 1 mil of vegetable oil by 1 degree Celsius. So if you have a pot of vegetable oil and a pot of water and you put them on the same stove, the oil will actually heat up a lot quicker because it doesn't actually take as much energy for it to change temperature. So they'll still have the same energy, you know, like oil at 100 degrees will have the same energy as water at 50 degrees, yeah, but they'll be at different temperatures. So that's what this sees. The mass is 10 mil, and so we got 4.19 times 10 mil, because that's what we used, times 93.9 minus 18.5. So we need the temperature difference. We need to know how many degrees we heated it up by. So I'm going to go 93.9 minus 18.5. So we heated it up by 75 degrees. I'm going to times that by 10 because it was 10 mils of water. So that's 754. Then I'm going to times it by 4.19 because it's water. And that gives me 3,159. 3,159 joules. So, practically, I've worked out, right? That I used, that the water energy, the heat energy of the water increased by 3,159. But in actual fact, it took 18,900 joules of butane to do that. So the very big question is, where did all the energy go? Or have I made a terrible mistake? Now, I don't actually think I've made a terrible mistake. I think most of the energy, and if I had a thermal camera, most of the energy actually, firstly, a lot of energy went into the tripod, right? We didn't measure that energy. And a lot of the heat energy would have just gone straight up and around. Energy's also gone into the glass, which we didn't measure at all. And also throughout the experiment, it would have been radiating heat. So basically, most of the energy that I used using the gas burner didn't go into the water, which is very interesting because it sort of shows you how inefficient it is in terms of using gas energy, like heating something up in a saucepan using a gas flame. So, in fact, I knew it was going to be much lower because I wrote down here, why do you think this value is so much lower than the energy value calculated in 1? So I anticipated that the energy value that we calculated would be so much lower, okay? Now, basically, somehow you've got to work out how to heat that water directly. And a scientist called Joule actually did that. And one way that you actually do that is you have like a combustion vessel inside the water. And then you totally insulate the vessel. And so almost all the heat from that combustion goes just into the water. It doesn't go into the atmosphere and all the rest of it. But it's a very interesting practical, don't you think? Now, you could actually do similar things with candle wax and heating water with a candle and looking at the efficiency of that. So anyway, hopefully you found this lesson very, very interesting. I know it sort of jumped around a little bit, but we got there in the end. All right. Thanks for joining me, and I look forward to seeing you again soon. Bye for now. Hey everyone, in this lesson we're going to be looking at or finding out the mass and the energy content of a match. So, what do you think the weight of a match is? How heavy is it in grams? Make an estimate. Okay, make an estimate. Don't cheat. Well, 1 mil of water has a mass of 1 gram. So a centimetre cubed of water has a mass of 1 gram. I'm going to guess 0.4 grams. That's my guess, not 0.4 grams. And I really don't know. Okay, it really is an estimate. Okay, so let's use the scales. Hopefully they're heavy enough to actually register on the scales. I'm a little bit concerned here. Let's find out. This will really be a test of the old scales. All right, 0.00 and drop the match on 0.14 or 0.13. Wow, I was not that close. 0.14. Let's get match 2. Tear it. Pop him on. 0.15. Very similar. Match 3. I'm using redhead matches. Oh, that one's burnt. My guess is that it will be a little bit lighter. I'm actually very impressed with these scales. Oh, that match is a bit heavier, 0.16. Oh, look, 0.14, 0.15, 0.16. Does that mean the next one's going to be 0.17? I don't think it works like that. 0.16. You know, there's someone at the match factory who weighs every single match. Not true. And 0.15. So how do we work out what the average is? We add up all the numbers and divide by how many there are. And I can see that the average is going to be, I'm going to guess the average is going to be 0.15. That's my guess. So I'll go 0.14 plus 0.15 plus 0.16 plus 0.16 plus 0.15 equals, divided by 5. Now, it is good to have the average is 0.152. It's always good to have a little bit of a think about what the answer is going to be, because if you get an answer that's wildly different to what you actually think it's going to be, then maybe you've made a calculator mistake, or maybe you haven't understood something. So I always like to try and have a little bit of a think before I just blindly put something in the computer. All right, so we're going to use the heat from the matches to heat up water to work out their energy content, because don't forget it takes 4.19 joules of energy to heat 1 mil of water through 1 degree Celsius. So we need 10 mil of water, and I discovered that on this particular beaker, the 10 mil line is actually very, very accurate. But I do have to come down here to avoid parallax error and make sure the bottom of the meniscus is on the mark. Now, need the tweezers. Okay, need the tweezers. Take the wire gauze off. No wire gauze this time. We're going to stand the beaker on the tripod so that I can directly heat it with the match. Now I'm going to pop this in here and just lower it a little bit. I really do like these retort stands. That's very, very good. And the initial temperature, the temperature at the beginning, it's a very important temperature, is 17.8. So 17.8, and now I'm going to heat it with the 5 matches in succession. Okay, the 5 matches in succession. So here we go. I need to capture as much of the heat as possible. This is going to be a bit tricky. So now there's a bit of soot That's okay. Bit of soot happening. I can see the temperature going up, which is good. Okay. I'm at 22 degrees, so I don't want to talk too much because that blows the... Oh, lost a bit of the fire there. Let's go to the next one. Oh, this is tricky. Now, if you do burn yourself, if you do burn yourself, put your burn under cold water. If it's significant, seek medical advice. Here we go. Now, this is a pretty ineffective way to determine the energy. Oh no, I've got a little bit burning there. The energy content of a match, because we are losing so much, okay? We are losing so much of the energy, which is not good at all. A lot of the energy is just going way out of the water. You know, it's going around the beaker. Anyway, with this equipment, this is about as good as I can get it. Oh no, just lost a lot of heat there, that's for sure. Oh, if you got a better way, let me know. Make sure there's no flammables around when you're doing this. Whoop. You know why we've got to do it quite quickly? Because we lose energy to the surroundings. Oh, that was a bad one. We're losing energy. It's cooling down. It cools down as well. Ooh. Oh, that match burnt very interestingly. Okay, and we're going to go up to the, see what the maximum is. 46.5, 47.4, 48.7, 49.7, 50.2, 50.8, 51.1, 51.5, 51.8, 52.1, 52.4, 52.6, 52.8, 53.1, 53.4. There's obviously still heat in the tripod, you see. 53.7, and that heat from the tripod is actually heating up the water still. So I'm waiting for the absolute maximum temperature. 54.3, 54.4. Still going up. I'm quite surprised here. 54.6, 54.8. It's definitely going to start dropping in a tick. 54.9. Wow, 55.1. Still going up. This is very surprising. 55.3. Oh, 55.4. This has got to be it. 55.5. 55.6. How is it still going up? 55.7. Will you hurry up? 55.8. Oh. 55.9. Ah. Will it get to 56? 55.9. And that's it. I'm going to call it 55.9. 55.9. So the temperature change is final, which is 55.9 minus the initial minus 17.8 equals 38.1 degrees. So we increase the temperature of 10 ml of water by 38.1 degrees using 5 matches. Now, up here it says estimate how many joules of chemical potential energy a single match has. Now 1 gram of butane, 1 gram of butane has an energy of 45,000 1 gram of butane has an energy of 45,000. So this is about, I can use a calculator because I want to see how many matches it take up 1 gram. So I'm going to go 1 divided by 0.152. So there's 6.5 matches. So if they were made out of butane, 45,000 divided by 6 matches, be 7,500, but they're not butane, but they are hydrocarbon. I'm going to estimate one match has got an energy of 5,000. So wood, I'm saying for a match, 5,000 joules. That's my guess. Okay, all right. Now we have to do this a second time. Okay, we've got to do this a second time. And so let's tip him out. Start with the same conditions. Oh, look at the soot. Look at the soot. Have to clean that soot off. I've got a little bit of a scourer here. Should take it off. Yeah. Okay, need to have the same conditions. Just going to cool down the beaker with this water first. So I've put a bit of cold water in there because I actually want to cool the beaker down pretty quickly. Because I really need to have very similar starting conditions. That's quite important actually. So let's get 10 ml of water. Perfect. And look, there wasn't very much variation in the mass of matches, so I'm going to make an assumption. And okay, that tripod's cooled down a fair bit. Let's pop that in and see what the temperature is. So because the mass of the matches are very similar, I'm not going to weigh out 5 matches and find 5 identical matches. Okay, I just don't think that's necessary. So I get 5 matches, and it appears that my starting temperature is going to be a little bit higher than last time. I'm not surprised because of course the tripod is a little bit warmer. The beaker still had a little bit of the warmth there. So it's 19.3. Close enough. Okay, here we go. Let's get some. And notice I'm lighting the match really, really close so that I'm going to try and do better this time. I'm going to try and increase the temperature difference by doing a better job by burning more of the match. That's my goal. One. Got that good flare happening. You can actually do experiments of energy content of food like this as well, where you burn like tiny teddies and matches, not matches, but like cashew nuts. There's lots of different foods which are quite flammable. I'm at 37.5. Ooh, don't breathe. It's not very good. The flames at either side, I'm losing some of that heat. That was not a good way of doing it. Not all the match is burning either. better job. Oh, the flame's too wide along the match. I'm not getting the heat into the beaker. One to go. I'm at 54.4 already. I think I've done a better job. I think I've been able to collect more of the heat. Yeah, I'm gonna go past 60. I know I started a little bit higher, but okay. Oh, there's some fire there. Okay, 62.6, and of course it's going to keep going up for a little bit like last time. 63.1, 63.3. La 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 la. La 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 la. 64.4, 64.5. I think it might be 10 degrees higher. 64.8, 64.9. 65.1, 65.3, 65.5, 65.6. That's it. Up 65.8. Just dropped 65.8. 65.8. So, what's the temperature change? Final minus initial, 65.8 minus 19.3 equals 46.5. 46.5. Okay. Now, I'm going to get an average of those two numbers. I'm going to use the average. Okay. Although there is a significant difference between the two. I'm going to use the average. 38.1 plus 46.5 divided by 2, 42.3. Okay, so I'm going to use 42.3 degrees Celsius as the temperature change. Calculate the energy increase of the water using QT. So QT is the energy increase. So it's equal to, all right, C is 4.19. That is the specific heat capacity of water. That is how much energy is required in joules to heat 1 ml of water by 1 degree Celsius. Now there's 10 ml of water, which is 10 grams. Yeah, 10 grams. Times by the temperature change, which is 42.3, which is 4.19 times 10 times 42.3 equals 1,772 joules. Hence, calculate the energy content of each match. Divide that by 5. Gives me 354. 354 joules. Now, I estimated 5,000, so I'm way under. Discuss the reliability of the two trials. How similar, different? They're actually quite different, these two trials. Did I get better at capturing the heat? I think so, maybe. Didn't really feel like it, but so they are different. So that I'd really want to do a third trial to really comment on this. It says discuss the validity of this investigation. Now, to do this properly, well, there's a few things that you want to do. You want to go on the internet. Ideally, you want to find out what type of wood matches are made from. I know they are made out of poplar in the old days, but these are not the old days, of course. These are the new days. It wouldn't matter too much, I don't think. Well, it wouldn't matter what the energy, what type of wood it is, but let's say it's poplar. You can find out what the energy per kilogram of poplar wood is and divide that by 1,000. So that we've got a theoretical amount, yeah? So there's a theoretical amount of heat energy. Then you can compare, you could change, so one match is 354. You could find out, doing a little bit of a calculation, how much energy there is in a gram of matches. That's not too difficult to do. And then compare those two results. And your result's going to be a lot less, because we just lose so much in terms of the process that we used. If you want to do this really properly, you need to have a vessel of water with a stirrer in there. Has to be fully insulated. And on the inside there's a chamber, and you put powdered wood with a chemical, a powdered chemical that has got oxygen in it, that releases the oxygen. And so that there's enough oxygen to burn. And then you have to have an electrical sparker or electrical heater to actually ignite the wood. And so the wood actually burns inside the vessel, inside the water. And so that all the heat of the combustion goes into the water. It's mixed around nice and evenly, and you can measure the temperature. That way you don't get any heat losses, and that you'll get a far more accurate result. So there we go. Thanks for joining me, and look forward to seeing you again sometime in the future. Bye for now. Yay! Congratulations on completing the Year 9 chemistry course. Whoa! What a marathon. What a lot of science we did. Wow. I think this was one of the longest courses that I've ever produced. And hopefully you've been able to do virtually all of the experiments and have learned a lot along the way that you've kept safe, and that you're invigorated to continue with chemistry and apply it to your everyday life. So I'm looking forward to seeing you again in the future, and until then, stay safe, be well, and bye for now. Okay.